This might be the most important question raised by our new knowledge of the galaxy. Nicolas Chauvin was a legendary character in French folklore, a man whose enthusiasm for his country was so great that his name is now attached to any attitude that involves, per the dictionary, excessive or prejudicial support for one's own ideas. In the sciences, the term chauvinism is usually used pejoratively to describe a position that precludes inquiry beyond generally accepted ideas. The ancient Greeks, for example, might be described as geocentric chauvinists, since they refused to consider the possibility that the Earth was not the center of the universe. Thinking about exoplanets, and particularly about the nature of life on those planets, is full of chauvinisms. The most common of these, carbon chauvinism, is the notion that life elsewhere must be based on carbon. For the record, both authors plead guilty to being carbon chauvinists for reasons that will be explained later. There are, however, two other chauvinisms that, while widespread, are less well known. We call them surface chauvinism and stellar chauvinism. Surface chauvinism is the idea that life has to exist on the surface of planets. This is what lies behind the search for the Goldilocks planet, for example. Yet it is actually a strange notion for terrestrial scientists to have. After all, we know that on our planet there are complex ecosystems at deep sea vents, miles below the ocean surface. We also know that there is bacterial life in rocks, miles below the surface of the continents. In fact, some biologists have argued that such organisms make up the majority of Earth's biomass. Why should exoplanets be different? Stellar chauvinism lies a little deeper in our subconscious. It is the idea that planets, at least planets capable of supporting life, have to be in orbit around stars. One of the great shocks in the search for exoplanets has been the dawning realization that most of the planets in our galaxy are not attached to stars. We call these rogue planets, and imagine a visit to one in Chapter 7. We discuss what kinds of life they might support in Chapter 13. We don't know what other kinds of chauvinisms may be hidden in our minds, but recognizing the ones we've outlined is a good way to start our journey through exoplanets, both real and imaginary. It makes sense that the first region that humans would explore when they turn their eyes to the heavens would be our own solar system. After all, in astronomical terms, the moon and our sister planets are our neighbors, closer to us than anything else in the sky. How could we avoid investigating them first? The origin of human knowledge of the solar system is lost in the mists of antiquity. Monuments such as Stonehenge show that people with no written language and, indeed, no metal tools could nonetheless possess an astonishingly detailed knowledge of the motion of the sun, the moon, and the planets. We know that the great ancient civilizations were aware of the planets. The Greeks, for example, assigned each of them to its own crystal sphere in the sky, and the appearances and disappearances of Venus may have influenced the development of the Mayan number system. Nevertheless, it wasn't until 1609 that Galileo Galilei, 1564 to 1642, turned a telescope to the sky and encountered the first of what would turn out to be a long string of paradigm-smashing surprises. In Galileo's time, the cosmology that was taught in universities, and that Galileo presumably would have learned, was that of the ancient Greek philosophers. This cosmology taught that Earth was the unmoving center of creation, and that once we got away from Earth, where there is change and decay, everything in the heavens was perfect and unchanging. Thus, Galileo's paradigm told him that the moon had to be a perfect crystalline sphere and the sun a perfect spherical ball of fire. But that's not what he saw. On the moon, he saw mountains, craters, and other imperfections, while on the sun, he saw a series of blemishes that we would call sunspots, or more likely, sunspot groups. Most telling of all, when he looked at Jupiter, he saw 4 stars, his term, that were clearly orbiting the giant planet. Whereas his paradigm told him that everything in the heavens had to be circling Earth. His data were telling him that some objects seemed to be perfectly happy orbiting Jupiter. These bodies are now known as the Galilean moons, though Galileo, in an attempt to win courtly favor, called them the Medicean stars. The ploy apparently worked because he was subsequently given a position in the court of the Medicis in Florence. Galileo published his findings in 1610 in a book called Sidereus Nuncius, Starry Messenger. It seems strange to the modern reader that the book caused a stir, since it is basically just a catalogue of what he saw through his telescope. But because he wrote in Italian and was therefore reaching the educated population outside the church, the book made him enemies who later would try him on suspicion of heresy for a subsequent book. We don't have room to go into that somewhat convoluted story here, although we should point out that Galileo's abrasive personality probably didn't gain him many friends either. In any case, once the new Copernican concept of heliocentrism was accepted, ideas about life in other locations in our solar system were quick to arrive. Some of the early thoughts about extraterrestrials seem pretty strange to us today. For example, in the 18th century, several serious astronomers proposed that there was life on the Sun. Not on the fiery outer surface, of course, but in the hypothetically cooler interior. Some even tried to use their telescopes to peer through sunspots to see farms and villages below. And then there was the English country parson Thomas Dick, whose 1837 book Celestial Scenery, or The Wonders of the Planetary System Displayed, illustrating the perfections of deity and a plurality of worlds, confidently predicted that we would find 8,141,963,826,080 people living on the rings of Saturn. From the tone of the book, we infer that the learned cleric expected them to be Englishmen. As the 19th century flowed into the 20th, thoughts about extraterrestrials began to concentrate on nearby worlds, the Moon, Mars, and Venus. There was an almost universal belief that the Moon was populated. Indeed, in 1901, H. G. Wells, 1866 to 1946, published his novel, The First Men in the Moon. In this book, earthly visitors wander about the lunar surface without spacesuits and encounter a technologically advanced race of Selenites. In 1895, the American astronomer Percival Lowell, 1855 to 1916, published the first of 3 books about the planet Mars, titled Mars, 1895. Mars and its Canals, 1906, and Mars as the Abode of Life, 1908, in which he described his observations of the Red Planet. In these books, he developed a picture of an advanced civilization on Mars, a civilization that built a complex network of canals to bring water from the poles to the arid equatorial regions. He even reported the rate of poleward progression of vegetation with the seasons to 3 decimal places. Given that we now know that there are no plants or canals on the Martian surface, we have to wonder what Lowell actually saw when he looked into his telescope. The current consensus is that he was pushing his instruments past their performance limits and that he connected the random dots he saw into a pattern, much as people do when they take a Rorschach test. Nevertheless, Lowell was a prominent figure in American science, the founder of Lowell Observatory in Flagstaff, Arizona, and his ideas influenced novelists and dreamers for decades. They probably also played a role in the promulgation of a strange kind of evolutionary theory of the solar system that was popular in the 1930s and 1940s. The basic idea was that Mars, Earth, and Venus represented progressive stages in development. Mars, arid and desolate, was the home of a dying civilization, whereas Earth held a civilization in full bloom. Venus, which was pictured as being like the Florida Everglades, only more so, was where civilization would flourish in the future. This beguiling notion, which is a perfect example of what the French call a folie d'éclair, clear but false idea, gave rise to all sorts of science fiction stories in which the swamps of Venus and the deserts of Mars played important roles. The notion that there were other civilizations out there was also involved in the development of a fictional character that one of the authors, J.T., enjoyed as a child. Ming the Merciless, Emperor of Mongo, the villain in many Buck Rogers movies. By the time these ideas were floating around, however, scientists had realized that the moon had no atmosphere and no life. Today we know that there is no dying civilization on Mars, and if life does exist there, it is, as we shall see in a moment, at best microbial. Venus, with a surface temperature hovering around 460 degrees Celsius, 860 degrees Fahrenheit, has no swamps or oceans, and in any case is too hot to support the civilization of the future. Even though the notion of evolutionary progression had been dropped by the time serious exploration of the solar system began in the second half of the 20th century, there was nevertheless a real hope that we would find life more or less like the life with which we are familiar somewhere in our neighborhood. When the Drake equation, see Chapter 13, was first written down in 1961 to estimate the probability of making contact with extraterrestrials, for example, many scientists argued that life had developed elsewhere in our own solar system and inserted their estimates of the number of times this had happened into the equation. In a sense, you can read the last half of the 20th century as a period of progressive restrictions on the places life could be found in our solar system. When Apollo 11 astronaut Neil Armstrong took his giant leap for mankind on the moon in 1969, no one expected to find life on the lunar surface. Nevertheless, when the Viking spacecraft landed on Mars in 1976, there was a palpable sense of disappointment among both scientists and the general public that the onboard experiments showed no unambiguous evidence for the existence of life. Since then, a veritable flotilla of spacecraft from many countries has flown out to Mars, the most recent being NASA's Curiosity rover, which landed in 2012. These decades of exploration have established several facts about our nearest planetary neighbor. There were oceans on the planet early in its history. Evidence of the first flyby of the Mariner 4 spacecraft in 1964 showed systems on the surface that resembled terrestrial river networks, suggesting that there have been fairly recent upwellings of liquid water on the Martian surface. There is water ice in the upper Martian surface that sporadically appears on the outermost surface in liquid form. While there is no unambiguous evidence for the existence of Martian life, neither can it be ruled out categorically. Given these facts, we suggest that the most likely scenario for Martian life is this. Life developed early on Mars as it did on Earth. When the planet lost its ocean and atmosphere to space, after all, it is only 1/10 the mass of Earth. Any life on the planet vanished. Today, the only evidence of this past life would be fossils on the Martian surface. This scenario, incidentally, explains NASA's obsession with mounting a sample return mission to bring back rocks that could hold evidence of that long-vanished experiment in biology. But if explorations of nearby worlds seemed to restrict the possibilities for the existence of life, exploration of the worlds of the outer solar system quickly reversed that trend. With the launching of the Galileo spacecraft to Jupiter in 1989, it arrived there in 1995, things changed. The reigning paradigm at the time said that the existence of life depended on the presence of surface oceans as it does on Earth. We'll discuss this paradigm in more detail in the epilogue when we talk about the so-called Goldilocks planet, but for the moment, we'll just regard it as one more example of the operation of the curse of the single example, which we noted in the last chapter. We know of life developing only on our own world, where the nearby star keeps the surface temperature between the freezing and boiling points of water. Given this, we naturally expected to find no conditions friendly to life in the outer solar system on worlds so far from the sun. But things didn't turn out that way. A word of explanation. When we talk about worlds, planets come to mind first. In the outer solar system, this would mean the giant planets Jupiter, Saturn, Uranus, and Neptune. No one, however, expected to find life on a planet like Jupiter. The conditions there are just too extreme. On the other hand, it is easy to overlook the fact that each of these planets has many moons, each of which qualifies as a world with its own unique history and structure. This, incidentally, will be an important point to keep in mind later when we talk about planets circling other stars. Indeed, the Galileo spacecraft was far too fragile to survive the crushing pressure it would have encountered had it tried to enter Jupiter's atmosphere, although it did drop a probe that returned data for a while. The surprises we found were not in the planet at all, but in its moons. Although Galileo named his stars for the Medici family, the modern practice is to use mythology as a guide to naming. Thus, the moons of Jupiter were given the names of mythological characters who were, well, we guess the best term is, associated with Jupiter, whose Greek name was Zeus. According to one myth, Zeus became enamored of Europa, an aristocratic Phoenician woman, and changed himself into a white bull that mingled with her father's herds. When Europa climbed on the bull's back, he ran off and carried her to Crete, where she became a queen. Such is the legend that resulted in the name of the first of Jupiter's moons to send shock waves through the scientific community. Europa was considered the second of the Galilean moons as far as distance from Jupiter is concerned. Indeed, Jupiter, too, is one of its older names. Recent discoveries of other bodies have moved Europa to the status of Jupiter's sixth moon. It is quite small, less than 1% of the mass of Earth, and the smallest of the Galilean moons. It is also far enough from the Sun that its average surface temperature is negative 160 degrees Celsius, negative 270 degrees Fahrenheit, well below the freezing point of water. Its small size means that it doesn't contain enough radioactive material to generate significant amounts of heat, so scientists expected the Galileo spacecraft to find a frozen, dead world. It's not that there's no water on Europa. We knew that its surface consists of water ice, but at Europa's ambient temperature, this ice would be as hard as rock. Appreciable fractions of the moon's surface are crisscrossed with cracks, but it also has large, smooth areas. The discovery that caused such a stir came from gravitational and magnetic measurements made by the Galileo spacecraft. The magnetic measurements indicated that there is a subsurface material capable of conducting electrical current. The small number of craters and the large, smooth areas on the surface were also telling, because the other Jovian moons are pockmarked with results of impacts. Since there is no reason why Europa shouldn't have been hit by meteorites as often as the other moons, the only conclusion we can draw is that there must be some mechanism that allows the moon to rebuild its surface over relatively short times, astronomically speaking. All these phenomena can be understood in terms of Europa's structure. Under a covering of ice is an ocean of liquid water, an ocean whose volume exceeds that of all of Earth's oceans combined. The water is briny, most likely as a result of minerals leaching out of rocks, and is therefore a good conductor of electricity. This explains Galileo's magnetic measurements. Meteorite impacts would presumably crack the overlying ice, allowing liquid water to flow over the surface and cover the impact craters before freezing. This would account for the unexpected smoothness of the European surface. Finally, the large cracks are thought to be the result of tides in the liquid ocean, which exert enough pressure on the overlying ice to produce fractures. The question of how thick the ice layer is remains a scientific problem, one exacerbated by the possibility that the thickness of the ice may vary from place to place. In some current models, for example, the thickness varies from 10 kilometers, 6 miles, in certain places to as little as 10 to 100 meters, 10 to 100 yards, in others. We have already hinted at one problem with the idea of a subsurface ocean on Europa. Simply stated, how can you have liquid water on a body that is so cold and that has no conventional sources of heat? Discovering the solution to this conundrum opened new vistas in our thinking about possible abodes of life. The answer has to do with Jupiter's gravitational effects on Europa. The moon is close in, completing an orbit in less than 4 days. The gravitational effects of the other moons guarantee that Europa is at a different distance from its home planet at different points in its orbit, and this, in turn, means that the solid structure of the moon is constantly flexed, like a piece of metal that is bent rapidly back and forth. The solid structure of Europa is heated by this flexing. In fact, this so-called tidal heating is enough to keep Europa's subsurface ocean above the freezing point of water. A dramatic confirmation of this picture occurred in 2013 when the Hubble Space Telescope detected a huge water plume being ejected from near Europa's south pole. The plume, some 200 kilometers, about 130 miles high, was a sporadic event, something like a geyser in Yellowstone National Park, but it was certain evidence of the presence of liquid water on the moon. That same year, scientists going over old Galileo data found a region on Europa's surface where an asteroid impact had left some minerals usually associated with organic materials, which suggests that Europa, like Earth, may have had the molecular building blocks of life brought in by meteorites and comets. All of this led to a rather surprising conclusion. Instead of being a cold, frozen world, Europa was suddenly promoted to being one of the primary locations for possible life in our solar system. Although no governmental agency has promised funding for a mission to Europa as of this writing, planetary scientists are already brainstorming about sending a space probe there and drilling through the ice to sample the ocean. Presumably the first step in such a mission would be to create a good map of the ice thickness to guide the choice of location for drilling. Because of the possibility of life on Europa, the Galileo mission was terminated in 2003 by deliberately crashing the spacecraft into Jupiter to prevent any possible contamination of the moon by terrestrial microorganisms. Having said this, if life is indeed found in Europa's ocean, it will most likely be microbial. While such a discovery would release biologists from the curse of the single example, it would probably not generate a great deal of interest among the general public. One lesson we can take from the surprise discovery of a liquid ocean in our solar system's backyard, however, is that if advanced life forms do develop in a Europa-like environment, they are unlikely to develop a science of astronomy quickly, because they couldn't see the stars in the normal course of affairs. They might have little interest in communicating with beings in other solar systems, at least until they have found a way to get through the ice and look out from their world's surface. If Europa were the only moon with a subsurface ocean, we could write the phenomenon off to chance. But as early as 2005, the Cassini spacecraft in orbit around Saturn detected geysers spewing from the surface of Enceladus, one of that planet's moons. Subsequent observations have shown that these eruptions are quite common. More than 100 have been seen, and that the material coming out is liquid water mixed with salt. It is thought, in fact, that eruptions from Enceladus supplied most of the material in one of Saturn's rings. In 2014, the Cassini spacecraft actually flew through a geyser and determined that the material venting from the surface was briny water mixed with simple organic compounds. The sixth largest moon of Saturn, only about 480 kilometers, 300 miles across, Enceladus is another world that we would expect to be dead and frozen. Like Europa, however, it is a beneficiary of tidal heating, and it appears to have a liquid ocean in its southern hemisphere about the size of Lake Superior. Current estimates are that the ocean is about 10 kilometers, 6 miles, deep, and covered by 30 to 40 kilometers, 19 to 25 miles, of ice. The way that the ocean of Enceladus was detected was slightly different from the detection process for Europa. Rather than measuring magnetic anomalies, the Cassini spacecraft recorded a slight change in its velocity as it flew near the moon's southern hemisphere. The basic point is that liquid water is denser than ice. This is why the ice on a frozen lake stays at the surface instead of sinking to the bottom. This difference in density manifested itself as a difference in the gravitational force the moon exerted on the spacecraft, and this, in turn, caused Cassini's measured change in velocity. Before leaving the outer solar system, we should talk briefly about one of the other moons of Saturn. Titan is the largest moon in the solar system, bigger than the planet Mercury. It is also the only moon in the solar system that has a significant atmosphere. It is, however, very cold. Surface temperatures hover around negative 180 degrees Celsius, negative 320 Fahrenheit. And at this temperature, familiar materials take on strange properties. Water ice, for example, is as hard as rock, and methane, natural gas, is a liquid. In 2004, the Cassini spacecraft dropped a probe named Huygens after the Dutch scientist Christian Huygens, 1629 to 1695, who first sighted Titan. That gave us our first close-up look at the moon's surface. The first reaction of planetary scientists to the information being beamed back was, "Wow, this looks just like Earth." Indeed, there are long, Sahara-style dunes around the equator and lakes up near the poles. The problem is that these familiar geological formations are composed of unfamiliar materials. The lakes are liquid methane, which rains out of Titan's skies, and the dunes are made from hydrocarbons that also fall out of the skies. One researcher compared them to dunes made of coffee grounds. Although the details of Titan's geology produced the sorts of surprises that scientists expect when they enter new worlds, there were no changes in paradigm associated with the exploration of Titan. As early as the 1980s, one of the authors, J.T., reported the general expectation that when we got to Titan, we would see the beginnings of the kind of organic chemistry that eventually produced life on Earth. And that, in essence, is what we found. However, because of the extremely low temperatures on Titan, chemical reactions on its surface take place extremely slowly. You can get a sense of why this might be so by noting that when you put food into a refrigerator, your aim is to slow decay processes. Putting it into a freezer will slow these chemical processes even more. As a rough rule of thumb, the rate of chemical reaction is cut in half for every 10 degrees Celsius, 18 degrees Fahrenheit, drop in temperature. Thus, any organic chemical processes that take place on Titan would take place very slowly, so slowly that we might not recognize them as constituting life. This is a point to which we shall return later. Think for a moment about the significance of what we have learned about the existence of water in the outer solar system. Traditional thought says that the presence of water is a necessary condition for the development of life. But our new discoveries seem to tell us that water is all over the place. Consider the following. Europa has a subsurface ocean with more water than is found in the oceans of Earth. 3 of Jupiter's largest moons, Europa, Callisto, and Ganymede, have subsurface oceans. The 4th, Io, probably lost its water long ago because of its intense heat. At least one moon of Saturn, Enceladus, has a subsurface ocean. And, if our mathematical models are to be believed, so does Titan, although we have as yet no direct evidence for this claim. Thus, even before we get out of the inner solar system, we find that water, far from being scarce in the universe, seems to be quite common. This is an unexpected result, at least as far as conventional thought is concerned. Pluto was discovered in 1930 by a Kansan farm boy named Clyde Tombaugh, 1906 to 1997, who worked at the Lowell Observatory in Flagstaff, Arizona. His story is unusual. He was interested in astronomy and cobbled together a telescope from spare parts he picked up around the farm. He made some sketches of Jupiter and sent them off to the Lowell Observatory, hoping to get a useful critique. Instead, he got a job offer and, once he arrived in Flagstaff, was assigned the tedious job of looking for a planet beyond Neptune. Later in life, Tombaugh commented on his turn of events by saying, "Hell, it beat pitching A." At the time, people thought that there were some anomalies in Neptune's orbit caused by an as-yet undiscovered planet farther out, a body they called Planet X. As it turned out, the orbital measurements of Neptune were incorrect, but the belief motivated the search for another planet, which Tombaugh discovered in due course. Even though Pluto was considered to be the 9th and presumably last planet in the solar system for more than 75 years after its discovery, it always presented astronomers with problems. For one thing, it is small and rocky, and the theories we discuss later said it is in a place where gas giants should form. For another, its orbit is tilted with respect to the orbits of the other planets. In addition, Pluto actually spends part of its year closer to the Sun than Neptune does. It was last closest to the Sun in 1989. Pluto's puzzles began to be resolved when astronomers started exploring the solar system beyond its orbit. It had been thought since 1951 that a disk of rocky debris called the Kuiper Belt extended outward to a distance of about twice the orbit of Neptune. The general consensus, as we pointed out in the previous chapter, was that the belt was simply a ring of debris left over from the formation of the solar system. In 1992, astronomers at the Mauna Kea Observatory in Hawaii documented the first objects in the Kuiper Belt. But it wasn't until 2005 that the first real surprise showed up. In that year, astronomer Michael Brown and his colleagues announced the discovery of a body now named Eris, a body comparable in size to Pluto that orbits at the outer edges of the Kuiper Belt. Since then, many more of these so-called Kuiper Belt objects, KBOs, have been found, and some astronomers have suggested that Neptune's moon Triton is actually a captured KBO. Finally, in 2016, astronomers at NASA's Jet Propulsion Laboratory in California presented evidence based on the analysis of the orbits of some KBOs for the existence of a planet in the Kuiper Belt that could be 10 times as massive as Earth. With these discoveries, the true significance of Pluto began to become clear. It isn't the last of the planets, a lonely straggler at the edge of the solar system. It is instead the first of a rich trove of worlds orbiting far from the sun. A few surveys of the Kuiper Belt, think of them as pencil-thin probes through the disk, have led astronomers to believe that we will find thousands, perhaps even hundreds of thousands of KBOs out there. Most will be merely smallish rocks, but many astronomers expect a dozen or more planet-sized objects to be found as well. If this prediction proves true, then the variety we found among the moons of the gas giants will have been only a prelude to the variety we will find when we explore this next part of our home system. As we discuss later in the audiobook, when the spacecraft New Horizons made the first flyby of Pluto in 2015, it found a world of unexpected complexity. A world that, like Europa, might even be an abode for life. As you read this, New Horizons has continued past Pluto to continue our exploration of the Kuiper Belt. Before we leave our familiar solar system, we need to take a moment to summarize both the paradigm that developed to explain how our own system formed and, remember the curse of the single example, our conjecture about how other systems may have formed. Our ideas about the formation of the solar system go back to the 18th century to the French physicist and mathematician Pierre-Simon Laplace, 1749 to 1827. The author of what is called the nebular hypothesis. In this scheme, mutual gravitational attraction among materials in an interstellar dust cloud caused the cloud to contract, and during this contraction, the rotation of the cloud increased, much as an ice skater's spin increases when she pulls in her arms. Eventually, this process led to a situation in which most of the cloud's mass was concentrated into a compact sphere in the center, a sphere that would eventually become the sun, and a flattened disk of leftover material spun outward. It was, incidentally, this theory that caused Napoleon to ask Laplace why he never mentioned God in his book on his theory. Laplace's famous reply, which may be apocryphal, was, "Sire, I have no need of that hypothesis." This was basically as far as Laplace got, but today we know a lot more about the details of the formation process. We now understand that the contraction of the sun continued until the temperature at its core got high enough to initiate nuclear fusion reactions, and the energy streaming outward stabilized the newly born star. The effect of this turn of events on the protoplanetary disk was striking. Out to a place somewhere between the present orbits of Mars and Jupiter, the temperature became so high that materials such as methane and water remained in a gaseous state and were eventually blown out of the inner solar system by a massive flood of particles emitted by the sun as it geared up. Beyond this so-called frost line, or probably more correctly, ice line, these materials could solidify and be incorporated into planets. Thus, The ice line marks the boundary between the inner and outer solar system. So, the central feature of our paradigm became this. Planetary systems should have small rocky planets close to their stars with larger gas giants located farther away. It is conventional to refer to the former as terrestrial planets and to the latter as Jovian. This distinction seems to be based on such simple physics that it's not surprising that it was firmly fixed in the minds of the first astronomers looking for exoplanets. Throughout most of the 20th century, scientists assumed that the planetary formation process was a relatively simple and sedate one, with the planets taking shape pretty much in their present locations by slow accretion. New computer simulations, however, have given us a different and much more violent picture of the events that led to our current roster of planets. The inner terrestrial planets formed by the gradual aggregation of solid bits of matter, think sand grains, into larger objects called planetesimals, which could be anywhere from boulder to mountain-sized. The planetesimals, through a continual process of collision, fragmentation, and aggregation, eventually formed larger bodies called protoplanets. The computer models tell us that as many as a couple of dozen Mars-sized objects caromed around the inner solar system in a titanic game of cosmic billiards, with some being ejected from the system and others combining into larger objects. Indeed, it was the collision of one of these objects with the nascent Earth that put the material that eventually formed the Moon into orbit. In addition, computer models tell us that in these early stages of formation, a complex interplay of gravitational forces caused Jupiter and Saturn to come closer to the Sun than they are now, sending many protoplanets into the Sun and ejecting others outward to the outer solar system, forming the Kuiper Belt. Eventually, the system settled down, and the planets we see today swept up the remaining debris of the planetary disk and assumed their present appearance. Computer models also tell us that the outer solar system underwent a similarly violent process of formation. After small rocky cores had formed, as with the terrestrial planets, gravitational attraction allowed them to accumulate the hydrogen and helium that were still there, far from the Sun. Jupiter and Saturn apparently formed first, followed by Uranus and Neptune. As mentioned earlier, various complex gravitational interactions moved the outer planets around as they swept up debris, kicked material out of the asteroid belt, and eventually assumed their present orbits. So that's our home system. A lot more complicated and diverse than scientists thought it was a few decades ago, and a lot more interesting. It seems that every time we explored a new region, we were surprised at what we found. This is a pattern that repeats itself as we turn our attention outward, beyond our own solar system. The question of whether there are solar systems besides our own has preoccupied human beings for millennia, even though the tools that have enabled us to find those worlds are relatively modern inventions. For most of recorded history, this question has been debated largely on philosophical or even theological grounds, rather than in terms that we in the 21st century would recognize as scientific. And as the earlier quotes show, from the earliest times there were two competing schools of thought. One that held that other worlds like Earth might exist, and one that thought they could not. It's important to remember that what we call science today requires hypotheses that can be tested. It is, in fact, the relentless testing of ideas against nature that distinguishes science from other forms of intellectual activity. Thus, for most of history, the search for what we now call exoplanets was not really science. Nevertheless, the quest for other planets has been addressed by some of the best minds the human race has ever produced. And some of the issues raised in these debates foreshadowed matters that scientists still wrangle with today. Let's start with the Greeks. To understand what the Greeks were looking for when they approached the issue of what historian Stephen Dick calls the plurality of worlds, we have to understand how they saw the universe in which they lived. To them it was an unquestionable fact that Earth, unmoved and immovable, sat at the center of creation. Around Earth, in a series of concentric crystal spheres, revolved the sun, the moon, the planets, and in the outermost crystal sphere, the stars. Thus, when the Greeks spoke of other worlds, they were actually talking about other collections of concentric crystal spheres, each centered on its own central, immovable earth. In their language, they were talking about other complete cosmoses, cosmoi. The Greeks debate over whether such cosmoi existed. As we have already pointed out, there were two competing, deeply divided schools of thought on the question, resembled the early 20th century dispute over the existence of other galaxies more than it did a search for other planetary systems. Of the two schools, the one associated with the work of Aristotle was by far the most influential, since it dominated the thought not only of the ancients, but of medieval scholars as well. In modern language, we would say that Aristotle came to his conclusions on the basis of his physics. To an Aristotelian, the world was composed of four elements: the familiar earth, fire, air, and water. Each of these had an innate nature that drove it to seek a particular spot in the universe. Something made of earth, for example, would seek out the center of the universe, which to an Aristotelian was the same as the center of the earth, while something made of fire would seek out the periphery of the universe. Thus, left to themselves, objects made of earth would fall, and objects made of fire would rise. It's important to remember that an Aristotelian watching a rock fall would see not the action of the force of gravity, as we would, but an expression of the innate nature of the rock. The rock would be like a salmon swimming upstream, compelled by forces beyond its understanding to seek the spot where it was spawned. Given this physics, it's easy to see why Aristotle rejected the notion of other worlds. Stated simply, if there were more than one earth, how would a rock know which center to seek? How could it decide which way to fall? For Aristotle, the only way to avoid this dilemma was to assert that other earths could not exist. The competing viewpoint to Aristotle was that of the atomists, a minority opinion throughout most of history. Their view was that the universe consisted of an infinite number of atoms, a word whose Greek root, atomos, translates as that which cannot be divided, separated by voids. The atoms were in constant flux, and the familiar cosmos resulted from the coming together of a group of atoms more or less by chance. In an argument that has similarities to those heard in modern debates about extraterrestrial intelligence, see Chapter 13, the atomists argue that, in an infinite universe, such comings together of atoms must occur repeatedly, and thus there had to be a plurality of worlds. We stress again that the important thing about these ancient debates is that neither side made any statement that could actually be tested, so they were not really scientific arguments in the modern sense. Nevertheless, they set the tone for the debate as it resurfaced in medieval Europe. Greek knowledge came to Europe circuitously with works translated first into Arabic at places such as the House of Wisdom in Baghdad, and then, after the Crusades, into Latin at places such as Toledo in Spain. Aristotle's main work on cosmology, the Kylo, the heavens, was translated into Latin in about 1170 and was quickly incorporated into the curriculum at the new universities at Oxford and Paris. Thus, when Thomas Aquinas, 1224 to 1274, approached the problem of the plurality of worlds in his great quest to reconcile faith and reason, he was heavily influenced by the Aristotelian physics. To Aristotle's arguments against the existence of other worlds, Aquinas added a Christian gloss, essentially arguing from the unity of God to a unity of God's creation. This argument, however, quickly ran into theological problems. In essence, theologians argued that it limited the power of God and questioned his omnipotence. In 1277, the Bishop of Paris, Etienne Tempier, apparently acting at the behest of Pope John XXI, produced a list of 219 beliefs that were to be considered heretical. This list, known as the Condemnations of Paris, included the idea that the first cause cannot make many worlds. Item 34. The first cause is God. And the point of item 34 is that to claim that God cannot make other worlds is to limit his power and hence to commit heresy. The list seems to have grown out of a conflict between theologians and the more liberal arts faculty at the University of Paris, centering on the latter group's enthusiastic embrace of the new Aristotelian learning. In any case, it changed the plurality of worlds debate, because in order to avoid problems with church authorities, new ways to deal with Aristotelian physics had to be devised. The man who first did this was William of Ockham, 1280 to 1347, a philosopher who is best known for developing the notion of Occam's razor, which holds that the correct answer to any question is likely to be the simplest one. He countered the Aristotelian argument given earlier by stating that, while the innate nature of the four elements would not change from place to place, the way that this innate nature was expressed could. He gave the example of two fires, one in Paris and one in Oxford. The innate nature of the fires would cause their flames to seek out different points on the periphery of the universe, one above Paris, the other above Oxford. Exchange the positions of the two fires, however, and the Paris fire will seek a place above Oxford, and vice versa. In the same way, something made of earth could seek out the center of another world, not our own earth. The thing that will strike the modern reader about this long history of argument about the plurality of worlds is that no one seemed to consider the question of whether any of these plural worlds contained living beings. In fact, it wasn't until the 15th century that the German theologian and churchman Nicholas of Cusa, 1401 to 1464, raised this issue. Rather than think that so many stars and parts of the heavens are uninhabited, he argued, we will suppose in many regions there are inhabitants. This notion was part of the cosmology of Giordano Bruno, 1548 to 1600, probably the best known of the early advocates of the multiple world picture. Bruno pushed the ideas of Copernicus further than anyone else had done, arguing that other stars like our sun had their own planetary systems, possibly with life on those planets. Bruno was an unconventional thinker, and he espoused many doctrines in opposition to accepted church teaching, including denial of the Trinity, the divinity of Christ, and the concept of transubstantiation. It was these theological views, rather than his cosmology, that led to his trial of heresy. In any case, he was burned at the stake as a heretic for holding such beliefs in 1600. Once the idea of extraterrestrial life had been raised by Nicholas of Cusa, serious theological problems quickly followed. Philip Melanchthon, 1497 to 1560, a Protestant theologian and collaborator of Martin Luther, argued that the idea of multiple worlds had to be rejected because of the theological issues it created. Christian doctrine, Catholic, Protestant, and Orthodox, is based on two important events: the fall, characterized by Adam and Eve's expulsion from the Garden of Eden, and the redemption, characterized by the crucifixion and resurrection of Jesus. If there are living beings on other planets, questions, debated today in the relatively new field called exotheology, must be asked. For example, did the fall occur on every planet and for every race? If it didn't, was the redemption needed for beings who had never experienced the fall? If the fall is universal, did Jesus have to go to every world to die and be resurrected? Or were the events on earth enough to cover everyone? If so, why is Earth so central? Are there other paths to redemption on other worlds? It's not hard to see how this sort of theological questioning could go on forever. In fact, there is some historical precedent for dealing with the problems associated with extraterrestrial beings. When European explorers first encountered people in the Western Hemisphere, for example, Native Americans probably looked as strange to them as an extraterrestrial would look to us. In 1537, Pope Paul III issued an edict titled Sublimis Dei that said, in effect, that the people in the Americas had souls and should be converted to Christianity and baptized. More recently, Pope Francis brought this tradition of acceptance into modern times by stating that he would baptize a Martian if the opportunity arose. With the Enlightenment and the beginnings of modern science, the plurality of worlds debate changed yet again. Important figures such as René Descartes, 1596 to 1650, and Christian Huygens published cosmologies that explicitly showed planets circling other stars. And although their ideas, like those of the Greeks and the medieval philosophers, were not subject to observational verification, they were nonetheless based on the new physical principles that were then being discovered and sound comfortably familiar to the modern ear. And so while philosophers and scientists continued to speculate on the existence of exoplanets and extraterrestrials, there was, as we have pointed out, a lively debate on the question of life on the moon. It wasn't until the mid-20th century that technology advanced to the point that the whole issue could be taken outside the realm of philosophy and made part of observational astronomy. Let's take a moment to discuss why finding exoplanets is so difficult. It wasn't until 1838 that the German astronomer Friedrich Bessel, 1784 to 1848, was able to measure the distance to another star. For the record, it was the star 6I Cygni, 10.9 light-years away. For the first time, scientists had a sense of the vastness of the Milky Way, the incredible distances that separate stellar systems. For reference, if we shrink the distance between Earth and the Moon down to a foot, the nearest star, Alpha Centauri, would be somewhere in the middle of Russia. Thus, we are looking for relatively small objects very far away, always a difficult task. Furthermore, while stars generate their own light, planets shine only by reflection, a fact that means that they are not only far away, but very dim. One author compared the problem of finding them to the difficulty of detecting a birthday candle at the edge of a searchlight in Boston using a telescope located in Washington, D.C. Yet, in a situation like this, the dimness of the planet is not the main problem. The Hubble telescope has detected far fainter objects in the sky. The problem is that the planet is close to its star, which is an extremely bright light source. Separating out the light reflected from a planet from the glare of its star is especially difficult. Faced with these twin obstacles, 20th century scientists began to search for exoplanets not by trying to observe the planets themselves, but by trying to observe the effects the planets have on their parent stars. To understand the techniques that were developed, it will help to imagine that you are an astronomer on a planet circling a distant star and that you are trying to detect the presence of planets in our own solar system. We usually describe our solar system in a loose way by saying that the planets circle the Sun. This isn't a precise description, however. In fact, the Sun and a planet such as Jupiter circle a point between the two called the center of mass. We use Jupiter as an example because it is the largest planet and has the largest effect on the Sun. You can think of the center of mass as the point where you could balance the two masses if they were connected by some impossible rod. Thus, while Jupiter completes its 10-year orbit around the center of mass, the Sun describes a much smaller circle in the same time frame. Since the center of mass of the Sun-Jupiter system is actually inside the Sun, the motion of the Sun is more like that of an out-of-balance washing machine than that of a planet. But that motion betrays the presence of the planet. The first scientists trying to locate exoplanets looked for this motion directly. The basic strategy was to find a nearby star that moves through the sky quickly, and then to look for wobbles in the star's path caused by a planet. In the late 1930s, astronomer Peter van de Kamp, 1901 to 1995 of Swarthmore College, began observing a small object about 5 light-years from Earth known as Barnard's star. Analyzing thousands of photographs taken over the next 40 years, he claimed to have detected the telltale wobble caused by a planet. Unfortunately, other astronomers have not been able to confirm his results, and it is now thought that the technical difficulties handicap faced in making these precise measurements were too large to be overcome with the technology available to him. Consequently, the consensus today is that he did not detect an exoplanet. A second, more promising way to detect stellar wobble is to use the Doppler effect. This effect occurs when a wave such as light or sound is emitted by a moving source. If the source is moving toward an observer, he or she perceives the wavelength to be shorter by the amount the source moves between the emission of crests. In the case of sound, this means a higher pitch. In the case of light, this means a shift toward the blue end of the spectrum. Similarly, if the source is moving away from the observer, he or she perceives a longer wavelength, a lower pitch for sound, and a shift toward the red for light. It is the Doppler effect that causes the familiar change in pitch in the sound of an automobile's horn when it passes you on the street. Consider a star with one planet in orbit, and for the sake of argument, suppose that the plane of the planet's orbit lies in the line of sight toward Earth. Then, as the star and its planet move around their center of mass, the star moves toward us for half of the revolution and away from us for the other half. This in turn means that the light we see is red-shifted for a while and then blue-shifted. In fact, we see a smooth oscillation of the wavelength between these two extremes. Because this technique measures the motion of a star toward and away from us, astronomers refer to it as a radial velocity measurement. The first discovery of exoplanets by this means was made by Alexander Voloshin and his colleagues at Penn State University in 1992. The problem, as we pointed out in Chapter 1, is that the two exoplanets they found are in a place where no one expected them to be. They are, in fact, orbiting a kind of star known as a pulsar. A word of explanation about pulsars. When a large star burns through its nuclear fuel, it ends its life in a gigantic explosion called a supernova. The entire outer covering of the star is hurled into space while its core collapses into an incredibly dense, rapidly rotating object known as a neutron star. Typically around 16 kilometers, 10 miles across, the star emits a continuous beam of intense radio waves. These beams are like the beacon from a lighthouse, and if they happen to sweep across an observer, he or she sees a steady succession of radio pulses, hence the name pulsar. The point is that the region of space around a pulsar is the last place you would expect to find exoplanets. Even if the star had a planetary system before it went supernova, it's hard to imagine how those planets could have survived the explosion. But in a paper published in the prestigious journal Nature in 1992, Voloshin and his colleagues presented unassailable evidence that the telltale oscillation in frequency due to the Doppler effect is present in radio waves from pulsar PSR 1257 plus 12. PSR stands for pulsating radio source, and the numbers indicate the position of the object in the sky. Not only that, but a detailed examination of the data showed not one, but two planets in the system. No doubt about it, PSR 1257 plus 12 has planets. Thus, Voloshin, who fittingly had received his education at the Nicholas Copernicus University at Torun in his native Poland, became the first astronomer to detect an exoplanet. Furthermore, the exoplanets are in a place that no exoplanet, in theory, has a right to be. So, the pulsar exoplanets around PSR 1257 plus 12 became the first in a long string of surprises that the galaxy had in store for us. For the record, we still don't really know why they are where they are. Either they survived the supernova explosion, God knows how, or they formed out of the debris after it was over. Either way, they are strange beasts. The first normal exoplanet was discovered in 1995. A team of Swiss astronomers working at an observatory in France, followed quickly by a team at the Lick Observatory in California, announced that there is a planet around the star 51 Pegasi. The name means that it is the 51st brightest star in the constellation Pegasus, a flying horse, about 42 light-years from Earth. And again, the planet turned out to be a surprise. This time, though, the surprise was of a different kind from that involved with pulsar planets. This new planet isn't a normal stellar system, but it is big, perhaps half the size of Jupiter, and it is located close to its star, closer in fact than Mercury is to our own sun. The problem is that there's no room for this kind of planet in the neat scenario we presented for our own solar system in the last chapter. Planets close to the star are supposed to be small and rocky, with large planets forming farther out. As the millennium turned, more and more of these so-called hot Jupiters turned up, and astronomers began to wonder whether any newly discovered exoplanets would be in systems like our own. Like the butterfly collector we talked about in Chapter 1, we seemed to be finding cabbage butterflies where our old paradigm told us we should find monarchs. What to do? As it turned out, a solution to this puzzle was not long in coming. With the launching of the Kepler spacecraft in 2009, it became clear that pulsar planets and hot Jupiters were just the beginning of our voyage into a strange new universe and the formation of a new paradigm. Sometimes trying to create a hard and fast definition of something is more trouble than it's worth. Mere words are often a poor way to describe the complex set of cognitive processes that go into recognizing an object, no matter how common and ordinary that object might be. This is why Justice Stewart's comment on pornography is used so widely in the intellectual community. In this chapter, we argue that it applies equally well to the definition of a planet. Having made this point, we acknowledge that defining a planet has been made significantly more difficult by the discovery of the diversity and complexity of exoplanets. The existence of hot Jupiters was the first example, and there will be many more. Until recently, most of the debate on the nature of planets has been confined to the planets of our solar system, and hence, in the end, suffers from the curse of the single example. To the ancient Greeks, who first introduced the word planet, there was no ambiguity in its definition. In their world, there were the fixed stars whose relationship to one another never changed, and there were other lights in the sky that moved from place to place in a regular and predictable way. The latter were the planets, from the Greek astros, planetai, or wandering stars. Transitory phenomena such as comets were thought to be conflagrations in the upper atmosphere, and therefore weren't part of Greek cosmology. It's important to realize that to the Greeks, Earth was not a planet. Instead, it was the unmoved and unmoving center of creation around which everything else moved. Technically speaking, however, the sun and the moon would have been classified as planets in the Greek cosmology since, like everything else, they moved around Earth. After the Copernican revolution, the sun moved to the center of the solar system in accepted cosmologies, and the moon became a satellite of Earth. In this scheme, there were 6 planets: the familiar Mercury, Venus, Earth, Mars, Jupiter, and Saturn. There was no debate about what was and what wasn't a planet, simply because all of these objects had been known from time immemorial. William Herschel, 1738 to 1822, discovered Uranus in 1781, but this event, along with the subsequent discovery of Neptune in 1846, didn't really trigger any debate, since they seemed to engage in the same sort of behavior as the known planets. They were just farther away. Actually, the naming of the planet Uranus tells us something interesting about how the astronomical community used to work. At the time of the discovery, Herschel was a professional musician and an amateur astronomer living in the town of Bath, England. A second oboe in the band of the Hanoverian Guards in his native Germany, he had emigrated to England when he found military life unappealing. A skilled telescope maker, he discovered the planet while making a systematic survey of the sky from his backyard. Following the example of Galileo and the moons of Jupiter, Herschel suggested the name Georgium Sidus, George's star, after the King of England for his new discovery. The gambit seemed to work as well for him as it had for Galileo, since Herschel received a royal pension from George III. His suggestion, however, was largely ignored by his fellow astronomers, particularly those outside England. By the end of the 18th century, common usage had made the mythological name Uranus, the Greek god of the sky and grandfather of Zeus, pretty much universally accepted. A similar, though more muted phenomenon followed the discovery of Neptune in 1846 when Alban Leverrier, 1811 to 1877, one of the astronomers who had predicted the planet's existence, pushed to have the planet named Leverrier's star. Unsurprisingly, outside France this name never caught on either. But in spite of these mild conflicts over naming, there was no question about whether what had been discovered was actually a planet. Unfortunately, this friendly state of affairs depended on the relatively primitive nature of the technology available to astronomers at the time. By 1801, however, telescopes had gotten good enough to detect Ceres, the largest body in what would later be identified as the asteroid belt. Eventually, many more such objects were detected. What to do? Does every rock circling the sun count as a planet? If not, where do you draw the line? In the early 19th century, newly discovered asteroids were simply counted as new planets. Indeed, even as late as 1867, one author claimed that there were no fewer than 90 planets in orbit around the sun. Over the last half of the 19th century, however, something interesting happened. There were no international bodies to take on the role of terminology police, but descriptions of the solar system began to change and evolve toward our current understanding. The asteroid belt was recognized as a system of bodies ranging from boulders up to Ceres, which is about 970 kilometers, 600 miles, across. Without getting into a debate about what a planet is, astronomers apparently realized that most asteroids didn't belong in the category. Like Justice Stewart, they knew it when they saw it, and asteroids definitely weren't it. The classification of Pluto. To understand the current controversy about whether Pluto is a planet, we have to talk a bit about how the scientific community is organized today. At the national level, there are professional organizations representing different scientific disciplines. The authors, for example, are an astronomer, MS, and a physicist, JT, and as such, are members in good standing of the American Astronomical Society and the American Physical Society, respectively. Other professionals may belong to the American Chemical Society, the American Medical Association, and so on. One important organization that spans all the sciences is the American Association for the Advancement of Science, AAAS, headquartered in Washington, D.C. These organizations fulfill many important functions. They publish scholarly journals to report on new research, organize professional conferences, and generally represent the interests of their constituencies to the public and to the government. In addition to these national scientific organizations, international ones began to be formed in the 19th century, often by mutual agreement among national groups. In 1875, for example, the International Bureau of Weights and Measures was set up by treaty. Headquartered near Paris, it defines and oversees the maintenance of important standards such as the second and the kilogram. It works in conjunction with national organizations such as the National Institute of Science and Technology in the United States to make sure that scientists and engineers worldwide have reliable standards for their measurements. Similarly, the International Union of Pure and Applied Chemistry, IUPAC, founded in 1919, has among its duties the task of standardizing chemical nomenclature. One example. When element 112 was produced, the discoverers wanted to name it after Nicholas Copernicus. It is customary to name new elements after famous scientists, Einsteinium, Curium, and so on. Their proposed symbol, Cp, turned out to be already assigned to a group of chemical compounds, however, so the IUPAC changed the symbol to Cn. When the International Astronomical Union, IAU, was founded in 1922, then it joined a large and growing body of international scientific organizations. Its first task was typical of the sorts of things these organizations do. Astronomers usually identify stars by the constellation in which they are found. The star 51 Pegasi, as we explained in the last chapter, is the 51st brightest star in the constellation Pegasus. As telescopes got better and fainter stars entered the astronomer's purview, it became increasingly important to know where one constellation began and another ended. Other than vague artists' drawings, however, these boundaries were not well defined. The first job IAU astronomers had to tackle, therefore, was to survey the skies and to find clear, permanent boundaries among constellations, a job they did very well. Maintaining these kinds of international standards is a difficult and often thankless task, and we have nothing but respect for the men and women who carry it out. Theirs is important work, absolutely necessary for the maintenance of the scientific enterprise. None of it is likely, however, to make tomorrow's headlines or to serve as grist for late-night comedians. Every once in a while, though, one of these organizations makes a decision that is so colossally, mind-blowingly silly that you can only stand in awe when you see it. Examples: the decision by the International Commission on Zoological Nomenclature to rename Brontosaurus in 1999, and, yes, the 2006 decision by the IAU to demote Pluto. So, let's get down to the basic question. Is Pluto a planet or not? The answer to this question depends on how you define the word planet. If you consult the Oxford English Dictionary, you find the word defined in its astronomical sense as follows: any of the various rocky or gaseous bodies that revolve in elliptical orbits around the Sun and are visible by reflected light, especially each of the 9 major planets. A definition like this wouldn't have been much help to the astronomers trying to deal with the asteroid belt in the 19th century, and it won't help us much in talking about Pluto. We need a lot more technical detail. Consequently, the IAU's board, in anticipation of dealing with this problem at its August 2006 meeting in Prague, created a committee to come up with a workable definition of the word planet. The committee was headed by Harvard University historian of science Owen Gingerich. Gingerich is well known in the scientific community. He is one of the most respected astronomical scholars, the authors would say the most respected astronomical scholar, in the world. If anyone could deal with the complexities associated with Pluto, the IAU elders most likely argued Gingerich was the man to do it. At meetings that Gingerich described as involving vigorous discussions of both scientific and cultural/historical issues, the committee formulated the following definition. A planet is a celestial body that A. has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, i.e. round, shape, and B. is in orbit around a star and is neither a star nor the satellite of another planet. Sensible. It's a planet if it's not just a rock and not big enough to be a star. Or it could be simpler. This definition certainly satisfies the "I know it when I see it" criterion. Let's look at these requirements in a little more detail. If you look at a rock, you'll see that, in general, it has an angular shape. This is because the electrical forces among atoms in the rock are strong enough to overcome any other forces that might be acting on it. So the rock retains its angularity. Start making the rock bigger and bigger, however, and eventually a new force begins to enter the picture: the force of gravity. When your rock becomes hundreds of miles across, the gravitational force exerted by all that mass becomes big enough to overcome the electrical forces between atoms, and the material in the rock starts to respond to gravity. The atoms start to rearrange themselves in response to the force of gravity, assuming the round shape required by the Gingerich Committee's first criterion. Thus, the asteroid series, about 970 kilometers or 600 miles across, meets this criterion, but the random rock in the asteroid belt does not. In the world of exoplanets, though, this criterion may need to be expanded a bit. For example, if a planet is rotating, a third force comes into play in addition to the electrical and gravitational forces discussed earlier: centrifugal force. This force takes the round shape and smears it out at the equator so that the body appears to be slightly squished. the technical term is oblate. Even a relatively sedate planet such as Earth exhibits this effect since the diameter from pole to pole is about 40 kilometers, 25 miles, shorter than the equatorial diameter. Since this amounts to a deviation of only about 0.3% from its sphericity, it's almost always reasonable to treat Earth as a sphere. For Saturn, however, this deviation grows to almost 10% of the planetary diameter, an effect not so easily neglected. There are sure to be rapidly rotating exoplanets out there, so in the future what we mean by hydrostatic equilibrium may have to take account of centrifugal force. In 2014, in fact, one of the authors, MS, and two of his students, Prabal Saxena and Peter Pankow, worked out the details of what the transit of a football-shaped planet would look like. In addition, we can imagine other as yet unanticipated forces that might have to be taken into account someday. Magnetism comes to mind, for example. Thus, as is always the case with exoplanets, we have to keep an open mind about what else we might discover and how it might affect our definition of a planet. How about the other criterion, the one about not being a star? As the mass of an object gets bigger and bigger, the temperature at its center increases until at some critical mass, the particles at the core are moving fast enough to initiate fusion reactions. When this happens, the object becomes a star. Thus, the criteria given earlier define a kind of middle ground between a rock in orbit and a double star system. The downside of this definition was that it would classify yet to be discovered Kuiper belt objects, KBOs, as planets. When the definition was proposed, it would have included 12 objects, including Ceres, and opened the door to many more possibilities. This potential expansion made some astronomers uncomfortable, for reasons the authors find hard to understand. During the 19th century, after all, chemists kept finding new chemical elements, but no one objected to identifying them all as elements. There was no move, for example, to demote some to dwarf elements. If nature has produced over 100 chemical elements, the community said, so be it. The number actually stands at 118 and counting today. So what's the problem with a couple of dozen planets in the solar system? To understand what happened in Prague, though, you need to understand something else about scientific meetings. The conference in Prague was scheduled to last 10 days. This is a rather long time for a scientific meeting. Even the annual meetings of the AAAS, arguably the most comprehensive scientific gathering in the world, last only for what is essentially a long weekend. Throw in travel time, and the 2006 Prague meeting of the IAU required an attendance of almost 2 weeks, an unusually large time commitment even for academic astronomers in the summer. Consequently, although many astronomers attended the conference, many came for only a few days, when their particular research interests were in play, and left before the conference was over. On the last day, in fact, only about 400 people were still in attendance, a fact that is important in understanding the resolution of the Pluto debate. The problems actually had started when the General Assembly opened. They began with objections from the floor that the definition of a planet produced by the committee hadn't been announced in advance. A reasonable complaint, even though the organizers had acted in this way in an attempt to avoid a media circus. Things went downhill swiftly from there, however, with, according to an observer, one participant literally screaming because a representative from his own narrow specialty hadn't been included on the committee. One person present at the meeting described the proceedings in an email as astronomers behaving badly. In any case, by the last day of the meeting, a new definition had been cobbled together and was presented for a vote. In essence, it added a third criterion to those listed earlier. This was that a planet must have cleared the neighborhood around its orbit. This is a strange requirement since the definition of cleared was never given. For example, in 2012, the good citizens of Chelyabinsk in Russia learned that Earth is still in the process of clearing its neighborhood when a house-sized meteorite landed near their city. Does this mean that Earth isn't a planet? Surely not. But the event illustrates the danger of trying to deal with a difficult definitional problem in haste. In this case, the question of how cleared an orbit has to be to satisfy the new criterion was not addressed, leaving the definition essentially useless. In any case, according to the IAU, there are now two new subcategories of planets. Dwarf planets, a category that includes Ceres, Pluto, and any new KBOs that may turn up, and Plutoids, a category that includes any dwarf planets outside the orbit of Neptune. Remember that Ceres is in the asteroid belt. The reaction to the IAU action was immediate and intense. In the astronomical community, there was a widespread negative response. Over 300 astronomers signed a petition opposing the new definition, a number that may well exceed the number of affirmative votes actually cast in Prague. There was a persistent claim that the vote was actually an expression of anti-American attitudes by European intellectuals. Pluto, after all, was discovered by an American. By contrast, Neil deGrasse Tyson, one of the world's leading explainers of science and a champion of Pluto's reclassification, blames the negative American reaction on the existence of the Disney character named Pluto, although the authors see this explanation as being rather far-fetched. Several factors, in truth, contributed to this negative reaction. For one thing, the word planet has many linguistic and cultural connotations outside astronomy. The Oxford English Dictionary, for example, lists no fewer than half a dozen definitions of the word. The idea that a group of narrow specialists would assume that they had the right to define a word with such a wide meaning smacks of a kind of arrogance. In any case, the upshot of the IAU vote is that many astronomers, possibly a majority, question the wisdom of the IAU definition. We close this rather discouraging discussion of Pluto with one final point to consider. If Earth were moved to the orbit of Pluto, it wouldn't, according to the IAU, be a planet either. Defining planet in the world of exoplanets. The IAU had the enormous bad luck to get involved in defining the word planet, just as the Kepler spacecraft, which we'll describe in the next chapter, was about to reveal the true complexity and diversity of planetary bodies in our galaxy. This newly understood complexity actually suggests a simple solution to the Pluto problem that would not generate much opposition. We already divide the inner planets of our solar system into two categories: terrestrial, small and rocky, and Jovian, gas giants. Why not just add a third category? Call it Plutonic, for Pluto and the KBOs. Given that the diversity of exoplanets will force us to define many new planetary categories anyway, why not just start the process close to home? In any case, we don't feel that the IAU definition is a useful way to approach exoplanets. Thus, in what follows, we adopt an extension of the more sensible definition proposed by the Gingrich Committee, call it the expanded Gingrich criteria, that includes the possibility of forces besides gravity being involved. Taking into account all forces acting on a body, if that body is bigger than a rock and smaller than a star and is not a moon, then as far as we're concerned, it's a planet. The launching of the Kepler satellite in 2009 changed our view of exoplanets forever. Most of the incredible diversity we've talked about and explore more fully later has been discovered by this single spacecraft. Indeed, while the Kepler was operating at full power, new planetary candidates were being announced at a rate equivalent to several a day, although the Kepler team actually announced the candidates in large batches. The Kepler spacecraft detects planets by a method that is easy to describe, if not necessarily easy to carry out in practice. It's called the transit method, and it works because of a simple fact. When a planet passes between an observer and a star, the observer sees the light from the star dim slightly, then return to normal as the planet moves on. A repeated pattern of such dimmings is a fingerprint suggesting the presence of the planet. As simple as this technique sounds, however, it encounters problems when actually implemented. To understand some of these difficulties, imagine again that you are an astronomer on a distant planet observing our own solar system. The orbits of the planets in our system lie in a plane known as the ecliptic. If you, the distant observer, are also in that plane, then your instruments will see the characteristic dimming and brightening as the planets pass in front of the sun. In this case, the planets will move across the sun's equator, producing the longest possible transit. But what if you are not in the plane of the ecliptic? To see what happens in this case, imagine tilting the ecliptic plane slightly upward. In this case, you will still see transits, but the planets will appear to pass higher up on the sun, and the transits will be shorter. Keep tilting the ecliptic, and you will reach a point where the planets no longer appear across the face of the star, and the transits will disappear altogether. A similar situation will follow if you tilt the ecliptic downward. What this means is that the transit method depends critically on the orientation of the ecliptic plane in any system we observe, and this, in turn, means that there is a limited range of angles for that plane that will allow planetary detection around a distant star. Planets in systems whose ecliptics are outside that range will simply be undetectable. You can see this most easily by imagining that you, our hypothetical astronomer, are observing our solar system from a spot 90 degrees above the ecliptic, i.e., you are looking down on the system. In this case, your instruments will record no transits, despite the presence of many planets. But suppose we astronomers here on Earth are lucky and do see a transitory dimming in a distant star. Does this mean we have found a planet? Not necessarily. There are many processes that can cause slight dips in a star's output. For one thing, stars naturally exhibit small up and down swings in their output, which is one of the biggest sources of ambiguity for astronomers using the transit method. For reference, even a staid star such as the Sun exhibits a natural variability of about 10 parts per million, ppm, which amounts to an uncertainty in the fifth decimal place in measurements of its light output. In addition, we know that the Sun goes through a regular 11-year sunspot cycle. At the peak of the cycle, there can be many sunspots or sunspot groups on the solar surface. And although sunspots are actually bright regions, they appear dark only because they are cooler than the surrounding material. They do produce a slight dimming because they replace areas of greater brightness on the solar surface. If you, as our hypothetical distant astronomer, had only a single dimming to analyze, you could easily mistake a sunspot event for a planet. In a similar way, a double star system could produce something that looked like a transit. Again, imagine observing such a system in which two stars revolve around each other from the plane of that revolution. When the two stars are widely separated, you will see a brightness representing the full output of both stars. When one star passes in back of the other, however, the total brightness of the system drops, producing an illumination curve that mimics a planetary transit. This is particularly true if one star is only partially shadowed by the other. Finally, as precise an instrument as the Kepler is, there is a limit to its resolution. What this means is that all the light coming from a small area of the sky is treated as if it comes from a single source. You can imagine that such a situation is capable of producing confusing results. For example, suppose that there was an eclipsing binary star system whose line of sight to an observer almost, but not quite, passed near another star that was being observed. And suppose further that the difference in the lines of sight from the binary and the star being observed was so small that the telescope treated all the light as if it came from a single source. In this case, the dimming in the distant binary would mimic a planetary transit in the foreground star. As this short list shows, there are many ways, more than we have room to explain in fact, to produce signals that could be mistaken for planetary transits. For this reason, the simple observation of a transit does not establish the existence of a planet. Instead, an object exhibiting that characteristic light curve is designated as a Kepler object of interest, KOI, and subjected to exhaustive further testing, which we will describe. The Kepler spacecraft had a mass of about 1,000 kilograms, 2,205 pounds, on launch, about the same as a smallish car, with an instrumental payload of 478 kilograms, 1,054 pounds. It is not in orbit around Earth, but instead trails after its home planet as it orbits the Sun. For reference, the spacecraft orbits the Sun in 372 days, which means that it is continually falling farther behind Earth. There are several reasons for this seemingly strange choice of orbit. For one thing, if the Kepler were in orbit around Earth, the planet would block out part of the sky. For another, mass concentrations in Earth produce slight changes in the gravitational field, perturbations that would make aiming the satellite more difficult. The central feature of the Kepler search strategy is that it continuously monitors the light from about 145,000 stars. Thus, when a dimming occurs, it is recorded by instruments on the satellite and reported back to Earth. As strange as it may seem at first, the Kepler is not pointed toward the heart of the Milky Way, the part of the sky that has the greatest density of stars. The reason, alluded to earlier, has to do with the resolution of the telescope. The density of stars in the plane of the Milky Way is so high that it would simply be impossible to isolate a single star against all the background stars. Instead, the telescope is pointed upward and out of the galactic plane. For experts, we note that it is pointed toward the constellation Cygnus. It is also pointed upward out of the ecliptic plane, thereby avoiding contamination of its signal by asteroids, KBOs, and sunlight. The small volume of space examined by the Kepler means that all the statements we will make later about the existence of planets in the galaxy are extrapolations from a small, but probably representative, sample. The main working parts of the spacecraft are a large mirror, 1.4 meters or 4.6 feet across, and an extremely sensitive camera. The Kepler camera records incoming light in pretty much the same way that your camera does, by reading the output of charge-coupled devices, silicon chips, that turn incoming light into a small electric current. The sensitivity of the camera determines the success or failure of a mission such as Kepler. Kepler scientists report a sensitivity of about 30 parts per million, essentially an accuracy at the level of 5 decimal places. For reference, the natural variability of the Sun is about 10 parts per million, and the change in light output due to the transit of an Earth-sized planet across a Sun-like star is about 80 parts per million. The satellite was launched in March 2009 after several delays due to budget problems at NASA. 3 months later, it was returning scientific data. The actual results of these measurements are discussed in the following chapters, but to get a sense of where things stand now, we need to understand an important aspect of spacecraft operation. It is crucial that scientists be able to point an instrument at a specific spot in the sky and keep it pointed there while measurements are being made. This, in turn, means that there has to be a way to orient the spacecraft in the emptiness of space. This task is generally accomplished through the use of reaction wheels, which are essentially gyroscopes whose axes of rotation stay fixed once they start spinning. Thus, a reaction wheel defines a direction in space that the spacecraft can use as a reference to maintain its orientation. The Kepler satellite originally had 4 reaction wheels to provide redundancy once the spacecraft was in orbit. In July 2012, one wheel failed. The spacecraft can operate on 3 wheels, but this failure took away the redundancy in the original design. Then, in May 2013, another wheel failed, and the spacecraft lost its ability to orient itself. Its engineers shut it down as they tried to find a way to proceed with the mission using 2 reaction wheels. In what can be described only as an engineering miracle, they found a way to return the satellite to active, if restricted, duty. The new technique depends on the fact that the Sun emits a constant stream of particles known as the solar wind. This wind exerts a slight pressure on any object in its path. In an operation that one engineer described as analogous to keeping a rowboat pointed upstream in a river, NASA engineers were able to use this pressure to stabilize the orientation of the satellite with respect to the solar wind. The remaining two reaction wheels can correct the inevitable drift from this position, so the satellite can have stable operation, but only in this restricted orientation. The new program was labeled K2, Second Light, and in 2015 Kepler scientists announced the discovery of two Earth-like planets by the reborn satellite. Before we move on to discuss these two new exoplanets, we'll point out again that the detection of a dip in the luminosity of a star just gets us to the label Kepler Object of Interest. Verifying that the dip is actually a planet requires a long process of validation. The first step is to raise the stellar system from a mere object of interest to a candidate. Doing that requires a complex series of operations involving the telescope's electronics and photometer. Operations that we won't describe in detail, but whose end result must convince scientists that the dip is real and not just a glitch in the system. More importantly, though, astronomers at this stage spend a lot of time ruling out the kind of contamination by eclipsing binaries discussed earlier. Only when these operations are successfully completed can the system under observation move from object of interest status to candidate status. At this point, the system is typically referred to ground or space-based telescopes for further study. We have already touched on some of the reasons that the Kepler, once it has identified a candidate, turns the validation process over to other instruments. The system is set up to avoid false positives, the mistaking of a signal generated by other processes, some of which we've discussed, for a signal generated by a planetary transit. In addition, planets far from their star make transits over long periods of time, and these times may well be longer than the operational lifetime of the Kepler. Jupiter, for example, makes a transit every 10 years, so an instrument like the Kepler observing our solar system would see only one transit, at best, during its lifetime. Confirming that the signal actually is produced by a planet can take a long time, and there are usually about 3 times as many candidates as confirmed planets in the Kepler output. For reference, the number of confirmed planets passed 1,000 in 2014 and passed 4,000 in 2016. The confirmation process is carried out by space-based observatories such as the Hubble Space Telescope, or more often by ground-based telescopes. Once the Kepler has identified a star that might have planets, the confirmation process doesn't necessarily require a high-level instrument to carry out the validation process. For example, a 32-inch teaching telescope at the author's home institution, George Mason University, in the suburbs of Washington, D.C., has been used to validate no fewer than 8 Kepler candidates, simply by observing regular transits. Once you know which star to look at, it doesn't take a lot of technological firepower to make these kinds of observations. Depending on the details of the system being analyzed, astronomers can use a number of different techniques in the validation process besides observing repeated transits. These include radial velocity measurements. As we saw in Chapter 3, the gravitational pull of a planet can impart a small back-and-forth velocity to its star, and this change produces a Doppler shift in the star's light. This shift can be measured. Transit timing variations. In systems with multiple planets, a planet's orbit is affected by the gravitational pull of the other planets. This produces small but predictable variations in the observed transits. Reflected light variations. Like Venus in our own system, exoplanets exhibit phases as they circle their star. This causes small continuous variations in the light output of the system that may be big enough to be detected. Stellar deformation. Sometimes the Kepler can detect changes in the shape of a star as its partner completes its orbit. This technique is most often used to rule out systems in which the companion is a small star known as a brown dwarf. Finally, we note that in 2016 a new method of confirming Kepler results was introduced. A group headed by scientists at Princeton University introduced a method of analyzing Kepler results based on a technique involving computerized processing of incoming data. In their initial paper, They reported 1,284 new exoplanets and rejected 428 candidates as false positives. We expect this kind of technique to become important in the future when massive amounts of new data from new satellites will need to be processed. Before we go on to explore the new worlds that Kepler has found, we would like to make a short digression to describe the incredibly complex story of how the satellite actually came into existence. Merely having a good idea isn't enough to convince a massive bureaucracy such as NASA to invest major resources in a new project, no matter how compelling. Nothing illustrates this fact better than the tale of how the idea of measuring planetary transits turned into an actual machine in space. As early as 1971, astronomers had proposed the transit method for planet hunting, and by 1984, NASA scientists William Barucki and David Summers, no relation to MS, had established that, in order to find Earth-like planets around other stars, we would need to observe those stars from space. As often happens in this sort of situation, NASA provided some modest funding to support the development of the instruments and technology needed for a transit mission. At this point, the main emphasis was on searching for Earth-type planets, what we called Goldilocks planets in Chapter 1. The central technical problem at this stage was the development of extremely sensitive and stable light detectors, or photometers. The reason for this emphasis is easy to understand. The photometers have to be sensitive because, as we pointed out earlier, the amount of dimming produced by a planetary transit is very slight. If the instrument reading fluctuates by more than this small amount, a phenomenon usually referred to as noise, then the transit signal will simply be lost. Similarly, if the reading of the instrument drifts over time, we won't be able to compare different readings taken of the same star. In 1992, NASA instituted the Discovery program. Its goal was to send out a fleet of small spacecraft rather than a few large and expensive ones. NASA Administrator Daniel Golden referred to these missions as faster, better, cheaper. The missions were supposed to cost less than $425 million and be completed in 3 to 6 months. The first proposal for a transit mission was submitted under the awkward title FreeSIP, Frequency of Earth-Sized Inner Planets. The NASA Review Board rejected the proposal mainly because it felt that the photometers available at the time were not up to the task of finding Earth-sized planets. Back to the drawing board. In 1994, following work on the photometers, the group again submitted to NASA a proposal for a transit mission and was again rejected, this time because it was too expensive. In 1996, a modified proposal was submitted, incorporating reduced costs by changing the position of the satellite to its present orbit. This generated another rejection, this time because the team had not demonstrated that it could successfully monitor thousands of stars simultaneously. It was at this time that the mission name was changed to Kepler. Throughout the mid to late 1990s, a sample photometer was built and tested at Lick Observatory in California. Another proposal to NASA in 1998, and another rejection. This time because there were still doubts that the photometer was sensitive enough to detect Earth-type planets. In 1999, a system was designed and tested incorporating the sorts of noise that would be encountered in an actual mission. In 2000, Kepler was again proposed, and this time it made it onto a short list of missions to be developed. Finally, in 2001, it was accepted as a Discovery-class mission, and the actual building of the spacecraft began. 5th time lucky. The point of this excruciating story is not that Kepler had a particularly hard time getting NASA funding. Any mission this complex and expensive has to go through a similar process. What it shows is that you don't just have to be smart in this business. You have to be persistent. First, there are those pulsar planets. We still don't really understand where they came from, although current speculation suggests they formed from debris after their star exploded. Their discovery was followed by a bunch of hot Jupiters, planets bigger than Jupiter and orbits closer to their stars than Mercury is to our Sun. We also pointed out that the only detection method available at the time was the radial velocity measurement, which would pick up hot Jupiters before it picked up anything else. Thus, at the turn of the century, there was a strange sense of foreboding in the scientific community. Was our home system really such an oddball in the galaxy? Was there anything out there besides hot Jupiters and other planets that, although real, were nothing like Earth? The launching of Kepler quieted those fears. The transit method isn't biased toward big planets, but it is capable of picking up dips in luminosity due to planets whose sizes range from smaller than Earth to bigger than Jupiter. It quickly became obvious that the hot Jupiters are actually a small fraction of the kinds of planets out there, and that the hot Jupiter problem wasn't really a problem at all, but merely an artifact of the radial velocity detection method. The detection of a transit allows us to determine a good deal about the exoplanet from some simple physics. The time between transits is the exoplanet's year, and from this we can determine the radius of its orbit if we use standard astronomical techniques to estimate the mass of the star. The amount of dimming tells us how much light the exoplanet is blocking, which allows us to determine its radius and hence its volume. Measuring the radial velocity of the star as it and the planet revolve around the system's center of mass allows us to calculate the exoplanet's mass and therefore its density, which is just the mass divided by the volume. And this, in turn, tells us if we are dealing with a terrestrial-type planet, small, rocky, and dense, or a gas giant, large and gaseous. We can often learn a great deal more about a newly discovered exoplanet through the use of spectroscopy. This technique depends on the fact that atoms of a specific chemical element emit and absorb a characteristic pattern of light known as a spectrum. It is sometimes possible to image the exoplanet directly by blocking out the light from its star. In this case, we can determine the composition of the exoplanet's atmosphere by directly observing the spectrum. The more light of a particular wavelength is emitted, the more of that particular element is in the atmosphere of the exoplanet. Even if we can't make this sort of measurement directly, we can observe the disappearance of specific light patterns when the exoplanet moves behind its star, and thus we can deduce the composition of the atmosphere. Once we have verified the existence of an exoplanet, once we know where to point our telescopes, we can learn a great deal about that exoplanet through simple observations and calculations. The diverse list of planets given in Chapter 1 was derived from this sort of work. Visiting the exoplanets. In the chapters that follow, we explore the new Kepler universe by imagining what it would be like to get on a spaceship and make a visit to each new world. We begin each visit by talking about what we can learn about the planet by observing it, and then try to explain those observations in simple terms. This process involves a certain amount of guesswork, as you might imagine, but no matter how strange our new planet may seem, the same basic laws of physics and chemistry that operate on Earth apply there. This means that our speculations can be based on a solid bedrock of scientific knowledge, even if applying those laws leads us to describe a world very different from our comfortable Earth. In addition, as we saw in Chapter 2, we already have a lot of experience with new kinds of worlds from the exploration of our own solar system, an experience that will supply many useful analogies in our discussion. To remind ourselves about the speculative nature of all these scenarios, however, we include a section appropriately titled Caveats at the end of each visit to talk about ways future measurements or theories might change the picture we're presenting. Finally, we should say a word about how these exoplanets are named. The general scientific procedure is this. We begin with the name of the star, which is followed by a letter indicating the order in which the planet was discovered. Thus, for example, the first planet we visit is labeled 55 Cancri E, which means that it was the fifth planet discovered around the star 55 Cancri. So fasten your seatbelts and get ready to explore our marvelous new galaxy. The planet's whole atmosphere is glowing brilliant green and yellow with a bit of red thrown in. The most intense light displays are at the poles. Powerful radio bursts blast out from high above the surface. The planet itself is black and doesn't reflect light, despite the intense heat that results from its close proximity to its star. An irregular network of gleaming white-hot lines interlace across the dark surface, like some impossible Jackson Pollock painting. Here and there, volcanoes spew something into the atmosphere that creates a diamond-like brilliance, catching the light of the star in spectacular displays. What is this place? The 55th brightest star in the constellation of Cancer, the Crab, 55 Cancri, is a pretty ordinary star. A little smaller than the Sun, a little cooler, a little over 40 light years from Earth. At first it doesn't seem to have much to command our attention, though there are a few intriguing characteristics we might mention. The star is, for example, much older than the Sun, between 7.9 and 8.4 billion years old, in contrast to the Sun's comparatively youthful 4.5 billion years. It also has a somewhat higher concentration of heavy elements. It isn't, however, the properties of the star that brings us to this section of the sky, but the fact that 55 Cancri is surrounded by a complex planetary system that includes the body 55 Cancri e, a planet first detected in 2004. This is the place we are calling Diamond World, one of the most extraordinary planets discovered by the radial velocity method. Stars and planets are made from materials in the same interstellar cloud, so we would expect the high concentration of heavy elements in the star to be reflected in the composition of its planets. One way to think about the role of stars in the universe is to picture them as huge factories that use primordial hydrogen as a fuel for nuclear reactions, producing metals that are returned to the cosmos when the star dies. In the jargon of astronomers, any element heavier than hydrogen is referred to as a metal, even gases such as oxygen and elements such as carbon. These metals are then taken up in new stars and planetary systems when they form. Our own Sun, for example, can be thought of as a third-generation system, having been formed from material created in 3 successive stellar cycles. 55 Cancri is most likely a 4th-generation star, a fact that explains its higher content of metals. Hypothetically, as we approached 55 Cancri in our imaginary spaceship, our first encounter with its planetary system would have occurred when we were about 100 times as far from the star as Earth is from the Sun. Astronomers refer to the Sun-to-Earth distance as the astronomical unit, or AU, and we adopt this nomenclature in what follows. We'd run into a disk of icy and rocky materials ranging from asteroid-sized to the size of Earth's moon. This outer disk is a direct analog to our own Kuiper belt. See Chapter 2. Moving inward, we would encounter our first large planet labeled 55 Cancri d, located 5.8 AU from its star. This planet is about 3.8 times as massive as Jupiter. The rest of the planets in the system are located less than 1 AU from their star, but before we get to them, we'd pass through another familiar feature, an asteroid belt. Made up of the same kind of rocky material we see in our own asteroid belt, the belt around 55 Cancri would have been thinned out by gravitational interactions over the long history of the system, and those same interactions would have produced the kind of gaps in the belt that we see in the rings of Saturn. Most likely it would have hundreds of small gaps, making it look something like the grooves on an old-fashioned vinyl record. Once we got to 0.78 AU, closer to the star than Earth is to the Sun, we'd encounter the objects that brought us to the system. A compact set of 4 planets ranging in size from about 8 times the mass of Earth to almost the mass of Jupiter. It is the innermost planet of this group, the world labeled 55 Cancri e, that will be the focus of our attention for the rest of our visit in this chapter. The first thing we notice about the planet is that it has an unusual orbit. It's tilted almost 80 degrees with respect to the equatorial plane of the star. In our own solar system, Pluto has the most tilted orbit, and that tilt is only 17 degrees. More importantly, though, 55 Cancri e moves very fast. It completes an orbit in only 17 hours, which means that its year is less than an Earth day. Most astronomers assume that the planet is tidally locked, which means that it always presents the same face to the star, much as the moon always presents the same face to Earth. This means that the lengths of the planet's day and year are the same. The basic laws that govern planets are called Kepler's laws of planetary motion. They were discovered by Johannes Kepler, 1571 to 1630, after whom the Kepler satellite itself is named. If we apply these laws to 55 Cancri e, we find that its orbit lies within the chromosphere, outer atmosphere, of its star. In a real sense, the planet is actually inside the star. We can start our analysis of the planet by trying to figure out what 55 Cancri e is made of. Its radius is about twice that of Earth, and it has a mass almost 9 times that of our own planet. This means that it has a density similar to rocks and metals on Earth, about 6 times the density of water. The size and density of 55 Cancri e pose some problems. For one thing, a planet of this size in our solar system would lie in the outer reaches like Uranus and Neptune, but these so-called ice giants have a density only about twice that of water. Furthermore, if a planet the size of 55 Cancri e had the same chemical composition as Earth, its own gravitational force would compress its rocks to twice the density we actually see. We have to do some careful calculations, but when we do, we find that we can understand the size and density of this planet if half of its material is carbon, with the rest being silicon, oxygen, and a smattering of other elements. This is our carbon world. This actually explains why most of the planetary surface is dark. Because it is so close to its star, 55 Cancri e receives almost 3,000 times as much stellar radiation as Earth receives from the Sun. This means that the planet is extremely hot, with a surface temperature near 2,000 degrees Celsius, 3,200 degrees Fahrenheit. Nevertheless, the planet seems to be dark with a reflectivity something like that of charcoal, which is, after all, another form of carbon. We can begin to understand the bright lines in volcanoes by noting that the electromagnetic radiation we receive from the planet's surface isn't reflected starlight, as it would be if we were observing a planet in our own solar system, but energy forcing its way up from the interior of 55 Cancri e itself. The interior of 55 Cancri e must be very hot and most likely contains liquid metals. We'll see where this fact leads us in explaining the planetary surface. The radio waves we detect are something we usually associate with particles running along magnetic field lines. In our own solar system, planets such as Earth and Jupiter generate magnetic fields through a combination of rotation and the presence of materials that conduct electricity in their interiors. Earth's magnetic field, for example, is generated by what is called a dynamo, associated with the rotation of the liquid part of its iron and nickel core, while Jupiter's magnetic field is associated with the rotation of metallic hydrogen. Particles, mostly from the solar wind, are accelerated along the lines of the planetary magnetic fields, producing the northern and southern lights on Earth when the particles collide with molecules in the atmosphere. The same effect produces radio emissions in Jupiter's much more extensive magnetic field. It is reasonable to suppose that 55 Cancri e should behave like Jupiter, only more so. Like all Jovian planets, it would have a rocky, metallic core several times the size of Earth. In fact, given its rapid rotation and the fact that it probably has conductive liquid material such as iron in its interior, we would expect to see a magnetic field several thousand times stronger than that of Earth. In addition, given the proximity of 55 Cancri e to its star, and assuming that the star emits something like a solar wind, as most stars do, we should also expect to see some pretty spectacular fireworks associated with the outflow of stellar particles. The reason for this is that the system we've described involves two strong but competing forces. One, magnetism, tries to protect the planet's atmosphere, while the other, the stellar wind, tries to destroy it. We can start to understand this interplay by noting that geological processes in the planet, processes we will describe, are constantly releasing gases, perhaps carbon dioxide or hydrogen cyanide, into the atmosphere. The intense heat quickly breaks up these molecules into their atomic components. If there were no magnetic field on a planet, the strong stellar wind would blow this nascent atmosphere off as fast as it formed, leaving an airless ball behind. The presence of a magnetic field changes all that, however. On 55 Cancri E, as on Earth, the magnetic field deflects the incoming particles in much the same way that a large rock deflects water in a swiftly flowing stream. The planet's magnetic field, which we would normally expect to be a symmetrical two-lobed structure, is distorted and stretched in the downstream direction. On the upstream side, pressure from the stellar wind compresses the field, and that is our competition, the stellar wind trying to push the magnetic field down to the surface, and the magnetic field pushing back to keep the particles away. It could happen that these two forces come to equilibrium and produce a stable atmosphere. We suspect, however, that they will not for this system. We know that the solar wind from our own sun is erratic, producing bursts we usually call solar storms or space weather. These events often have serious effects on terrestrial communication systems and power grids and are a major source of danger to unshielded astronauts in space. If the star 55 Cancri behaves in a similar way, we can imagine scenarios in which intense stellar bursts push the magnetic field down and blow away the atmosphere. Then, when the storm subsides, the magnetic field would reassert itself and the atmosphere would be rebuilt, burrowing in concentration until the next stellar outburst. The atmosphere in this case would be in a constant state of change. Finally, the fact that the planet's magnetic field is distorted and stretched out downstream by the stellar wind leads to a phenomenon known as reconnection, whose main effect is to accelerate particles back toward the planet. Screaming in along the field's lines, they would produce northern and southern lights so intense that you could read this book in the middle of the night if you were on the surface. To understand the appearance of the sky on this strange world, however, we have to think a little more about the atmosphere with which these incoming particles are interacting. On Earth, the air we breathe is made up of mostly molecular nitrogen and oxygen, two atoms of nitrogen or oxygen bound together. On 55 Cancri E, however, the temperature is too high for molecules to stay together. In addition, the high temperature makes it easy for light atoms, such as hydrogen and helium, to escape into space. We expect, then, that whatever atmosphere the planet has is composed of atoms of carbon and oxygen being released from the surface as carbon dioxide molecules, and then broken up as described earlier, mostly a carbon atmosphere for a carbon world. Given the known properties of carbon, we can understand the green and yellow colors we observe, since this is the kind of light that carbon atoms emit, while oxygen atoms supply some red and green as well. Furthermore, given the fact that the stellar wind particles are being funneled toward the poles by the magnetic field, we understand why those regions are brighter than the rest of the planet. What about that network of bright lines on the surface? Again, an analogy with our home planet can help. We know that the surface of Earth is constantly changing, that no geological feature lasts forever. The main reason for this situation is that the interior of the planet is very hot, partly because of the decay of radioactive nuclei and partly because Earth is still in the process of cooling down after its fiery beginning. As a result, the interior of the planet boils, moving around chunks of the surface known as plates. The continents ride on the plates, and so are in constant motion. This process, known as plate tectonics, should be seen on any planet where there is a significant heat flow from the interior. On Earth, the boundaries of the plates produce well-defined geological features. The Mid-Atlantic Ridge, for example, is an undersea mountain chain extending from Iceland to Antarctica. It marks the place where hot magma from the interior comes to the surface and then cools to create new crust. Similarly, the Andes Mountains on the western coast of South America mark a place where one plate is pushed beneath another and crust is destroyed. These sorts of places are known as subduction zones and are often associated with volcanic activity. The history of Earth can be thought of as a constant interplay between the creation and destruction of surface material, with continents moving around in response to forces deep beneath the surface. Because 55 Cancri E has a mass almost 9 times that of Earth, the cooling off process will take much longer there than it has for Earth. Consequently, we should see that same interior, boiling process that we see on Earth. The deepest interior should in fact contain a material unknown on Earth, liquid carbon, or if you prefer, liquid diamonds. Remember that it is the rotation of this molten material that gives rise to the magnetic field described earlier. The bright lines we see on the surface are, in fact, places like the mid-Atlantic ridge, where molten material from the interior is coming to the surface, glowing brightly until it cools off. But the most spectacular geological features on 55 Cancri E could be the subduction zones and their associated volcanoes. As molten carbon from the interior is brought to the surface, it may crystallize into diamonds before being spewed into the atmosphere, creating a light show unlike anything we've ever seen on Earth. Coupled with the intense auroras, the diamonds would make the surface of this world an artist's dream, provided, of course, that we could find a way for the artist to survive there. This carbon world is a good case study of a type of planet we expect to find in some abundance in the galaxy, large planets made primarily from heavy elements. We can, in fact, imagine many variations on the 55 Cancri E theme. We will probably find iron worlds, nickel worlds, sulfur worlds, and so on, since we know that all of these elements are made in stars. In fact, the planet Mercury in our own solar system could reasonably be labeled a nickel-iron world. Each of these heavy metal worlds will have its own peculiarities, its own unique characteristics. As always, the variety we find when we look at exoplanets challenges our imagination. First, we should point out that measurements of the density of 55 Cancri E are still in the process of being refined, so our estimates of the carbon content on this world may change. It's hard to see, however, how such refinements could alter the conclusion that the planet has a high percentage of that element. The existence of a magnetic field and the behavior of solar wind particles are based on pretty solid reasoning. So, unless 55 Cancri is one of those rare stars without a solar wind, that part of our description should stand. The discussion of plate tectonics is a little more speculative. The laws of physics and our experience with our own solar system tell us that there must be an intense heat flow out of the planetary interior, but how this heat flow affects the surface is a somewhat trickier question. Theoretical studies of planets in our own solar system indicate that the presence and motion of plates depend critically on details such as the amount of water in the planet's interior. A planet without much water might find its surface motion locked up, like a frozen engine. We think, for example, that it is the low concentration of water on Venus that prevents it from exhibiting plate tectonics, even though it is roughly the same size as Earth. We argue, however, that it is reasonable to expect to find the kind of plate boundaries and diamond volcanoes we've described on 55 Cancri E. And if we don't find those features on 55 Cancri E, we'll undoubtedly find them somewhere else in the galaxy. It's dark. Very dark. The only lights are pinpricks of illumination from stars located light years away, but it's not cold. In fact, it's like a house in which the lights have been turned off, but the furnace is still running. There's no sun in the sky, but you can hear waves lapping on a distant shoreline. Any life in this place must see in the infrared because there is almost no visible light. We must be on a planet, or at least a moon. But where is this planet's sun? Doesn't every planet have to be in orbit around a star? Well, maybe not. Think back to our description of the formation of the solar system in Chapter 2. We can think of the formation as proceeding in 3 stages, something like shifting gears in a car. First, the planets form. Then, the remaining dust and debris get absorbed or thrown out of the system, and finally, the planets begin a complex dance driven by the force of gravity, what we call a game of cosmic billiards. In this last stage, planetary orbits shift around and planets can be ejected from the solar system. According to some theoretical calculations, as many as a dozen Mars-sized objects may have been thrown out of our own nascent solar system during this phase. However, these ejected bodies don't just disappear. They continue wandering around the galaxy, most likely in orbits around the galactic center. In fact, it is likely that there are many more of these rogue planets out there than there are planets circling stars. Faced with this fact, our first impulse might be to think that rogue planets must be pretty uninteresting, frozen worlds with no life, no heat, no energy. We argue, however, that this impulse results from what we called surface chauvinism in Chapter 1. We know that even on Earth, life is not confined to the surface. There are complex ecosystems around deep-sea vents, for example, and bacteria living in a rock a mile beneath the surface. Both would do quite well if Earth itself became a rogue planet, although in that case the oceans would freeze over. In fact, as we said before, a planet without a star is a little like a house with the lights turned off, but the furnace running. The inside temperature of the house, or of a relatively large planet, really isn't affected much by the star's absence. In the previous chapters, we have come across 4 different ways that energy can be supplied to a planet. Number 1. Direct radiation from a star. This is what powers life on Earth's surface. Number 2. Cooling off from the initial period of formation, a process that can take many billions of years. It's still supplying energy to Earth, for example. Number 3. Radioactive decay of elements in the planetary interior. The decay of uranium is an important source of Earth's internal energy. Number 4. Tidal heating. This is what produces the subsurface oceans on the moons of Jupiter and Saturn, as we saw in Chapter 2. Looking at this list, we see that only the first item depends on the presence of a star. A planet, wandering off on its own, still retains its original internal heat, and radioactive nuclei still decay inside it. If the planet is a gas giant, it may well be accompanied by its moons, and the force of gravity still produces tidal flexing to sustain subsurface oceans, just as it does on some of the Galilean moons of Jupiter. Except for the surface, then, the presence of a star is pretty irrelevant for any planet or moon, and we are as likely to find life on a rogue planet as we are to find it in the oceans of Europa or, for that matter, around deep ocean vents on Earth. And this means that rogue planets are as interesting to study as their star-circling cousins. Given this fact, we are immediately confronted with the question of how to detect rogue planets. Neither the radial velocity method nor the repeating transit method, the techniques we've used to find exoplanets up to this point, will work, because they both depend on the presence of a star. Alternatively, since, as we'll see, rogue planets generate a lot of heat, we could look for them with infrared detectors. Unfortunately, our current infrared detection sensitivity is too low to allow this to be a feasible means of finding these worlds at this time. Instead, finding rogue planets will require a totally new way of trying to find planets, since up to now we have discussed only techniques requiring the presence of a star. In fact, astronomers have known of such a technique for some time. It's called gravitational lensing, and it comes from, of all places, the general theory of relativity. The theory predicts that when a beam of light or other kind of electromagnetic radiation passes near a massive object such as the sun, its path is deflected. Looking back along this deflected path, it appears to an observer that the light beam is coming from a different place than its actual source. It was, in fact, the detection of this deflection during a solar eclipse in 1919 that first propelled Albert Einstein to international prominence. Now imagine a rogue planet moving into a position directly between you and a distant star. Imagine further a cone of light emitted by the star in such a way that the rogue planet is at the center of the cone's base. Each ray in the cone's surface is deflected by the mass of the rogue planet, and those rays come together at the point where you are making your observation. In effect, the rogue planet acts as a kind of lens, focusing the light from the distant star. Looking back along these focused rays, however, you see not a single point of light, but a ring of light corresponding to the extension of that focused cone. This so-called Einstein ring indicates the presence of a massive object between you and the star. Although if the alignment isn't exactly as described, you'll see arcs of light rather than a complete ring. Gravitational lensing is widely used in astronomy to detect massive objects of galactic size, especially concentrations of dark matter, but it can be used to detect rogue planets as well. The challenge, of course, is that we don't know when and where a ring will show up, so there is no monitoring technique that can maximize the chances of detection. The best we can do is depend on chance alignments to give us a ring now and then. For this reason, we have seen evidence for only a handful of rogue planets to date. From these few detections, however, astronomers have estimated that the number of rogue planets in the galaxy is larger than the number of planets circling stars. Because of the uncertainties in the data, these estimates are extremely imprecise, but they put the number of rogue planets between 2 and 100,000 times greater than the number of their more sedentary brethren. Given the paucity of data, we are going to take a different approach to discussing rogue planets than we did for Diamond World. Instead of imagining a visit to a known world, we will imagine what the life history of a rogue planet might be. We'll name our fictional planet Haven for reasons that we will describe later. Metaphorically speaking, our own sun is located in the far suburbs of the Milky Way. On a clear night, we can see about 2,000 stars in the sky. Move in toward the galactic center, still suburban but closer to downtown, and you can easily get into a position where the skies would blaze with 100 times as many stars. We'll put Haven's birthplace in a region like that. In Chapter 6, we saw that all heavy elements, metals, are made in stars and returned to interstellar space when stars die. Because Haven's star would have formed closer to the center of the galaxy, we expect that there would have been many more supernovae in its neighborhood than in our own, and hence that objects in Haven's home system would contain more heavy elements than are found in our own system. These heavy elements, of course, include radioactive materials capable of generating heat. We expect that the basic process of planetary formation for Haven and its neighbors would have gone on pretty much as it did in our own system, with perhaps some variations due to the greater number of supernovae in the region. Inside the ice line we discussed in Chapter 2, we find small, rocky, terrestrial planets with gas giants forming farther out. Like Jupiter, these gas giants have a rocky core, perhaps several times the size of Earth, covered by massive mantles of hydrogen and helium. Oddly enough, this structure would introduce a new supply of heat into Haven's interior. At the kind of pressures we find inside the planet, liquid hydrogen and helium don't mix, so the heavier helium would form into drops and fall toward the planetary center. This helium rain would have the effect of releasing gravitational energy, adding yet another source of heat to the list we gave earlier. We know that this process occurs because we can detect its effects in Saturn. The formation of our planet is in some ways a miniature version of the formation of its solar system. As the central body of Haven takes shape, it would acquire a disk of materials that form planetesimals and, eventually, moons. The location and size of these moons would be a matter of chance, but just for the sake of argument, let's suppose that Haven acquires 4 moons like the Galilean moons of Jupiter and 1 large moon, maybe an Earth-sized moon, farther out. We also expect that collisions between the planetesimals would supply enough rubble to populate a series of rings around the planet, rings similar to those we see around Saturn. Gravitational forces over time turn these rings into the vinyl record configuration we saw in the last chapter. The fact that all these moons are forming beyond the ice lines means that many of the planetesimals in orbit would contain water ice. Thus, as each moon forms and its temperature increases because of heat generated by inflowing objects, it reaches a point where surface oceans form. Add in the extra energy provided by the decay of radioactive nuclei, nuclei that, as we saw earlier, could be more abundant than in our own solar system, and those oceans might even boil. Eventually, however, enough energy would be radiated into space to drop the surface temperatures of the moons below the freezing point, and the oceans would be covered with a layer of ice. From this point onward, the subsurface oceans would be kept liquid by a combination of the residual heat of formation, radioactivity, and tidal heating. It's essential to realize that Haven's star has little to do with the formation of the moons. The most important force operating is the gravitational attraction of the planet itself. As the game of cosmic billiards progresses in Haven's system, we can imagine many scenarios that could result in the ejection of planets. For example, Haven might get locked into a gravitational tug-of-war with one of the other gas giants, a tug-of-war resulting in the ejection of Haven and one or more terrestrial planets and the rearrangement of the orbits of the remaining planets. Nothing in this process, however, would separate Haven from its moons. The mutual gravitation involved is much too strong. So, when Haven heads out into the galaxy, leaving its star behind, it takes its moons along with it. As discussed in Chapter 2, our current theories suggest that planets were ejected early in the history of our own solar system. What happens to Haven after ejection depends on the details of the ejection process. The planet could go into a highly eccentric, comet-like orbit around the galactic center, or it could, like the Sun, settle into a sedate circular rotation, making a circuit every 200 million years or so. Whatever happens, however, Haven is extremely unlikely to suffer collisions with another star or rogue planet. Space is just too empty for that to happen. It will, in fact, achieve a kind of immortality, circling around in interstellar space for billions of years as it slowly cools off. While this is happening, though, interesting things are occurring on Haven's moons. The initial heating of a small moon during formation could actually boil off the surface ocean. The gravitational attraction of the moon wouldn't be enough to hold on to the molecules, and they would be lost to space. Such a moon might evolve into something like Jupiter's moon, Io, with volcanoes driven by heat flowing out from the interior. Other moons might be more like Europa. After an initial cooling off period, they would have oceans, perhaps hundreds of miles thick, covered by a relatively thin layer of ice. Tidal heating, together with heat from the interior, keeps these oceans liquid and perhaps even keeps them at temperatures above the Earth's surface. Such moons, like Europa, are prime candidates for the development of life. But it is the farther Earth-sized moon that interests us most. Let's call this moon Haven 5, following our assumption that Haven, like Jupiter, has 4 Galilean-type moons. Because of its size, the heat from Haven 5's initial formation would be slow and dissipating. We expect that the initial melting would allow heavy materials such as iron and nickel to sink to the center, so that this moon, like Earth, would have a heavy core. In addition, because of the moon's size, we expect the heating from radioactive nuclei to be intense. Consequently, we expect this moon to exhibit the kind of tectonic activity we saw on 55 Cancri E in the preceding chapter. Molten material from the interior would be continuously brought to the surface and perhaps drive its own version of plate tectonics. The material brought up from the interior would contain gases such as steam and carbon dioxide that would be released at the surface. Unlike moons such as Io, however, Haven 5 is big enough to hang on to those gases, so it would acquire an atmosphere, probably an atmosphere rich in carbon dioxide and maybe molecular hydrogen. And this leads us to the most surprising feature of this world, the existence of something very similar to a greenhouse effect. We are used to thinking about Earth's greenhouse effect this way. Sunlight comes to the surface because the atmosphere is largely transparent to visible light. The energy, however, is sent back into space as infrared radiation, which tends to be absorbed by carbon dioxide. Thus, the presence of carbon dioxide raises the temperature of the surface above what it normally would be. The key point to notice in this scenario is that the source of heat coming to the surface isn't what's important. The warming effect operates when that heat is radiated upward toward space into an atmosphere that contains carbon dioxide. Haven 5 would have no incoming starlight, but it would have sources of intense heat in its interior, and this heat would cause its surface to radiate in the infrared. As this radiation tries to escape into space, it would be absorbed by carbon dioxide in the atmosphere, and the surface of the moon would be warmed just as Earth's surface is warmed by the greenhouse effect. We can even imagine scenarios in which the combination of internal heat and atmospheric warming keeps the surface temperature high enough to maintain liquid oceans. Haven 5, in other words, would look just like Earth, except that there would be no sun in the sky. To beings like us, who interact with the world by using visible light, the moon's surface would be eternally dark, the darkness of interstellar space. Any life that evolved on the moon would most likely have eyes that saw infrared radiation, since there is abundant heat on Haven 5. We note that some animals on Earth, such as pit vipers, have organs that see in the infrared. So now it is clear why we called our imaginary rogue planet Haven. Despite the absence of a star, its moons could have liquid oceans, perhaps even surface oceans. In the cold depths of interstellar space, its moons could indeed be havens for life, possibly even life on the surface. However, we have to recognize that our chances of detecting a system like Haven are not very good. It won't shine by reflected light, since it is near no star and it has no light source of its own. Our telescopes won't pick it up, and it would have to pass improbably close to Earth for us to pick up its signature in the infrared. But such habitable rogue planets might be ubiquitous. Obviously, the system we've described is fictional. We argue, however, that if rogue planets are really as common as estimates suggest, then there is almost certainly a haven out there waiting to be discovered. The existence of a surface ocean on a large moon isn't impossible, but its existence would depend critically on the amount of internal heat flowing to the surface. With little tidal heating, this heat would have to come from the heat of formation and radioactivity. Both of these sources diminished with time, so eventually the moon's surface oceans would freeze over. The insulating properties of the ice would probably be good enough to keep water beneath it liquid for a long time. The question of whether life could develop in such an environment is one on which reasonable people differ. We'll discuss the origin of life on Earth in Chapter 11, but here we simply note that life on our own planet developed very quickly once it was able to do so. It is conceivable, therefore, that life on Haven 5 could have developed while the moon had a surface ocean or around deep-sea vents if it didn't. We'll leave the question of what that life might be to science fiction writers. It's cold.
Beyond the Milky Way. With the size and shape of the galaxy measured, the question of our place in creation now shifted from the position of the Sun within the galaxy to the nature of the universe itself. If the progress from Copernicus through Newton to Leavitt and Shapley appears relatively fast, certainly when viewed in the context of the glacial progress through the 2,000-year dominance of Aristotelian thinking, then the decade that followed Shapley's determination of the size of the Milky Way might be described as an intellectual avalanche. The revolution was fueled from two sides. A new generation of telescopes and the increasingly sophisticated observational techniques developed by astronomers like Leavitt, Hertzsprung and Shapley provided the data, and in parallel, theoretical physics experienced a revolution. Claims of revolutions or paradigm shifts have to be made with great care in science. Indeed, the terminology is quite unfashionable in certain academic circles. But from a physicist's perspective, there is no doubt that physics experienced a revolution in 1915, because in November of that year, Albert Einstein presented a new theory of gravity to the Prussian Academy of Science. The theory is known as general relativity, and it replaces Newton's law of universal gravitation. Many physicists regard general relativity as the most beautiful piece of physics yet devised by the human mind, and we will explore why this is so a little later. For now, let us note that the Big Bang, the expanding universe, black holes, gravitational waves, and the whole evocative landscape of 21st century cosmological language began, absolutely, with the publication of general relativity. The parallels with the Newtonian revolution are clear. Without Newton's laws, there is no deep understanding of the solar system and the motions of the planets. Without general relativity, there is no deep understanding of the large-scale structure and behavior of the universe. But we are getting ahead of ourselves. As the second decade of the 20th century dawned, the size and shape of the Milky Way galaxy was established, albeit with rather large errors, but the true extent of the universe beyond our galaxy was still hotly debated. Could we at least cling to a sort of token pre-Copernican fig leaf and place our galaxy at the center of the universe? The desire to be special runs deep. The last intellectual rearguard action against our demotion can, rather theatrically, be said to have been played out on a single evening on the 26th of April 1920 in the Baird Auditorium at the Smithsonian Museum of Natural History, Washington, D.C. This is, of course, an oversimplification, but allow me a minute to enjoy the sound of the outraged, shaking jowls of 1,000 historians of science before I qualify and partially justify this hyperbolic claim. The Mariner 10 mission had enabled scientists to see about half of the planet, so the first real glimpses into the terrain of Mercury came from the flybys of Messenger. As planetary scientist Nancy Chabot explains, before Messenger, we had only seen 45% of the planet, and we saw some stuff during the flybys before we went into orbit. But after orbiting the planet, we've now mapped 100% of the planet and seen nearly everywhere. There are some permanently shadowed regions which are still mysterious, but after mapping the full planet, we have a good idea of what the surface looks like, and craters are absolutely a dominant landform. This planet has been sitting there for billions of years and been hit over and over, and it hasn't had a lot of processes to destroy those craters. Amongst the thousands upon thousands of craters on Mercury, the largest by far is Caloris Planitia, a lowland basin 1,525 kilometers in diameter that is thought to have formed in the early years of the solar system, around 3.9 billion years ago. It was first spotted as Mariner 10 sped past in 1974, but due to the trajectory and timing of the craft, only half of it was lit, so the full character of this crater remained a mystery for another 30 years, until Messenger could photograph it in all of its glory. Taking one of its very first photos, Messenger revealed Caloris to be bigger than had been previously estimated, encircled by a range of mountains rising 2 kilometers from the Mercurian surface, whose peaks create a 1,000-kilometer boundary around the lava plains within. On the other side of the mountains, the vast amount of material that was lifted from the planet's surface at the moment of impact formed a series of concentric rings around the basin, stretching over 1,000 kilometers from its edge. The collision that created Caloris hit Mercury with such force that it also had more global consequences. Messenger photographed in great detail an area named, in the not particularly scientific vernacular, the weird terrain, a region at the planet's diametrically opposite point, the antipode to Caloris. This area of strange geological formations, distinct from the rest of the surrounding terrain, was likely created by the seismic shock wave of the Caloris impact, reverberating through the whole of the planet. Right up until the end of its mission in 2015, Messenger continued to uncover many of Mercury's secrets, including a few very particular surprises. Using a combination of photography, spectroscopy, and laser topography, Messenger revealed tantalizing evidence that even this close to the Sun, water ice can exist on the surface of a planet. Even though the Sun blasts much of Mercury's surface, the tilt of its rotational axis is almost zero, so there are craters and features around the planet's poles that never see direct sunlight. Combined with the lack of atmosphere, These regions are forever exposed to the freezing temperatures of space, and it's in this environment that Messenger was able to record the clear signature of water ice. Here, in the eternal night of a polar crater, it's cold enough for ice to survive for millions of years, just meters away from the savage ferocity of the sun's light. However, Messenger's most startling discovery was still to come. The mission objectives had been developed to explore the deep history of Mercury and provide data to test against our theories of the formation and early life of the planet. Messenger was equipped with a collection of spectrometers designed to analyze the composition of Mercury at different depths. The Messenger team had worked on a detailed set of predictions outlining the chemistry of the planet. But as the spacecraft began to sniff at the Mercurian surface, it soon became clear that our assumptions had not been quite right. As the gamma-ray and X-ray spectrometers analyzed the elements on Mercury's surface, they began to measure the unexpected characteristic signature of a number of elements such as phosphorus, potassium, and sulfur at much higher levels than they were expecting. Up to this point, the working hypothesis had been that during the formation of Mercury and all the rocky planets, as the rock condensed and combined to form the planet, the heavier elements like iron would sink towards the center, forming the bulk of the core, while the lighter elements, such as phosphorus and sulfur, would remain near the surface. These more volatile elements would then be expected to be stripped away from the surface, particularly on a planet like Mercury, which is so close to the Sun. And yet the Messenger data confirmed high levels of potassium, and sulfur was detected at 10 times the abundance of the element on Earth or the Moon. Both are volatile elements, easily vaporized, and when this close to the Sun, they simply should not have survived the planet's birth. On top of that, the Messenger data confirmed what we had long suspected about the structure of Mercury, that it is the densest of all the planets, with a massive iron core making up 75% of the planet's radius, compared to just over 50% here on Earth. The core creates a strange lopsided magnetic field, indicating that the internal dynamics of the planet are different to anything we have seen before. All of this adds up to making Mercury something of a mystery, as nothing quite accords. The eccentric orbit, the abundance of volatile elements on the surface, and the oversized iron core all point to the planet having a history far more complex than was first imagined. And the only explanation to make sense of the Messenger data is that Mercury was not born in its current sun-scorched position. It has long been supposedly known that the orbits of the planets are eternal, stable loops that sustain the structure of the solar system in an endless rhythm. But everything we are learning now suggests that this is far from the whole story. Mercury, like all 4 of the rocky siblings, was formed of molten rock. A few million years later, as the young planet began to cool, its crust solidified, and its journey around the Sun transformed from being part of a swirling cloud into a clearly defined passage, an orbit. The path the infant Mercury travelled, however, was most probably far removed from the course it now holds. The young Mercury was born not as the closest planet to the Sun, but at a much greater distance, far beyond the orbit of Venus, beyond Earth, perhaps even beyond Mars. This was a planet that came into being in the mildest region of the solar system. It was far enough away from the Sun to allow volatile elements like sulfur, potassium, and phosphorus to be folded into its first rocks without being vaporized away by the heat of the Sun, but maybe near enough for its surface to be warmed, perhaps even just the right amount for liquid water to settle on its surface. This may well have been a planet big enough to hold an atmosphere, a watery world upon which all the ingredients of life could well have existed. Mercury, it seems, really did have its own moment in the Sun, but these hopeful beginnings were not to last. Today, it's hard to imagine the planets in any orbit other than our night sky. They feel eternal, permanent, and so it's natural to think of the solar system as a piece of celestial clockwork, a mechanism running with perpetual and unchanging precision, marking out the passage of time. In time frames that we can comprehend, days, weeks, months, and years, the motion and trajectory of the planets is just that, clockwork. We use these markers to plot out the 24 hours of a day, 365 days of a year, and the lunar cycle is, of course, intimately linked to our months. Beyond that, Newton's laws of universal gravitation, first described in 1687, allow us to this day to plot out the trajectories of all the heavenly bodies far into the future and back into the distant past. This predictability of motion is what allows us to plot great astronomical events, such as eclipses and transits, far into the future. It's why, for example, we can predict that on the 14th of September 2099, the Sun, Moon and Earth will be in precise alignment to create the final total solar eclipse of the 21st century across North America. But 100 years ahead or behind us is nothing more than a proverbial blink in terms of the life of the solar system, and over longer durations the clockwork becomes a lot less reliable. If there was only one planet orbiting one star, for example if Mercury was the orphan child of the solar system, we would be able to calculate precisely the gravitational force between Mercury and the Sun, and to plot Mercury's orbit around the Sun with essentially infinite precision. But add one more planet into our rather vacant imaginary solar system, let's say we make it Jupiter, so there is now a gravitational force between all three objects, the Sun, Mercury and Jupiter, and it's no longer possible to calculate exactly where they're all going to be in the future, or where they were at some point in the past. When there are more than two objects in play at any one time, you have what physicists call a chaotic system. It means the planets can push and pull one another, moving entire orbits in ways we simply cannot predict. So the further we look back in time, the less certain we are of the position of any of the planets. Our mathematics fails, so instead we have to rely on circumstantial evidence to piece together a picture of the past. In the case of Mercury, it's the evidence from MESSENGER detailing the levels of volatile elements like potassium and sulfur that enable us to begin to understand the early life of the planet and infer that Mercury must have begun life further out in the solar system than it finds itself today. So what happened next? How did a planet that began its life in the sweet spot of the solar system end up in the scorched interior? The answer lies in the other clue MESSENGER confirmed for us, Mercury's massive iron core. Relative to its size, Mercury has the most massive core of any of the rocky planets. 75% of its diameter and almost half of its mass is molten iron, compared to around just a fifth of the mass of the Earth. We've suspected the oddity of Mercury's composition for well over 150 years, and that's because of some brilliant deduction by a German astronomer called Johann Franz Encke, who determined the mass of Mercury by measuring the gravitational effect it had on a passing comet, a comet that we now call, unsurprisingly, Comet Encke. With an approximation of the planet's mass, we are able to calculate the density of the planet, and with that calculation, approximate its composition. So we've known for some time that Mercury is odd, but only with the arrival of MESSENGER did we begin to reveal just how odd the smallest planet actually is. By accurately measuring Mercury's magnetic field, we've been able to confirm that far from being a geologically dead planet, Mercury has a dynamic magnetic field driven by an internal force, indicating that the core is at least partially liquid. This goes against the conventional thinking of planetary dynamics, because we would expect a planet as small as Mercury to have lost its internal heat long ago. Just as Mars lost its heat because of its size, we would have expected the core of Mercury to have cooled and solidified. But MESSENGER's data proved otherwise. By combining precise measurements of Mercury's gravity field with the extraordinary mapping of its surface, MESSENGER found that Mercury's structure is unique in the solar system. It appears to have a solid silicate crust and mantle above a solid layer of iron sulfide, which surrounds a deeper liquid core layer possibly with a solid inner core at the center of the planet. This challenges all the theories about its formation. 4.5 billion years ago, we know that the inner solar system was in turmoil. In the middle of it all, the newly born Mercury found itself orbiting far out from today's intimate proximity with the Sun, surrounded by rocky debris and scores of planetary embryos all jockeying for position. The young solar system was still a place where planets could live or die. But it wasn't just the rocky planets that found themselves disturbed. Jupiter, the largest and oldest of all the planets, was on the move. And when a planet of that size shifts its position, there are almost always casualties. We'll come back to the story of Jupiter's grand tack and the havoc it spread throughout the solar system in Chapter 3. But for now, all we need to know is that the evidence suggests that the juvenile Mercury was kicked by the gravitational force of Jupiter on an inward trajectory, finding itself flung in towards the Sun and into the path of danger. In the crowded orbits of the early solar system, such a change of course was fraught with danger, and all of the evidence indicated that this was the most violent and defining of turns in Mercury's history. As the planet swerved inwards, it collided with another embryonic world and shattered. Today we see the evidence of this ferocious collision in the strange structure of this tiny planet. A giant core has been left behind, the exposed interior of a planet that had much of its outer layer, its crust mantle, stripped away and lost to space in the aftermath of the collision. This collision not only transformed the physical characteristics of the planet, but also knocked Mercury further inwards on a lopsided trajectory that we see reflected in the most elliptical orbit of all the planets. Although we cannot be certain of these events, it's a brilliant piece of scientific deduction to use the evidence we have to create a plausible scenario of events that happened unimaginably long ago. Events that drove the first rock from the Sun from a position full of potential to a place much too close to the Sun to support any form of life. An opportunity lost. After 4 years of observation and its brilliant discovery of Mercury's ancient past, Messenger finally ran out of fuel on the 30th of April 2015 and added yet another crater to this tortured world that once held such promise. Shrouded in an unbroken blanket of cloud, the next rock from the Sun tells a very different story. Over 50 million kilometers beyond Mercury lies a world that at first sight has the potential to be far more Earth-like than her scorched inner companion. Venus is perhaps the most mysterious of all the planets. Lying on the inner edge of the so-called habitable zone, this is a planet that holds its secrets close. For centuries, it has teased us with its brightness in the early morning and early evening sky. It's so bright because it's a large planet about the same size as the Earth. It's not too far away from us either, and the clouds that shroud it are highly reflective, reflecting 3/4 of the light that hits them. That's the frustrating but tantalizing thing about Venus, because even when you look at it through a big telescope, it is featureless. You never see the surface, which means that until the 1950s, scientists could only speculate about what lay beneath. In the late 19th and early 20th centuries, many thought that beneath her clouds Venus was hiding a mirror world to Earth. If not home to complex sentient life, then certainly hosting basic life forms. Faced with that impenetrable cloak, our collective imaginations fueled the idea of a living, breathing world beneath the clouds, a shroud that meant for the first half of the 20th century, we lived convinced that we were far from alone in the solar system. Nobel Prize-winning chemist Svante Arrhenius was one of the most renowned scientists to fuel the mythology of what lurked behind Venus's cover. Like many of the scientists of his era, Arrhenius let his curiosity wander into many different realms, including astronomy, and he hypothesized at length about the Venusian environment. Assuming the clouds of Venus were composed of water, he wrote in his book The Destinies of the Stars that a very great part of the surface of Venus is no doubt covered with swamps, creating an environment not unlike the tropical rainforests found here on Earth. Expanding on this picture, he suggested that the complete cloud cover of the planet created a uniformity totally unlike the extremes of weather that define different parts of the Earth. In Arrhenius's imagination, this stable environment, with a consistently uniform climate all over the planet, meant that any life on Venus lived without the evolutionary pressures of changing environments that drive natural selection here on Earth, leaving Venus in an evolutionary limbo akin to the Carboniferous period. Describing a world full of prehistoric swamps and dark forests, Arrhenius created the perfect canvas for science fiction writers of the time to conjure up a menagerie of curious life forms lurking beneath the clouds. Today, Arrhenius is far less known for his fertile imaginings on the wildlife of Venus than he is for his work on the climate of Earth. In 1896, he was the first scientist to use basic principles of chemistry to demonstrate the impact that the atmosphere can have, in particular levels of carbon dioxide, on the surface temperature, a process that was called the Arrhenius effect, but is now known as the greenhouse effect, an effect that would not only have profound consequences for our understanding of our impact on our own planet, but would also be vital in explaining the true nature of Venus beneath the clouds. By the 1920s, as ground-based technology improved, we stopped painting the surface of Venus with our imaginations and started filling in the gaps with facts. The first spectroscopic analysis of the planet's atmosphere suggested that it wasn't water or oxygen that filled the clouds of Venus, so some thought this hinted at an arid desert land beneath. Others speculated that formaldehyde filled the air, leading to the belief that Venus was not only a dead planet but a pickled one too. But come the 1950s, the true nature of Venus began to be revealed, as more accurate Earth-based observations suggested the presence of overwhelming levels of one defining gas in the Venusian atmosphere. This was not a planet shrouded in clouds of water and oxygen, nor pickled in formaldehyde. This was a planet engulfed in a blanket of carbon dioxide, and as Arrhenius had demonstrated on Earth, this almost certainly meant that whatever lay beneath the clouds, the heat would be beyond the limits of even the most resilient life forms on Earth. As the first spacecraft were being built to explore our sister world, it was becoming increasingly clear that visiting Venus would be far from easy, and she would be far from welcoming. In the early 1960s, the Soviet Union began a series of missions under the program name Venera, which attempted to explore the atmosphere and surface of Venus directly for the first time. The initial launches of the Venera program failed before they had even left Earth's orbit, but within a couple of years the program began to slowly see some success. Venera 1 was successfully launched on the 12th of February 1961. Designed as a flyby mission, it is thought to have passed within 100,000 kilometers of Venus, but a total telemetry failure on the craft meant that no data was returned to Earth. As far as we know, Venera 1 is still in orbit around the Sun to this day. Venera 3 attempted to go a step further, and was designed to enter the Venusian atmosphere to take the first direct measurements. However, on crossing the atmospheric boundary, the probe's systems failed, and no data was returned as it plummeted towards the ground. All that was left for Venera 3 was the historic position as the first human-built object to crash into another planet's surface. Despite multiple failures, the Soviets didn't give up, and in October 1967, Venera 4 entered the atmosphere of Venus and sent back data supporting the Earth-based observations, revealing for the first time that the blanket of clouds surrounding Venus was made up of primarily carbon dioxide, 90 to 95%, 3% nitrogen, and just trace amounts of oxygen and water vapor. Venera 4 confirmed beyond all doubt that this was no second Earth. As it descended through the thick clouds, the temperature rose to 262 degrees Celsius. The atmospheric pressure increased to 22 standard atmospheres, 2,200 kPa, and this was still 26 kilometers above the surface. As Venera 4 parachuted its way down to the surface, it provided data to Earth while confirming its own imminent death. This was a spacecraft that was not designed to survive the intense pressures and temperatures it was measuring, let alone the lack of the water landing it was designed for. The craft failed during the descent and was lost long before it reached the surface. Gradually, through the following missions, the Soviet scientists began to overcome each and every challenge Venus put in front of them. Venera 7 was built to survive the most violent of landings, and even though its parachute failed, it made it to the surface intact in 1970 and was able to use its damaged antennae to transmit limited temperature data for 23 minutes before it expired. Venera 9 not only made it to the surface and operated for 53 minutes in October 1975, but was also the first craft to successfully deploy its camera on the ground and transmit an image back to Earth. In the first ever picture taken from the surface of another planet, the black and white fractured image revealed a rocky, desolate landscape, with measurements confirming it to be a blistering 485 degrees Celsius, with an atmospheric pressure of 90 atm crashing down. By the time Venera 13 launched on the 30th of October 1981, the ambition of the missions and the confidence in delivering data from the surface had been radically transformed. Venera 13 functioned for 127 minutes in recorded temperatures of 457 degrees Celsius and a pressure of 89 Earth atmospheres. The probe's cameras deployed, taking the first color image from the surface of Venus. Spring-loaded arms measured the compressibility of the soil, while a mechanical drill arm took a sample of the Venusian surface that was analyzed by an onboard spectrometer. If that wasn't enough, onboard microphones were deployed to record the vicious winds that were assumed to be whipping the surface of Venus, the first ever recording of the sound of another planet. As the Venera missions came to a close in 1983, not even the smallest doubt remained of Venus's hostility. Far from the benign water world we had once imagined, the reality was that this was not a sister we recognized. In our search of the heavens for a place like home, we'd found a toxic, fiery hellscape. Venus is an enigmatic world, almost Earth-like in size, position, and potential, and yet as far from paradise as it's possible to imagine. If Mercury's story is one of catastrophic orbital change, and Earth's of balance and stability, the story of Venus is a tragedy, a tale of subtle yet relentless decline. So why did it all go wrong for Venus? Why did a world born with such similarities to the Earth take such a different path? To answer that, we need to look beyond the tortured planet we see today and go back to a time when Venus was a young, thriving planet. 4 billion years ago, Venus was a familiar world, a world created from the same dust as the Earth, born just about the same size, and settled into an orbit that seemed just far enough away from the glare of the sun to allow a precious process to begin to take hold. In almost every conceivable way, Venus's early life mirrored that of our own world. As its newly formed crust settled and cooled from the violent heat of its birth, an atmosphere began to grow around the young planet, fed by gases bubbling up from the molten rock below its surface, as well as captured from the clouds of gas and dust it swept through on its orbit around the sun. Clinging to the young Venus, this thin layer of gas would have certainly contained nitrogen, oxygen, and carbon dioxide. But most intriguing of all, we are certain it would have also contained large amounts of water vapor. High in the Venusian atmosphere, this water vapor eventually cooled enough to change state from vapor to liquid. And with that transformation, a process began that perhaps for the first time on any of the planets would have seen the conditions become just right for droplets of liquid water to take shape and begin falling from the Venusian sky. These were the first rains of the solar system, showering down onto the dry plains of Venus. Gradually these rains would have not just fallen but flooded the surface. Rivers would have flowed, and shallow oceans taken hold of large swathes of the planet's surface. Venus, perhaps before even the Earth, became a water world, a planet with skies full of clouds and a surface full of oceans, feeding the cycle of water around this young planet. How can we be certain this blue version of Venus existed? Unlike Mars, where we can see the evidence of its watery past etched onto its surface, we have no such direct evidence of the presence of liquid water on the surface of Venus. The only physical evidence we have that suggests the planet's watery past comes from measurements taken by NASA's Pioneer Venus spacecraft back in 1978. One of its most surprising discoveries revealed an unexpected amount of deuterium, heavy water, in the atmosphere compared with hydrogen. This DH ratio is far smaller on Venus than it is on Earth, and that's interesting because when the two planets formed, the ratio would have almost certainly been the same. Because hydrogen is far more easily lost from an atmosphere than deuterium, this smaller ratio suggests that Venus has lost a lot more water than the Earth over its lifetime, the signature of a long-lost primordial ocean, as cosmochemist Larry Nittler explains. Scientists believe that Venus once had a lot of water in its oceans, but lost it over time, and perhaps in oceans as recently as 1 billion years ago. The reason we can tell this is from the isotopic composition of hydrogen measured in its atmosphere by spacecraft. Now, hydrogen has 2 flavors of isotopes. Whereas most hydrogen atoms are just a single proton in the nucleus, some, a small fraction, are what we call deuterium, that have a proton and a neutron, so they weigh twice as much as the regular hydrogen. What happens when you have evaporation of water from a planet, or the atmosphere, is that the water molecules that contain hydrogen are much lighter than the water molecules that contain deuterium, so they evaporate more easily and can be lost more easily. So over time, as you evaporate water, deuterium-bearing molecules stay behind relatively to the regular ones, and you build up a deuterium to hydrogen ratio. And by back-calculating from the measured ratio today, we can figure out how much water has been lost over the billions of years of evolution, and on Venus, it's quite a lot. None of this is solid proof, but it does begin to point us in one direction, and with no further exploration of the surface, we've had to rely on an accumulation of indirect evidence to begin to paint a more detailed picture of Venus's watery past. As with almost all of our understanding of the planets, the evidence that built this picture has been accumulated through decades of exploration. Starting with the Venera mission's first touchdown on the planet, to the Pioneer Venus orbiter, and to the more recent Magellan mission, which not only relayed extraordinary radar soundings of the surface of Venus, but provided the first full topographical map of the planet collated over a period of 4 years in orbit. Combining all of the data that has been accumulated over decades of exploration has allowed us to peer deep into the planet's past, using the same tools that enable us to model the future of climate change here on Earth, to create climate models of Venus in the past, present, and future. The results of this analysis, conducted most recently by a team from NASA's Goddard Institute for Space Studies, GISS, all point to the same conclusion. In the distant past, Venus was a planet covered in shallow, primordial oceans. Some estimates suggest that this water world was far from fleeting, a blue planet just like our own that could have been sustained for around 2 billion years, and perhaps only disappeared some 700 million years ago. It's a tantalizing thought that such a similar world to our own existed for so long with liquid water on its surface. We know life took hold quickly on our own blue planet, within 500 million years of the Earth being formed. So there seems good reason to suspect that if Venus really was as wet as the models predict, it too could have sprung into life. Exactly what went on in the long-lost rivers and oceans of Venus is yet to be discovered. Hidden behind the clouds, we have not yet been back to search for any signs that life ever took hold here. Our exploratory attentions have turned to Mars, as a planet that not only has a fertile past, but is also a possible target for human colonization in the future. We know for certain that no life, at least no life we understand, could exist on Venus today, And perhaps even the evidence of any biology on that long-lost water world has long ago vanished under the oppressive heat, rampant volcanism, and extreme pressures of the planet today. The history of science is littered with crunching moments of conflict, debates, and disagreements that divided opinion in the most passionate of battles. The wonderful thing about science, however, is that the debates can be settled when facts become available. Science and conservative common sense famously clashed in 1860 when Thomas Huxley and Samuel Wilberforce fulminated over the new theory of evolution published by Darwin 7 months earlier. I imagine Wilberforce's indignant, reddening cheeks shaking with righteous outrage as he denied the repugnant possibility that his grandfather was a monkey. None of his relatives was a chimpanzee, by the way. We simply share a common ancestor with them around 6 or 7 million years ago. But the unctuous, oleaginous, and saponaceous bishop, as Disraeli once called him, was having none of it. This might be a little unfair to the great Victorian orator and Bishop of the Church of England, but in the case of evolution, he was firmly on the wrong side of reality. Few great leaps in knowledge occur without dividing opinion, and this is entirely appropriate. Extraordinary claims require extraordinary evidence, and the great scientific discoveries we are celebrating here are utterly extraordinary. The trick, as an educated citizen of the 21st century, is to realize that nature is far stranger and more wonderful than human imagination, and the only appropriate response to new discoveries is to enjoy one's inevitable discomfort, take delight in being shown to be wrong, and learn something as a result. The world of astronomy had its moment of intellectual sumo in what has become known as the Great Debate. The year was 1920, and two eminent astronomers found themselves stuck on a train together, travelling the 4,000 kilometres from California to Washington to discuss the greatest cosmological question of the day. The younger of the two men, Harlow Shapley, we have already met. He had just published his data suggesting that the Milky Way galaxy was much larger than previously suspected. This, however, was where he believed the universe stopped. Shapley was convinced our galaxy was the beginning and end of the cosmos. His travelling companion thought otherwise. Heber Curtis had been studying a misty patch of light known as the Andromeda Nebula. He was convinced that this was not part of our galaxy, but a separate island universe of billions of other stars. It's not known what they discussed on the train, but the debate itself took place at the Smithsonian Museum of Natural History throughout the day and night of the 26th of April. At stake was the scale of the universe itself, and both men knew that the question would ultimately be settled by evidence rather than debating skills. The human race had already been shunted from the centre of the universe by Copernicus, and now faced the possibility that the Milky Way galaxy itself was part of a multitude, stretching across millions of light-years of space. The question wasn't settled that evening, but the experienced Curtis, perceived as the underdog because of the magnitude of what he was suggesting, landed significant blows. Curtis observed that the Andromeda Nebula contains a number of novae, exploding stars that shine temporarily but brightly in the night sky. But he also noted that the novae in Andromeda appeared on average to be 10 times fainter than any others. Curtis asserted that Andromeda's novae appear dimmer simply because they are perhaps 500,000 light-years further away than those in the Milky Way. Andromeda is therefore another galaxy, claimed Curtis, which strongly implied that the other so-called nebulae were other galaxies too. This was the very definition of an extraordinary claim, and the extraordinary evidence came only 4 years later. In 1923, a photo of Andromeda, taken by a 33-year-old astronomer called Edwin Hubble, further fueled the great debate. It's only a photograph, but just like Anders' Earthrise, it belongs to a rarefied group of images that have transformed our perspective. Aside from their scientific merit, such images assume great cultural significance because of the ideas they generate and the philosophical and ideological challenges they pose. They also carry with them, in the shadows, personal stories. Someone would have taken a photograph of Andromeda someday and discovered what Hubble did, but Hubble took this one, and his story therefore becomes inextricably intertwined with it. Some don't like their history presented in this way, but science is richer when its stories include people as well as ideas. Curiosity is, after all, a human virtue. Hubble may never have taken the photograph had he followed through on a promise to his father to practice law. Reading jurisprudence at Queen's College, Oxford, as one of the first Rhodes Scholars, Hubble aimed to fulfill his father's wishes, but John Hubble died before Edwin finished his degree. The death of his father encouraged Edwin to ditch law and revisit his childhood passion for astronomy. He left Oxford for the University of Chicago, joined the Yerkes Observatory, and received his PhD in 1917 with a thesis entitled Photographic Investigations of Faint Nebulae. After brief service in the US Army at the end of World War I, Hubble obtained a position at the Mount Wilson Observatory. He found himself at the controls of the largest, most powerful telescope on the planet, and with the knowledge and good sense to point it at the most intriguing and controversial object in the night sky, Andromeda. Just like Curtis before him, Hubble could make out distinct features within the misty patch, but the newly commissioned 100-inch Hooker telescope allowed him to see much more detail. On the 5th of October 1923, he took a 45-minute exposure, found 3 unidentified specks that he assumed were new novae, and marked them all with an N. To confirm his findings, Hubble needed to compare this plate with previous images of Andromeda taken at Mount Wilson. The following day, he made the journey down to the basement archive where the observatory's collection of images was catalogued and stored. To Hubble's delight, 2 of the specks were indeed newly discovered novae, what we now know to be the bright nuclear flares of white dwarf stars as they accrete gas and dust from a nearby companion. But it was the 3rd speck that he found most interesting when he compared it to previous images. As Hubble scanned back through the Mount Wilson catalogue, he discovered that the star had been captured before. In some plates it appeared brighter, whereas in others it appeared dim or not present at all. Hubble immediately grasped the importance of his discovery. The 3rd speck was a Cepheid variable, the type of star Henrietta Leavitt had studied 2 decades earlier. In one of the most famous corrections in scientific history, Hubble crossed out the letter N and replaced it in red ink with the letters VAR, followed by a very understated exclamation mark. Hubble had discovered a cosmic yardstick in Andromeda, and it was a trivial matter to calculate the distance. The new star varied with a period of 31.415 days, which, following Leavitt, implied its intrinsic brightness was 7,000 times that of our Sun. And yet it appeared so dim in the night sky that it was invisible to all but the most powerful of telescopes. Hubble's initial calculations revealed that the star was over 900,000 light-years away from Earth, a staggering distance when the size of our own galaxy was estimated to be no more than 100,000 light-years across. Hubble, with the help of Leavitt's ruler, laid the great debate to rest. Andromeda, the distant patch of light in the night sky, is a galaxy, an island, according to current estimates, of 1 trillion suns. Current measurements put the giant spiral at a distance of 2.5 million light-years from the Milky Way, one of around 54 galaxies gravitationally bound together to form our galactic neighborhood known as the local group.
In the daytime, our universe stretches only as far as the horizon. The sun hides in plain sight because it's too bright for us to see it directly. Only rarely do we glimpse a watercolor moon. Unless we think hard, our intellects are confined to the surface of the Earth. After sunset, beyond cities, the universe appears, a destination for the imagination, albeit separated by a seemingly unbridgeable gulf. This may be true for the stars, but it is not so for the planets. There are times when Mars, Venus, Jupiter, and Saturn dominate the sky, bright lights that shift position nightly against the fixed stars, commanding our attention even if we aren't certain what we're looking at. The distances are still vast by terrestrial standards, but despite appearances, the gulf is certainly not unbridgeable, because we have visited all of these planets, and taken our first steps into the outer reaches of the solar system beyond. And yet the wandering lights in the dark still feel detached from human affairs, and the time and effort we've spent in visiting them might seem to be an indulgence. This assumption, however, is profoundly wrong. The solar system is a system. The Sun and the 8 major planets and countless billions of minor planets, moons, asteroids, comets, and unclassified lumps of ice and rock were formed back in the mists of time, and they continue to evolve as one. We rarely notice the dynamic, interconnected nature of our system, although asteroid strikes on our planet are not such a rare occurrence. The Chelyabinsk impact in February 2013 injured 1,500 people when a 12,000-ton asteroid broke up as it entered the Earth's atmosphere at 60 times the speed of sound. And the Tunguska airburst in Siberia in 1908 flattened 800 square miles of forest in an explosion comparable to that of the most powerful hydrogen bomb ever tested. The surface of the Moon bears testament to a record of violence and destruction from the skies that the Earth has also endured, but the relentless erasure of craters by weathering, and our good fortune that no major impacts have occurred in recorded human history, are the reason for our misplaced sense of isolation from the heavens. The interdependent nature of the solar system has become more evident as we've begun to understand its history. It's tempting to imagine that the physical layout of the planets is a fossilized remnant of primordial patterns in the collapsing dust cloud around the newly ignited Sun 4.6 billion years ago. But our exploration of the planets, coupled with increasingly powerful computer simulations of the evolution of the solar system, has revealed that this is not the case. Planetary orbits are prone to instability, particularly so in the early, more chaotic years when our solar system was young. The details of precisely how the planetary orbits have shifted are still uncertain, but we now suspect that Mercury, the innermost planet, began life much further out and was deflected inwards to its present-day seared orbit. Jupiter and Saturn may have drifted inwards shortly after their formation, before reversing their course and retreating, but not before affecting the distribution of material out of which Mars and Earth would later form. Around the time that life began on Earth, Neptune and Uranus may have been flung outwards, disrupting the orbits of billions of smaller objects far from the Sun. The record of this time of unprecedented violence, known as the Late Heavy Bombardment, is written across the scarred surface of the Moon, itself most likely formed in a glancing interplanetary collision between Earth and a Mars-sized planet 4.5 billion years ago. The planets are like snowflakes. The detail of their structure, their composition, size, spin, and climate are a frozen record of their past. An understanding of the planets beyond Earth is therefore a prerequisite for understanding our home world, and that, in turn, is a prerequisite for understanding ourselves. Earth is unique in the solar system because it's a planet with a complex ecosystem. The genesis and subsequent 4 billion year evolution of life on Earth required planetary characteristics which are necessarily linked to the evolution of the system as a whole. There had to be liquid water on the surface, and much of this water was delivered after the Earth's formation by icy, water-rich asteroids and comets, possibly deflected inwards from the outer solar system by Jupiter. These rivers, seas, and lakes of extraterrestrial origin had to persist for the best part of 4 billion years, which required a stable atmosphere to maintain surface temperatures and pressures within a limited range. 4 billion years is a long time, around a third of the age of the universe. The Sun has brightened by 25% since the Earth formed, which makes the stability of our environment all the more difficult to understand. In a chaotic system of planets around an evolving star, a planet with life-supporting properties and the remarkable stability enjoyed by Earth over billions of years may be extremely unusual. The study of our sister worlds, Mars and Venus, has proved instructive in understanding just how fortunate we may have been and how delicate our position today might be. 4 billion years ago, as life began on Earth, Mars was also Earth-like. It had oceans and rivers, an active geology and complex surface chemistry, the ingredients of life. One of the primary goals of the fleet of spacecraft currently in orbit around and exploring the surface of Mars is to search for evidence of past or even present life, and to understand why the red planet was transformed from a potential Eden at the dawn of the solar system to the frigid desert world we observe today. The story is complex, but one of the most important differences between the two worlds is size. Mars is just 1/10 the mass of Earth, too small to hang on to its internal heat, its protective magnetic field, and its atmosphere for much more than 1 billion years after its formation. Yet Mars formed in a similar region of the solar system to Earth and Venus, so why is it so small? The answer may lie in the fast-changing orbits of Jupiter and Saturn early in the solar system's history. These surprising findings will be explored later in this book. The history of Venus is perhaps even more puzzling, in part because of the immense difficulty of exploring the planet. Venus is often described as a vision of hell. Surface temperatures are high enough to melt lead, and the atmospheric pressure is 90 times that on Earth. Sulfuric acid raindrops fall from its clouds. And yet, long ago, Venus too may have been Earth-like. Perhaps there were once Venusians, before a runaway greenhouse effect took hold, and began destroying Venus's temperate climate about 2.5 billion years ago, although this date is highly uncertain. Taken together, the stories of the 3 large terrestrial planets are salutary. If an alien astronomer observed our solar system from afar, they would classify Mars, Earth, and Venus as potentially living worlds, orbiting as they do inside the so-called habitable zone around the Sun, the region within which, if atmospheric conditions are right, liquid water can exist on the surface of the planets. All 3 worlds may once have been habitable, and all 3 worlds may once have harbored life, but now only Earth supports a complex ecosystem, let alone a civilization. Understanding why Mars and Venus diverged so significantly from Earth over the last 4 billion years will provide great insight into the fragility of worlds, and perhaps suggest whether our own good fortune is near impossible to comprehend or merely outrageous. Planets change. Ours could change at any moment. A stray comet from the frozen Kuiper belt beyond the orbit of Neptune could put an end to our story. We could also put an end to ourselves. The study of Venus might help us avoid one of the world planets we could destroy ourselves, because it shows us what greenhouse gases are to avoid. I think one of the reasons why anthropogenic climate change is so difficult for certain planets is that the atmosphere and incapable of trapping enough heat to modify the temperature of those people might get where they will squash and boil and dissolve on the surface of the planet. The explanation of the process if we want to know how we came to be, we need to understand the histories of the planet. Should be our primary concern. That may be so, but I argue that a deeper understanding of the evolution of the planets is essential for our continued prosperity and existence on this one. The threat of catastrophic climate change is an obvious example, but there are many other reasons why knowledge is important. There is feedback in human affairs. Our collective state of mind affects the decisions we make. To confine our imaginations to the surface of the Earth is to ignore both our immense good fortune and the fragility of our position. A wider knowledge of both will, I believe, help secure a safer and more prosperous future. Earth sits a mere 150 million kilometers from the Sun. Not too hot, not too cold, with surface temperatures ranging from -88 to +58 degrees Celsius. This Goldilocks location has created a stability of climate that, despite the best efforts of ice ages and impacts, has allowed life to maintain an unbroken chain for nearly 4 billion years. And yet we know for certain that it cannot last. Our Sun, like every star in the universe, is far from static. Stars have life cycles of their own, and eventually the hydrogen fuel that powers the nuclear reactions within a star will begin to run out, and the star will enter the final phases of its lifetime. It will expand, cool, and change color to become a red giant. Small stars, like our Sun, will undergo a relatively peaceful and beautiful death, which will see it pass through a planetary nebula phase to become a white dwarf, which will cool down over time to leave a brown dwarf. Life on Earth has prospered through our Sun's middle years, but these optimum conditions are waning. At first the changes will be invisible, but 1 billion years from now they will be obvious to any life forms left on the planet. An immense sun filling the sky will warm and transform itself and the Earth that it shines upon. The Sun is both the giver and the taker of life on our planet. It is one of the great paradoxes of the universe that as the life of a star like ours begins to wane, its size and luminosity will increase. A rise in luminosity of just 10% will see the average surface temperature on Earth rise to 47 degrees Celsius instead of the 15 degrees Celsius that it is today. The effect of this rise in temperature manifests in a lifting of vast amounts of water vapor from the oceans into the atmosphere, creating a greenhouse effect that could quickly and rapidly run out of control, evaporating the oceans and sending the surface temperature skyrocketing. Astrobiologist David Grinspoon explains. The greenhouse effect is the name we give to the physical process by which planets heat up through the interaction of their atmospheres and solar radiation. Basically, solar radiation comes in what we call the visible wavelengths. Primarily, they're wavelengths that we can see, and most atmospheric gases are very transparent to visible radiation. So light from the Sun comes through pretty much unimpeded by an atmosphere and reaches the surface of a planet. Then the surface of the planet re-radiates that radiation in infrared, because planets are much cooler than the Sun. And that means they radiate at much longer wavelengths, what we call infrared or heat radiation. That infrared radiation doesn't make it through an atmosphere so easily. Some of the atmospheric gases, the ones we call greenhouse gases, block infrared radiation, and so therefore the more of those greenhouse gases that are in a planet's atmosphere, the harder it is for that surface radiation to make it back out into space, and the more that planet will heat up. Estimates of the timescale that will see our oceans disappear vary massively, and are heavily influenced by a multitude of factors. But few are in doubt that by the time our planet reaches its 8 billionth birthday, in 3.5 billion years' time, the end will be in sight. With temperatures heading above 1,000 degrees, life will have long disappeared from a surface that is beginning to melt under the burning sun. Moving even further into the future, the outlook becomes bleaker. As the Sun enters old age, it will grow into a red giant, engulfing the Earth within its expanding atmosphere. Moonless, lifeless, and perhaps reduced to its inner core, our planet and the civilizations it once harbored will be nothing but a distant memory, etched in the atoms that made us all, as they are dispersed amongst the cosmos. For planet Earth, the clock is ticking, and time is slowly running out. But ours is far from the only world to enjoy its moment in the sun. Across the history of our solar system, stretching deep into its ancient past and reaching far into its future, we see stories of worlds in a constant battle with our ever-changing star. Close in, Ancient worlds such as Mercury, which long ago lost their fight with the sun, are taunted by views of Earth and what might have been. Further out and even hotter, Venus circles, shrouded in a choking cloak of cloud, and even further beyond the Earth, Mars sits cold and barren. Beyond these planets, frozen worlds await, huddled in perpetual hibernation, anticipating the moment when the warmth of the sun reaches out far enough, with sufficient heat, to trigger a first spring. On that day, mountains of ice will melt, rivers of water will flow, and where there was once only bleakness, in the distant future on planets once frozen and lifeless, we might find a place that looks very much like home. The story of our solar system is not as we once thought it, eternal and unchanging. Instead, it is a place of endless transformation. It is a narrative that repeats itself with a predictable rhythm. As one world passes, another comes into the light. Only one planet has maintained stability for almost the entire life of the solar system. The Earth has remained habitable for at least 4 billion years, while change has played out all around it. What makes the Earth so lucky compared to all of its terrestrial siblings? To answer that question, we need to look not just at our planet, but at the whole of the solar system, going right back to the very beginning. For the first few million years after its birth, there were no terrestrial worlds to see the sun rise, and there were no days, no nights, no circular tracks around it. Instead, surrounding our infant star was a vast cloud of dust and gas. A tiny fraction of the material left over from the sun's formation. This swirling cloud would one day coalesce to form the various planets of the solar system, and many other smaller bodies. But at this time, 4.7 billion years ago, there was nothing but tiny specks of dust reflecting back the light of our slowly growing star. Only time, vast amounts of empty time, would allow enough of this gas and dust to catch and cluster, randomly forming the smallest of seeds. Most of these seeds would hardly get the chance to grow at all, smashed apart and returned to the immense swirl of dust from whence they arose. Just a few would grow big enough and survive long enough to capture and condense more of the cloud, slowly increasing their mass and density. We still do not fully understand the process by which grains of dust no thicker than a human hair can amass to become rocky objects the size of a car, and as yet no model exists to explain this part of the evolution of a planet. But what we do know is that once that disk of gas and dust becomes populated with clumps of rock that make it past the meter-sized barrier, a powerful force comes into play to propel the process forward. These newly formed planetesimals are big enough to allow the great sculpting force of gravity to draw the clumps together, growing to sizes of over a kilometer in length. Swirling around the sun, thousands upon thousands of these objects live and die, colliding and coalescing under the increasing gravitational forces of attraction, until eventually just a few emerge as planetary embryos, moon-sized bodies known as protoplanets. In the last violent stages of the process of planetary birth, these protoplanets swirl around in crowded orbits, and many are destroyed, returned to the dust of their origins. But occasionally, when a collision brings two or more of these giant objects together, the size of this mass of rock becomes big enough for gravity to pull it in from all sides, creating a sphere of newly formed rock, a new world. In that moment, a planet is born. Each of the terrestrial planets in our solar system was born this way. They are the survivors of a process that destroys far more worlds than it ever creates, and which left just 4 rocky planets remaining, starting closest to the Sun with Mercury, then Venus, Earth, and finally, farthest out, the cold and dead world of Mars. Today, these 4 worlds all look vastly different. and yet all were created the same way, made up of the same ingredients and orbiting the same star. So why have they ended up so distinct from each other, and with such starkly different environments? And what makes this place, the Earth, so unique, the only one of the rocks that has blossomed with life? To understand, we have to look deep into the past of our solar system, to explore the unique history of each of the planets by means of amazing feats of human engineering across billions of miles, and into environments of unknown and unimaginable extremes. Getting to the smallest planet in the solar system is anything but easy. Skirting past the Sun at a distance of just 46 million kilometers at the closest point in its orbit, Mercury is a planet that is not only held deep in the gravitational grip of our massive star, but is also moving at an average orbital speed of 48 kilometers per second, by far the fastest orbiting planet in the solar system, and far outpacing the Earth's more leisurely 30 kilometers per second. It needs to whip around this quickly, otherwise it would have fallen into the Sun's embrace long ago. But the combination of its speed and position make it a planet that's immensely difficult to get close to, and even harder to get into orbit around. In order to do so, you have to travel fast enough to catch up with Mercury, but not so fast that you cannot somehow slow down to prevent a headlong descent into the Sun. And that challenge has meant that until relatively recently, it was the least explored of all the terrestrial planets. For many decades, our first and only close-up glimpse of the innermost rock orbiting the Sun came from the Mariner 10 spacecraft, when on 3 separate occasions in 1974 and 1975, it briefly flew past Mercury. This was the first spacecraft to use another planet to slingshot itself into a different flight path, using a flyby of Venus to bend its trajectory, to allow it to enter an orbit that would bring it near enough to Mercury to photograph it close up. Clad in protection to ensure it could survive the intense solar radiation and immense extremes of temperature, Mariner 10 was able to send back the first detailed images of Mercury as it flew past at just over 200 miles above its surface. It passed by the same sunlit side of Mercury each time, so it was only able to map 40 to 45% of Mercury's surface. The spacecraft took over 2,800 photos, which gave us never-before-seen views of the planet's cratered moon-like surface, a surface that we had never previously been able to fully resolve through Earth-based observation. Despite the beauty of the pictures taken, it wasn't the images from Mariner 10 that really surprised us. It was the data the probe collected relating to Mercury's geology, which pointed to a much more surprising history of the planet than had previously been imagined. Mercury, it seemed, was far from being just a scorched husk. Mariner was able to sense the remains of an atmosphere, consisting primarily of helium, as well as a magnetic field and a large iron-rich core, opening a mystery that would remain unexplored for another 30 years. As it flew past Mercury for the last time on the 16th of March 1975, the transmitters were switched off and its contact with Earth silenced. Mission completed, Mariner 10 began a lonely orbit of the Sun that, as far as we know, continues to this day. At first sight, many things about Mercury simply don't make sense. During its 88-day orbit around the Sun, it travels in a lopsided elliptical orbit, which means it can be as far away from the Sun as 70 million kilometers, but occasionally as close as 46 million kilometers. This is by far the most irregular of orbits of all the planets, but it is not the end of Mercury's oddity. Temperatures at midday can rise to 430 degrees Celsius on the surface, but at night, because it's a small planet and it has no atmosphere, temperatures fall to minus 170 degrees, giving it the greatest temperature swing of any known body in the solar system. Its rotation is also unusual, gravitationally locked to the Sun in what is known as a 3-to-2 spin-orbital resonance. This means the planet spins precisely 3 times on its axis for every 2 orbits, which in turn means that its day is twice as long as its year. In effect, you could be travelling over its surface at walking pace and keep the sun at the same point in the sky as you strolled through eternal twilight. As planetary scientist Nancy Chabot explains, a day on Mercury is not like a day on Earth. It has a very unusual orbit. It has to go around the sun twice to have one complete solar day on the planet, where the sun goes from directly overhead to directly overhead. And this actually takes 176 Earth days. Because of the planet's orbit, there are places on the Mercurian surface where a hypothetical observer would be able to see the 2.5 times larger in the sky sun appear to rise and set twice during one Mercurian day. It rises, then arcs across the sky, stops, moves back towards the rising horizon, stops again, and finally restarts its journey towards the setting horizon. Most of Mercury's anomalies can be explained by the orbital mechanics of its journey around the Sun, except, that is, for the odd elliptical orbit that takes it on such an oval-shaped, elongated course. This irregularity has puzzled astronomers for centuries, and hints at an ancient planet that was very different from the Mercury we see today. To truly begin to understand Mercury's history, we had to wait nearly 40 years before we could return to her. On the 18th of March 2011, NASA's Messenger spacecraft became the first to enter Mercury's orbit. And over the next 4 years, it succeeded in not only photographing 100% of the planet's surface, but also collecting extensive data on its geology. But before any of this could happen, Messenger had to take perhaps the most circuitous route in the history of our exploration of the solar system. Just passing close to Mercury to take a few snaps, as Mariner 10 did, is hard enough. But actually entering into its orbit was thought to be either too difficult to achieve or too costly to execute, as cosmochemist on the Messenger mission Larry Nittler explained. There are two major challenges to getting a spacecraft into orbit around Mercury: gravity and money. When you go from Earth to Mercury, you're falling into the gravitational well of the Sun, which makes you accelerate faster and faster as you get closer. And if you were to go straight from Earth to Mercury, this means that you would basically just zip right by the planet, or you would need to bring an incredible amount of fuel to put the brakes on, more than you could actually afford. A number of missions never made it further than pencil and paper, while others floundered and failed at the proposal stage. It was only when Chen-Wan Yen, a NASA engineer from the Jet Propulsion Laboratory, JPL, provided a trajectory that could not only get a craft into orbit, but could do it at an estimated bargain bucket cost of $280 million, that the Messenger mission could really begin to take flight. Taking off from Cape Canaveral on the 3rd of August 2004, Messenger began a 6-year, 7-month, 16-day journey to Mercury that would take it on a 7.9 billion kilometre trajectory before it entered into orbit around the smallest of all the planets. To arrive at Mercury with the right speed and on the right course would require a complex route that would entail a number of gravity-assist maneuvers around the Earth, Venus, and Mercury itself to reduce the speed of the craft relative to Mercury. So, combined with the brief firing of its large rocket engine to finally insert it into orbit, this mission profile allowed Messenger to complete its voyage without the need to carry the vast reserves of fuel required to slow its passage through the firing of rockets. This design made the craft lighter and cheaper, but ultimately much slower. Almost 7 years was a long time to wait for the team patiently charting its progress across the stars. Larry Nittler described Messenger's course as sneaking up on Mercury by taking a 7-year journey, flying around the Sun many times, doing multiple flybys around Mercury and Venus, and each time transferring some of the craft's speed and energy to the planet, so it could slow down, so that when we finally got to Mercury after 7 years, we were able to fire our engine just a little bit to slow down even more and get captured by the weak gravitational field of the planet. Appropriately, when Messenger finally entered into Mercury's orbit at 0045 UTC on the 18th of March 2011, the path it settled into was highly elliptical. This orbit took it on a 12-hourly cycle from 200 kilometers above the planet's surface to 10,000 kilometers away from it. It may seem like an odd orbit for a craft with the singular aim of getting as close to Mercury as possible, but this was an essential part of the design of the mission, vital to protect Messenger from the fierce heat radiated by the scorching hot surface of Mercury. The sunlight reflected from the surface is so powerful, it would have literally melted the solder holding the spacecraft together if it wasn't given time to cool down between its closest approaches to the planet. Protected by an enormous ceramic solar shield and its eccentric orbit, Messenger could begin its work. For 2 years, the spacecraft mapped pretty much every bit of the surface of Mercury, and the images beamed back to Earth revealed a planet that's been in the firing line for billions of years. Too small to hold on to an atmosphere that might protect it from meteorites, and lacking any processes to recycle old terrain, Mercury's ancient surface is the most cratered place in the solar system.
1968 was a difficult year on planet Earth. The Vietnam War, the bloodiest of Cold War proxy tussles, was at its height, ultimately claiming over 3 million lives. Martin Luther King Jr. was assassinated in Memphis, prompting presidential hopeful Bobby Kennedy to ask the people of the United States to tame the savageness of man and make gentle the life of this world. Kennedy himself was assassinated before the year was out. Elsewhere, Russian tanks rolled into Prague, and France teetered on the edge of revolution. As I approached my first Christmas, my parents could have been forgiven for wondering what kind of world their son would inhabit in 1969. And then, as Christmas Eve drifted into Christmas morning, an unexpected snowfall decorated Oakbank Avenue, and Borman, Lovell and Anders, 400,000 kilometers away, saved 1968. Apollo 8 was, in the eyes of many, the moon mission that had the most profound historical impact. It was a terrific, noble risk, a magnificent roll of the dice, a distillation of all that is great about exploration, a tribute to the sheer balls of the astronauts and engineers who decided that, come what may, they would honor President Kennedy's pledge to send a giant rocket more than 300 feet tall, the length of this football field, made of new metal alloys, some of which have not been invented, capable of standing heat and stresses several times more than have ever been experienced, fitted together with a precision better than the finest watch, carrying all the equipment needed for propulsion, guidance, control, communications, food, and survival on an untried mission to an unknown celestial body, and then return it safely to Earth, re-entering the atmosphere at speeds of over 40,000 kilometers per hour, causing heat about half that of the temperature of the sun, almost as hot as it is here today, and do all this, and do it right, and do it first, before this decade is out. If I heard that from a leader today, I'd be first on the rocket. Instead, I have to listen to vacuous diatribes about fairness, hard-working families, and how we're all in it together. Sod that, I want to go to Mars. To set Apollo 8 in context, Apollo 7, the first manned test flight of the Apollo program, was flown by Schirra, Isola and Cunningham in October 1968. Apollo 8 was supposed to be a December test flight for the lunar lander, conducted in the familiar surroundings of Earth orbit, but delivery delays meant that it was not ready for flight, and the aim of meeting Kennedy's deadline looked to be dead. But this wasn't the 21st century, it was the 1960s, and NASA was run by engineers. The program manager was George Low, an Army veteran and an aeronautical engineer who knew the spacecraft inside out and had the strength of character to make decisions. Why not send Apollo 8 directly to the moon without the lunar lander, proposed Low, allowing Apollo 9 to test fly the LEM, Lunar Excursion Module, in Earth orbit in early 1969 when it became available, and pave the way for a landing before the decade was out. Virtually every engineer at NASA is said to have agreed, and so it was that only the second manned flight of the Apollo spacecraft lifted off from Kennedy on the 21st of December, 10 short weeks after Apollo 7, bound for the moon. The crew later said that they estimated their chance of succeeding to be 50-50. Precisely 69 hours, 8 minutes and 16 seconds after launch, the command module's engine fired to slow the spacecraft down and allow it to be captured by the moon's gravity, putting the 3 astronauts into lunar orbit. Newton's almost 300-year-old equations were used to calculate the trajectory. This was a spectacular, practically unbelievable engineering triumph. Less than a decade after Yuri Gagarin became the first human to orbit the Earth, 3 astronauts traveled all the way to the moon. But the mission's powerful and enduring cultural legacy rests largely on 2 very human actions by the crew. One was the famous and moving Christmas broadcast, the most watched television event in history at that time, when distant explorers read the first lines from the book of Genesis. "We are now approaching lunar sunrise, and for all the people back on Earth, the crew of Apollo 8 has a message that we would like to send to you," began Anders. "In the beginning, God created the heaven and the earth was without form and void, and darkness was upon the face of the deep." Borman concluded with a sentence clearly spoken by a lonely man 400,000 kilometers from home. "And from the crew of Apollo 8, we close with good night, good luck, a Merry Christmas, and God bless all of you on the good Earth." The mission's most potent legacy, however, is NASA image AS8142383, snapped by Bill Anders on a Hasselblad 500 EL at f11 and a shutter speed of 1/250th of a second on Kodak Ektachrome film. It was, in other words, a very bright photograph. The image is better known as Earthrise. When viewed with the lunar surface at the bottom, Earth is tilted on its side with the South Pole to the left and the equator running top to bottom. Little landmass can be seen through the swirling clouds, but the bright sands of the Namib and Saharan deserts stand out salmon pink against the blackness beyond. Just 368 years and 10 months after a man was burned at the stake for dreaming of worlds without end, here is Earth, a fragile crescent suspended over an alien landscape, the negative of a waxing moon in the friendly skies of Earth. This is an unfamiliar planetary Earth, no longer central, just another world. When Kennedy spoke of Apollo as a journey to an unknown celestial body, he meant the moon. But we discovered Earth, and in the words of T.S. Eliot, came to know the place for the first time.
Today, Venus has the slowest rotation of any planet in the solar system, taking 243 Earth days to complete one rotation on its axis. This period is known as the sidereal day, which is different to a solar day, the time it takes for the Sun to return to the same point in the sky. On Earth, the sidereal day at 23 hours, 56 minutes and 4.1 seconds is very close to the solar day, which lasts pretty much exactly 24 hours. But on Venus, the difference between these two periods is much greater. Even though the planet takes 243 days to rotate on its axis when combined with its orbit, a solar day on Venus lasts for 116.75 Earth days. It means every day on Venus lasts almost 4 months on Earth. And not only that, but Venus also rotates from east to west, one of only 2 planets to do so, along with Uranus. So across this toxic world, a sunrise would last literally for days as it inches across the sky. This slow progression of the Sun in the Venusian sky, due to the planet's creeping rotation, has raised many questions about how in the past the planet would have been heated, and how the climate would have been affected by such a different rotation compared with the Earth's. Today, the climate of Venus is what is known as isothermal. There is a constant temperature between the day and night sides, and between the equator and the poles. This is because the thick atmosphere literally acts like a blanket, dissipating the heat of the sun, so that the only real variation in temperature on the Venusian surface occurs due to differences in altitude. In its past, however, this may have been very different. With a more Earth-like atmosphere, so the sun would have been beating down on the planet's surface for days on end. To make things even more complex, we know the spin of a planet is intimately linked to its climate, and we've got strong evidence to suggest that how fast a planet spins is directly related to its chance of habitability. Until very recently, it was assumed that the slow rotation of Venus must have been caused by the presence of a thick atmosphere early on in its history, that in effect acted as a brake on the planet's spin. However, recent studies now suggest that the planet could have had a thin atmosphere like that of modern Earth, and still have ended up with its slow rotation. Gradually, as we start to build a picture of ancient Venus, we begin to see beyond the cloud cover of today, through to an ancient planet with an Earth-like atmosphere, and a day lasting over 200 Earth days, as the sun beat down on the ocean-covered surface. To make sense of the climate of this Earth-like Venus, the team at the Goddard Institute needed to make another tweak, or postulation to be more precise, to the model. With the sun hitting the one side of the surface for so much longer than on the Earth, the evaporation rate of the oceans would be far greater and potentially incompatible with the water world we suspect existed. But by simply adjusting the amount of dry land on the surface of Venus, especially in the tropics, the effect is dramatic. With a higher percentage of land, the models suggest that even the slow rotation would not dry out the planet, and it could have held on to enough water to be ripe for supporting the emergence of life. By combining all of this data, the GIST team have painted our most up-to-date picture of early Venus, and it's a beguiling image. Within the infant solar system, it is a planet the size of Earth, with similar atmosphere to the one we see today. On Venus, days lasted for months as the sun arced slowly across the sky from west to east, rising and setting over a vast, shallow ocean. Finally, the data from radar measurements taken by NASA's Magellan mission in the 1990s was used to paint the last brushstrokes of this long-lost world. Filling in the lowlands with water, the topography of this ancient world emerges, with the highlands exposed as the Venusian continents. It all points to the possibility that Venus could have been the first habitable world in our solar system. So what changed? To find out, we need to look not just at the planet in isolation, but also at the star around which it orbits. No planet lives out its life in isolation. Venus, like all the planets, is not just part of a configuration of planets and moons, asteroids and comets, but is also part of a solar system, a system that is driven more than anything else by the star at its center. Today the sun burns bright in our skies, bathing our planet in just enough starlight to keep the oceans from freezing, but not too much to boil them away. Earth lies in the sweet spot we call the Goldilocks zone, but as we have already seen in this chapter, nothing in the solar system is forever, and what we see today is not what we will see tomorrow, nor what we would have seen yesterday. As our sun gets older, it's gradually burning hotter and hotter. This is because as it ages, the process of nuclear fusion, the fusion of hydrogen into mainly helium, gradually leads to an increase in the amount of helium in its core. This rise in helium causes the sun's core to contract, which in turn allows the whole star to shrink in on itself, creating an increased pressure that results in a rise in the rate of fusion, and so the energy output of the sun goes up. If tomorrow the sun is burning hotter than today, it of course makes sense that in the early days of the solar system our sun burned far less brightly. It's a life cycle that is common to all main sequence stars, the category of star that includes our sun. And as the most common type of star in the universe, we've been able to study this life cycle in intimate detail, allowing us to make immensely detailed predictions about the characteristics of our Sun in the past and in the future. Winding back the clock, the current consensus among astronomers is that 4 billion years ago the faint young Sun was at least 30% dimmer than it is today. This cooler Sun would have undoubtedly had a big impact on all of the terrestrial planets. Earth would have been much colder, and as it was receiving far less solar energy, it remains something of a mystery as to why our planet wasn't frozen solid. Instead, at this time on Earth, first life was just beginning, in the liquid water that we are pretty certain covered its surface. At the same time, 3.5 to 4 billion years ago, the young Sun would have bathed Venus in a warmer glow. This ocean world found itself in its very own sweet spot, a world held in a delicate balance. With the Sun weakened and restrained, the Earth-like atmosphere of Venus could act as a gentle blanket, keeping the surface temperate and covered in an abundance of liquid water. But even with this additional solar energy, we think Venus would still have been much cooler than the Earth is today. In fact, we believe temperatures at that time would have been like a pleasant spring day here on Earth. It wasn't to last. Slowly the young Sun grew brighter, its increased energy output causing temperatures to gradually rise, which in turn began to lift more and more water vapor into the air, thickening the atmosphere and sealing the planet's fate. Although the oceans of Venus may have persisted for billions of years, as the surface warmed and the atmosphere thickened, the destiny of this planet was already set, driven by an unstoppable process we have recently become very familiar with here on Earth. The greenhouse effect is a process that has the power both to protect and to destroy a planet. But despite this power, it actually boils down to some pretty simple physics. It's all about how sunlight, solar radiation, interacts with the constituent parts of an atmosphere. In the case of the Earth, as solar radiation hits our atmosphere, some of it is reflected straight back out into space, some is absorbed by the atmosphere and clouds, but most of the sunlight, about 48%, passes straight through the atmosphere and is absorbed by the Earth's surface, where it is heated up. The reason so much solar radiation makes it to the surface is because the gases in our atmosphere, like water vapor and carbon dioxide, are transparent to light in the visible spectrum. When you think about it, that's pretty obvious, because there's a source of visible light in the sky, the sun, and we can all see it. But it's a different story when that sunlight heats the surface of the Earth and re-radiates back out, not as visible light, but as the longer wave infrared light, thermal radiation. We can't see this light, but as it radiates back out from the Earth's surface, carbon dioxide and water vapor absorb the infrared, trapping that energy, and so the planet maintains a higher temperature that is intimately linked to the constituent parts of the atmosphere. The higher its level of gases like water vapor, carbon dioxide, methane, and ozone, the greater the greenhouse effect and the bigger the uplift in temperature. Despite the very real threat that this now poses to the future of our planet, the greenhouse effect on its own is not necessarily a bad thing. The Earth would be at an average temperature of around -18 degrees Celsius without it. But as we are currently witnessing here on Earth, shift the balance of those gases, and things can change very quickly. At some point in Venus's past, the levels of water vapor lifted into the atmosphere by the warming sun pushed the greenhouse effect to become precariously more intense. With less and less of the sun's energy escaping, the ambient temperatures began to rise exponentially, until the day came when the last raindrops fell onto the surface of the planet, the heat evaporating the rains long before they could reach the ground. Venus had reached a tipping point. With the increasing temperatures feeding more and more water vapor into the atmosphere, a runaway greenhouse effect took hold, driving away the oceans. This led to the surface of the planet getting so hot that carbon trapped in rocks was released into the atmosphere, mixing with oxygen to form increasing amounts of another greenhouse gas, carbon dioxide. With no water left on the surface and no other means to remove it, carbon dioxide built up in the atmosphere, setting the planet on a course that would result in the scorched body that we see today. And so Venus's moment in the sun came to an end. Earthlings take note. When it comes to the greenhouse effect, there is a precariously thin line between keeping a planet warm and frying it. Of the 4 rocky worlds, only one has managed to navigate through the instability and constant change of our solar system over the last 4 billion years and maintain the characteristics needed to support life. Mercury lost its fight early as it was flung inwards towards the sun. Venus flourished at first before slowly coming to the boil, and Mars, the runt of the litter, became a frozen wasteland long ago. Only Earth, uniquely among the planets, has persisted with an adequate stability over the last 4 billion years to allow liquid water to remain on its surface and an atmosphere just thick enough to keep its climate calm, not too hot and not too cold. Events have rocked us, and extremes of temperature have waxed and waned, but never outside of the parameters needed to harbour life. In a chaotic solar system filled with planetary might-have-beens, Earth is a shining example of stability, and the evidence for this is to be found in every nook and cranny of the planet. Today, Earth is dominated by life. The land and seas are teeming with millions upon millions of species, with thousands of new life forms discovered each year. Somehow, even when disaster threatened, the Earth has remained a living world. While endless species have come and gone, life has always persisted. It's woven into the fabric of the planet, an integral part of every continent and every ocean. Life plays a crucial role in maintaining the balance of the atmosphere that keeps our planet temperate. But we know for certain it cannot last. The Kamchatka Peninsula in eastern Siberia is one of the most inhospitable places on Earth. A volcanic wasteland peppered with thousands of hot springs, it's here that we find some of the toughest living things. Extremophiles survive here that are able to withstand temperatures and pH levels higher than any other land-based life forms we have ever discovered. Kamchatka is part of the Pacific Ring of Fire, and despite its remoteness, biologists have long been enticed here to explore its toxic, bubbling cauldrons for signs of life. Complex life, animals and plants, struggle to survive in temperatures above 50 degrees Celsius, so searching for life here is all about searching for single-celled life forms, bacteria and archaea, ancient microorganisms, that are somehow able to endure in this hostile environment. Life forms like Acidilobus aceticus, an archaea that can be found in a hot spring where the water is so acidic it reaches a pH of 2, and where temperatures rise to 92 degrees Celsius. In other parts of the hydrothermal field, bacteria like Desulforella acetivorans have been discovered, which happily live in pools that are touching 60 degrees Celsius, but it's these that are the real hotheads. In one of the biggest and hottest pools investigated by scientists, a large number of microbes have been found living in temperatures approaching 97 degrees, making it one of, if not the, hottest environment ever studied for signs of life on land. But to find the greatest hotheads on planet Earth, you need to look not on land, but deep beneath the sea. In the furthest depths of the Atlantic, around the black smoker hydrothermal vents blurting out of the ocean floor, we found strains of archaea that can survive temperatures of 122 degrees Celsius, and perhaps even higher. These rare life forms live at the very edges of biology. Unique adaptations to their cellular chemistry enable the proteins and nucleic acids that create the structure of the microorganism to function, while the membranes that are protecting the cells utilize different fatty acids and lipids to keep the cells stable at the higher temperatures. Perhaps there are even tougher life forms that we are yet to discover, But the thermophilic microorganisms that we have so far identified and investigated in places like Kamchatka all point to the fact that life has its limits. Evolution by natural selection can only adapt so much, and even though it's impossible to imagine what life on Earth will look like in a few 100 million or even a few billion years' time, we know that biology is constrained by thermodynamics. And so we can say with some certainty that there will come a time when the Earth is too hot for any living things to exist. Natural selection will eventually run out of options as the laws of physics outplay it, and all life will come to an end. When this will happen, no one can be certain. But as the sun ages and grows hotter, temperatures on Earth will rapidly rise. Today, the average surface temperature on the planet is 14.9 degrees Celsius. But with just a 10% rise in the sun's luminosity, the average temperature will rise to 47 degrees Celsius and climbing. The increased temperatures will raise great storms across the planet. The rains will remove carbon dioxide from the atmosphere, and it will be locked away as newly formed sedimentary rock. Trees and plants will struggle as they are robbed of the gas that sustains them, until eventually photosynthesis will cease. The lungs of our planet will fail, and the precious oxygen that green plants and algae produce will dwindle. With the primary food source gone, the food chain will collapse and the age of complex life on Earth will draw to a close. Heat-loving extremophiles may flourish for millions of years more, but eventually nuclear physics will have its way, and as average temperatures race above 100 degrees Celsius, the last pockets of life will be extinguished from the Earth. We can say with confidence this is going to happen because we can plot the future of our Sun far more precisely than the future of the Earth. Our understanding of nuclear physics allows us to predict what happens inside the cores of stars, and thus we can see the past, present, and future of stars like ours written across the night sky. The heavens are filled with shining examples of stars that give us a glimpse into the future of our Sun. Arcturus, for example, in the constellation Boötes, is one of the brightest stars in the northern hemisphere. It's around the mass of the Sun, perhaps a little bit heavier, and so in the distant past would have had remarkably similar characteristics to our own star. Today, though, Arcturus is 6 to 8 billion years old, potentially 3 billion years older than the Sun, and as it is no longer a main sequence star, it is now in the red giant phase. Its fuel exhausted, it has swollen up to 25 times its original diameter, and is around 170 times as luminous, despite the fact that as its core slowly burns out, it is cooling. To see even further into the future, we need to look towards the brightest star in the northern sky, Sirius. The dog star, as it's commonly known, is twice the mass of the Sun and still fully in the main sequence. But obscured by the glare of Sirius A is a faint companion, Sirius B. This is a star that has already burnt through its fuel, swollen into a red giant, and the outer layers have drifted off into space, leaving the fading core of the star about the size of the Earth, known as a white dwarf. These stars are just two examples amongst many that point us towards the ultimate fate of our Sun, a fate that we believe will play out over the next 5 billion years or so. Just like Arcturus, as the Sun exhausts its hydrogen fuel, its outer edge will inflate and it will enter a red giant phase. Expanding millions of kilometers out into space, it will engulf Mercury first. Venus's fate will be sealed next as the Sun expands further. Some models predict that Earth may just escape the fiery end of its neighbours, heated to 1,000 degrees Celsius, but hanging on beyond the edge of the dying star as its orbit extends out due to the lessening mass of the Sun. Dead but not destroyed, Earth and Mars will orbit as burned-out relics of their former selves. The era of the 4 rocky inner planets will be over, the billions of lives lived on the surface of one of them nothing but a distant memory. But within our solar system lies another family of rocky worlds, whose moment in the Sun may be to come. Far beyond the asteroid belt, millions of miles away from the sun-drenched planets of the inner solar system. The gas giants of Jupiter and Saturn are home to another family of rocky worlds. Jupiter alone has 79 known moons orbiting it, a menagerie of satellites of multiple shapes and sizes. We've been peering at these moons since Galileo Galilei spotted 4 of them, Io, Europa, Ganymede and Callisto, known as the Galilean moons, over 400 years ago, with his telescope transforming our understanding of our place in the solar system. Today we have explored the Galilean moons not just from afar, but close up, and found them to be dynamic worlds. Io is fiercely volcanic, and Europa, the ice moon, shows tantalizing evidence on its surface pointing to a subsurface ocean sitting below its icy crust. Ganymede and Callisto make up the final 2 Galilean moons, and just like Europa, they are rocky worlds with an abundance of water ice on their surfaces, and perhaps their own oceans lurking beneath. These 3 rocky, frozen worlds are all sitting in the cold outreaches of our solar system, touched by the distant sun but barely warmed, lying dormant until perhaps one day the aging sun will reach out and turn these bodies into ocean worlds for the very first time. The next planet out, Saturn, also has its ever-growing family of moons. Amongst its collection of over 60 confirmed satellites are Titan, the only known moon with a dense atmosphere and liquid lakes on its surface, though they are primarily methane, not water, and Enceladus, a frozen ice moon just like Europa with a liquid ocean deep beneath its ice. We will come to Enceladus in detail in Chapter 4, but for now it's intriguing to note that this icy moon may be our best current candidate as a second life-sustaining world in our solar system. Until we go back and explore further, we can't be certain what lies below its surface. But the possibilities that the Cassini probe has so tantalizingly hinted at make it one of the most exciting places for us to visit within the next generation of interplanetary expeditions. All these ice worlds, sitting dormant in the frozen reaches of the solar system, offer the promise of a very different future, one in which the rocky worlds of the inner solar system have been reduced to cinders, and a new generation of worlds waits to awaken. Ice worlds will become water worlds, warmed by the expanding sun, until our dying star ultimately collapses into a white dwarf.
Outwards to the Milky Way. Newton's laws are the keys to understanding our place in our local neighbourhood. Coupled with precision observations of the motion of the planets and moons, they allow the scale and geometry of the solar system to be deduced and their positions to be calculated at any point in the future. The nature and location of the stars, however, requires an entirely different approach, because at first sight they appear to be point-like and fixed. The observation that the stars don't appear to move is important if you know something about parallax, as the ancients did. Parallax is the name given to a familiar effect. Hold your finger up in front of your face and alternately close each of your eyes, keeping your finger still. Your finger appears to move relative to the more distant background, and the closer your finger is to your face, the more it appears to move. This is not an optical illusion. It's a consequence of viewing a nearby object from 2 different spatial positions, in this case the 2 slightly different positions of your eyes. We don't normally perceive this parallax effect because the brain combines the inputs from the eyes to create a single image, although the information is exploited to create our sense of depth. Aristotle used the lack of stellar parallax to argue that the Earth must be stationary at the centre of the universe, because if the Earth moved, then the nearby stars would be observed to move against the background of the more distant ones. Thousands of years later, Tycho Brahe used a similar argument to refute the conclusions reached by Copernicus. Their logic was completely sound, but the conclusion is wrong because the nearby stars do move relative to the more distant background stars as the Earth orbits the Sun, and indeed as the Sun orbits the galaxy itself. You just have to look extremely carefully to see the effect. Amongst the thousands of stars visible to the naked eye, 61 Cygni is one of the faintest. It's not without interest, being a binary star system of two orange K-type dwarf stars, slightly smaller and cooler than the Sun, orbiting each other at the lethargic rate of around 700 years. Despite the pair's relative visual anonymity, however, 61 Cygni has great historical significance. The reason for this quiet fame is that this faint star system was the first to have its distance from Earth measured by parallax. Friedrich Bessel is best known to a physicist or mathematician for his work on the mathematical functions that bear his name. Pretty much any engineering or physical problem that involves a cylindrical or spherical geometry ends up with the use of Bessel functions, and in blissful ignorance, you will probably encounter some piece of technology that has relied on them in the design process at some point today. But Bessel was first and foremost an astronomer, being appointed director of the Königsberg Observatory at the age of only 25. In 1838, Bessel observed that 61 Cygni shifted its position in the sky by approximately 2/3 of an arcsecond over a period of a year as viewed from Earth. That's not very much. An arcsecond is 1/3600th of a degree. It is enough, however, to do a bit of trigonometry and calculate that 61 Cygni is 10.3 light-years away from our solar system. This compares very favourably with the modern measurement of the distance, 11.41 plus or minus 0.02 light-years. Parallax is so important in astronomy that there is a measurement system completely based on it, which allows you to do these sums in your head. Astronomers use a distance measurement known as a parsec, which stands for per arcsecond. This is the distance of a star from the Sun that has a parallax of 1 arcsecond. 1 parsec is 3.26 light-years. Bessel's measurement of the parallax of 61 Cygni was 0.314 arcseconds, and this immediately implies that it's around 10 light-years away. Even today, stellar parallax remains the most accurate way of determining the distance to nearby stars, because it is a direct measurement which uses only trigonometry and requires no assumptions or physical models. On the 19th of December 2013, the Gaia space telescope was launched on a Soyuz rocket from French Guiana. The mission will measure, by parallax, the positions and motions of 1 billion stars in our galaxy over 5 years. This data will provide an accurate and dynamic 3D map of the galaxy, which in turn will allow for an exploration of the history of the Milky Way, because Newton's laws, which govern the motions of all these stars under the gravitational pull of each other, can be run backwards as well as forwards in time. Given precise measurements of the positions and velocities of 1% of the stars in the Milky Way, it is possible to ask what the configuration of the stars looked like millions or even billions of years ago. This enables astronomers to build simulations of the evolution of our galaxy, revealing its history of collisions and mergers with other galaxies over 13 billion years, stretching back to the beginning of the universe. Newton and Bessel would have loved it. Stellar parallax, when deployed using a 21st century orbiting observatory, is a powerful technique for mapping our galaxy out to distances of many thousands of light-years. Beyond our galaxy, however, the distances are far too great to employ this direct method of distance measurement. In the mid-19th century, this might have appeared an insurmountable problem, but science doesn't proceed by measurement alone. As Newton so powerfully demonstrated, scientific progress often proceeds through the interaction between theory and observation. Newton's law of gravitation is a theory. In physics, this usually means a mathematical model that can be applied to explain or predict the behavior of some part of the natural world. How might we measure the mass of a planet? We can't weigh it directly, but given Newton's laws, we can determine the planet's mass very accurately if it has a moon. The logic is quite simple. The moon's orbit clearly has something to do with the planet's gravity, which in turn has something to do with its mass. These relationships are encoded in Newton's law, and careful observation of the moon's orbit around the planet therefore allows for the planet's mass to be determined. For the more mathematical reader, the equation is m planet plus m moon equals 4 pi squared a cubed over gp squared, where a is the time average distance between the planet and the moon, g is Newton's gravitational constant, and p is the period of the orbit. This equation is in fact Kepler's third law, discovered empirically by Kepler in 1619. Kepler's laws can be derived from Newton's law of gravitation. Under the assumption that the mass of the planet is far larger than the mass of the Moon, this equation allows for the mass of the planet to be measured. This is how theoretical physics can be used to extract measurements from observation, given a mathematical model of the system. To measure the distance to objects that are too far away to use parallax, therefore, we need to find a theory or mathematical relationship that allows for a measurement of something, anything, to be related to distance. The first relationship of this type, which opened the door to all other methods of distance measurement out to the edge of the observable universe, was discovered at the end of the 19th century by an American astronomer named Henrietta Leavitt.
Mars is a mirror for our dreams and nightmares. To the naked eye, the planet exhibits a reddish hue, blood red in the imagination, god of war, star of judgment. Through a small telescope, it is the most Earth-like of planets, with cinnabar deserts and white polar ice caps. A world we could imagine visiting, perhaps even settling in. 19th century astronomers convinced themselves they saw plains and mountain ranges, and canals delivering meltwater from high latitudes to arid equatorial cities. Some thought the Martians a peaceful civilization, far in advance of our own. Others saw threat. Across the gulf of space, minds that are to our minds as ours are to those of the beasts that perish, intellects vast and cool and unsympathetic, regarded this earth with envious eyes, wrote H.G. Wells in his classic science fiction novel The War of the Worlds in 1897. The nature of Mars remained a mystery until well into the 20th century, because the planet is small and far away, and therefore difficult to view with ground-based telescopes. Even the Hubble Space Telescope, high above the distorting effects of Earth's atmosphere, produces images which would not at first sight have prevented Wells from publishing. With a little imagination, the ice caps, high clouds, and dark regions circling the deserts could be mistaken for evidence of a water cycle feeding the seasonal advance and retreat of vegetation. Photographs from the first flyby of Mars by NASA's Mariner 4 spacecraft on the 15th of July 1965 abruptly laid to rest the romantic notion of Mars as Earth's habitable twin or potential foe. These images revealed an arid surface reminiscent not of our blue planet, but of our desiccated moon. Overnight, we discovered for certain that Earth is the only planet in the solar system capable of supporting complex life. And contemporary accounts of the impact of the Mariner 4 flyby suggest that this was a powerful realization. In November 1965, the Bulletin of the Atomic Scientists carried an article entitled "The Message from Mariner 4," and the message was bleak. The shock of Mariner's photographic and radiometric reports is caused not only by their denial of the terrestrial image of Mars, but by the revelation that there is no second chance, at least not in the solar system. President Lyndon B. Johnson was reported as commenting, it may just be that life as we know it, with its humanity, is more unique than many have thought." The hesitation in the first few words is revealing. Here is Mars as a symbol of our cosmic isolation. It is as though deep, or perhaps not so deep, in the subconscious, the 1960s power brokers all the way up to the president suddenly understood that the Earth is far more fragile and precious than a dispassionate analysis of their Cold War brinkmanship might suggest. Or perhaps the perspective delivered by exploration is always shocking. Apollo 8's Earthrise, the photograph that delivered such a positive end to a troubled 1968 by setting the blue Earth against the grey Moon, was 3 years away. But Red Mars provided a foretaste. In response, Carl Sagan co-authored a paper suggesting, somewhat playfully, that all was not lost. Mariner 4 took only 22 photographs with a resolution of over a kilometre. in a strip crossing the region in which the astronomer Percival Lowell had sketched canals from his observatory in Flagstaff, Arizona at the turn of the 20th century. From the warmth of the Arizona desert, Lowell wrote that Mars was chilly, but no more so than the south of England, which certainly supported a civilization of sorts. Using several thousand photographs of a similar resolution taken by meteorological satellites in Earth's orbit, Sagan and his co-authors found only a single feature that unambiguously indicated the presence of a civilization: Interstate Highway 40 in Tennessee. They concluded that Mariner 4 would not have detected human civilization had it flown by Earth. We do not expect intelligent life on Mars, but if there were intelligent life on Mars comparable to that of Earth, a photographic system considerably more sophisticated than Mariner 4 would be required to detect it. The non-existence of an extant Martian civilization was confirmed by the Mariner 9 mission in November 1971, the first spacecraft to orbit another planet. Mariner 9 achieved a photographic resolution of 100 meters per pixel, and no sign of intelligent life, past or present, was detected. The twin Viking landers in 1976 failed to detect even microbial life, although the combined results of the suite of microbiology experiments carried by the spacecraft are not considered to be unequivocal, because Martian soil chemistry is, to coin a phrase from the official NASA report, enigmatic, and could conceivably have masked any biological activity. In hindsight, the fact that Mars is not teeming with life today is not so surprising. Mars orbits 50 million miles further from the Sun than Earth, and receives less than half the solar energy. It is a small world with a tenuous atmosphere that provides little insulation or greenhouse warming. NASA's Curiosity rover in the Gale crater has measured midday temperatures above 20 degrees Celsius, but in the early hours of the morning it has experienced minus 120. As Alfred Russel Wallace wrote in 1907, any attempt to transport water across the Martian surface today would be the work of madmen rather than of intelligent beings. There are no canals, no cities, and no envious eyes. The planet is a frozen, hyper-arid desert, too far from the Sun to support complex life. Yet it hasn't always been this way. Observations from our fleet of orbiting spacecraft and landers have revealed a complex and varied past. Once upon a time, the red planet was glistening blue. Streams ran down hillsides, and rivers wound their way through valleys, carved by a water cycle from land to sky and down again, from mountains and highlands to the sea. This presents a great challenge for planetary scientists. Put simply, nobody would have been surprised if Mars had always been an inert rock, because it is a small planet far from its star. But the geological evidence is unequivocal. The surface tells a different story. Mars, then, remains an enigma. As a wandering red star, it stirred the imagination of the ancients. As a telescopic image, too small and shifting for visual or intellectual clarity, it became our twin. When spacecraft flew by, it shocked us into considering our cosmic isolation. The red planet was relegated in our collective consciousness to the status of just one more rock, glistening in the night. Then we landed, and discovered a world that was once habitable, and could be again. A map of Mars can be read like a history book. Unlike Earth, where constant weathering, tectonic activity and volcanism have erased the deep geological past, Mars has been relatively quiescent for most of its life. The scars of collisions from the first turbulent billion years after the formation of the solar system can still be seen from orbit. Ancient cataclysms documented below a thin film of dust. NASA's Mars Global Surveyor spacecraft spent 4.5 years mapping Mars in the late 1990s and provided detailed maps with colors corresponding to differences in altitude. Just as on Earth, there is significant variation, but the geological features on our smaller sister world are much bigger and bolder. The highest elevations on Mars are found on the Tharsis Rise, a great volcanic plateau and home to the largest volcano in the solar system, Olympus Mons. At over twice the height of Everest, Olympus Mons towers 25 kilometers above the lowlands of Amazonis Planitia to the west, and its base would fit inside France just about. Cutting a deep scar across Tharsis to the southeast of Olympus Mons is Valles Marineris, named after the Mariner 9 spacecraft that discovered it, a canyon that dwarfs anything on Earth. The Grand Canyon would fit into one of its side channels. The lowest points on Mars are found in the Hellas Impact Basin, the largest clearly visible impact crater in the solar system. From the highest points on the crater rim to the floor, Hellas is over 9 kilometers deep. It could contain Mount Everest. The atmospheric pressure at the floor is twice that at the rim, high enough for liquid water to exist on the surface, in a narrow range of temperatures. These are extreme altitude differences for a small world. Over 30 kilometers from the summit of Olympus Mons to the floor of Hellas. On much larger Earth, for comparison, there is only 20 kilometers difference between the summit of Everest and the Challenger Deep in the depths of the Mariana Trench. The most striking and ancient elevation difference on Mars is that between the northern and southern hemispheres of the planet, known as the global dichotomy. Mars is an asymmetric world. The northern hemisphere is on average 5.5 kilometers lower in altitude than the southern. There is no consensus as to how the dichotomy formed, other than that it was early in the planet's history, and before the large impacts which created the Utopia and Chryse basins around 4 billion years ago. At some later time, the northern lowlands were resurfaced by volcanic activity in a similar fashion to the smooth lunar seas, which accounts for their lack of cratering relative to the much more ancient terrain to the south. The oldest terrain on Mars is found in the Noakis Terra region of the southern highlands. It is characterized by heavy cratering reminiscent of the far side of the Moon. Even small craters in the Noakian highlands are heavily eroded, which suggests the regular, if not persistent, presence of liquid water. There are dry river valleys and deltas, and evidence of water pooling in the craters and overflowing their walls, forming interconnected networks of lakes. This is how we know Mars was once a warmer and wetter world, at least occasionally. The evidence is written across the land of Noah. In contrast, the younger terrain of Hesperia Planum displays much less evidence of regular erosion by water, but bears the scars of occasional catastrophic floods that cut deep valleys over very short periods of time, and may have formed temporary large lakes or seas. The Amazonis Planitia region shows little sign of flowing water, fewer impact craters, and less evidence of active volcanism, suggesting it was formed more recently, when Mars was significantly less geologically active. The persistence of surface features over many billions of years in the Noakian, Hesperian, and Amazonian regions has led to the historical epochs of Mars being named after the distinctive terrains that still bear the characteristic marks of the climate and geological activity that formed and sculpted them. The Noakian period was the earliest and wettest, and coincided with the origin of life on Earth around 4 billion years ago, when conditions on both worlds appear to have been very similar. The Martian atmosphere may have been denser than Earth's and dominated by carbon dioxide, but significant questions remain about how such an atmosphere could have warmed Mars sufficiently to deliver the warm, wet climate, and how that atmosphere was lost. The MAVEN spacecraft, currently in orbit around Mars, aims to answer this question, as we'll discuss later in this chapter. The Noakian period ended as Mars became increasingly cold and arid around 3.5 billion years ago, just as life was gaining a foothold on Earth. The Hesperian period, the time of catastrophic floods, ran from the end of the Noakian to around 3 billion years ago, when Mars entered its current frozen, arid phase, punctuated by occasional volcanic activity and the large-scale movement of ice, but with very little evidence of flowing water. The long, 3-billion-year freeze from the end of the Hesperian to the present day is known as the Amazonian. This is a summary of what we know about Mars. The whys pose a significant challenge to planetary scientists. Given a warm, wet, and seemingly stable world early in its history, what triggered the loss of atmosphere and descent into modern-day aridity? What happened to the water on Mars? Was it lost to space, or does it persist today as surface ice or in subsurface rocks or reservoirs? If so, how much water is still accessible? Could we exploit the ancient reservoirs of Mars to support a human colony? And perhaps most significantly of all, did life arise on the planet during the Noachian period, coincident with the origin of life on Earth? And could that life still be present on Mars today? The current fleet of spacecraft in orbit around Mars and roving across its surface has been designed to answer these questions. Mars today is a planet buzzing with activity. Communications to Earth and the Martian Internet are managed by the Mars Reconnaissance Orbiter, MRO, an orbiting bridge between worlds. MRO carries the HiRISE instrument, a camera with resolution high enough to see basketball-sized features on the Martian surface. The Mars Color Imager Marquee camera monitors Martian weather, and the Compact Reconnaissance Imaging Spectrometer for Mars, CRISM, identifies mineral deposits, particularly those formed in the presence of surface water. Orbiting with the MRO is the Mars Atmosphere and Volatile Evolution Mission, MAVEN. This cameraless spacecraft operates between 150 kilometers and 6,000 kilometers above the Martian surface, measuring the composition of the atmosphere at different altitudes and observing how the tenuous gases are stripped from the planet by the solar wind. Mars Odyssey is the veteran of the orbiting fleet, having arrived in 2001 and still being operational in a polar orbit, searching primarily for water ice on the surface. Mars Express is a European Space Agency mission that is delivering high-resolution photographs, mineralogy data, radar investigation of the near subsurface, and atmospheric measurements, including the search for methane, a gas that on Earth is associated with biological activity. India's Mangalyaan space probe is primarily a technology demonstrator, but it carries a secondary scientific package capable of investigating atmospheric composition. The newest arrival at Mars is the joint European Space Agency Russian ExoMars Trace Gas Orbiter, which will observe seasonal changes in the Martian atmosphere and search for subsurface water deposits. The spacecraft will form the communications bridge for ESA's ExoMars rover, due to land in 2021. The two most recent explorers of Mars are the Opportunity and Curiosity rovers. The Opportunity rover landed on the Meridiani planum close to the Martian equator on the 25th of January 2004, with a planned lifetime of 90 Earth days. In a spectacular testament to the Jet Propulsion Laboratory's engineering excellence, Opportunity remained operational until a planet-wide dust storm covered its solar panels in June 2018, after over 14 years and a journey of 45 kilometers on the surface of Mars, exploring the Endurance, Victoria, and Endeavour craters. On the 13th of February 2019, Opportunity was finally declared dead. Opportunity's younger and far larger companion on Mars is Curiosity, the most massive and most capable spacecraft ever to touch down on a planet beyond Earth. The landing itself was a tour de force of engineering ingenuity and audacity. The enormity of the mission is best described through the words of Alan Chen, operations lead at NASA for the Curiosity mission, at 10:31 PDT on the 5th of August 2012, watching the landing at the Jet Propulsion Laboratory alongside the team. The engineers described it as 7 minutes of terror. 7 minutes to maneuver a spacecraft that had taken 8 years to design and build, with a program cost of more than $2.5 billion, from 13,000 miles per hour at the top of the Martian atmosphere to a soft landing on the surface of the planet. The tension reflected the high stakes. The Mars Science Laboratory mission, to give the lander and orbiter their full title, was a high-risk flagship science mission in the same category as Voyager, the Hubble Space Telescope, Viking and Cassini, and was beset by cost and schedule overruns and controversy. This is in many ways unsurprising. New technologies and ambitious scientific objectives are difficult to implement and achieve, and in part because of this deliver great rewards. In hindsight, nobody would question the value of any of these missions, which have delivered some of the greatest insights and most inspiring images in the history of exploration. Yet this never prevents bean counters and rival scientists with agendas, and more charitably, budgetary challenges of their own, whinging and even considering cancellation. This is naive. Funding for science is almost always grudging from a political class whose view of the acquisition of knowledge is utilitarian. The far deeper value of exploration as a critical part of the internal voyage of our species, bringing us into direct confrontation with the mystery of our existence, is lost on them, at least until occasional Johnsonian, President, not Alexander Boris to Pfeffel, moments. It may just be that life as we know it with its humanity is more unique than many have thought, and we must remember this. Which means that a cancellation of one project does not mean an uplift in funds for another. More likely the budget will be lost to science. At the time of writing, the same issues plague another NASA flagship mission, the James Webb Space Telescope. As Robert D. Baum wrote in an op-ed article for Space News in December 2008, at the height of the Mars Science Laboratory controversy, when implementing flagship missions, cost and schedule overruns are not uncommon. But history shows that the mission return often eclipses the expenditure. The Hubble Space Telescope experienced a development cost overrun several times its approved project budget, and was launched much later than originally planned. In hindsight, would any rational space scientist not concede that the return from Hubble was worth the investment? Given the febrile atmosphere, however, no amount of philosophy or reason would mitigate the costs of failure of the Mars Science Laboratory mission. A landing accident was both possible and unthinkable. Delivering almost a ton of fragile rover onto the surface of Mars with pinpoint accuracy is not trivial, which is perhaps why the chosen engineering solution seemed, not to put too fine a point on it, daring. Mars has a thin atmosphere, so slowing down a spacecraft when it's travelling around 10 times faster than a bullet is hard. And yet the atmosphere is thick enough to apply sufficient frictional heating to destroy a spacecraft without adequate protection, and turbulent enough to cause significant uncertainty in the landing site of an unsteered vehicle. This renders the more obvious engineering solutions redundant. You can't simply deploy a parachute and float to the surface. The 1970s Viking landers used a combination of heat shields during aerobraking, parachutes, and retro-rockets with success. But the Curiosity engineering team dismissed this tried-and-tested solution. It did not allow for high enough precision, or for the gentle landing required for the pinpoint delivery of a large rover with delicate wheels. The Viking landers had legs built like tanks. The Viking landers also carried their heavy descent rocket systems with them to the ground, which didn't matter because they stayed put. Curiosity would have had to lug all this unnecessary mass around Mars for years. The Opportunity rover, her sister ships Spirit and the earlier Mars Pathfinder, employed a combination of aerobraking, parachutes, rockets, and airbags to cushion the falling spacecraft. But these previous rovers were lightweight in comparison, at just over a fifth of the mass of the gargantuan Curiosity. A rover of this size and complexity bouncing over the surface in an airbag cocoon was not considered feasible, primarily because of the sheer mass of the airbag system needed to cushion the impact. The lightweight Opportunity rover's landing system was almost twice the mass of the rover itself. The chosen Entry, Descent and Landing Procedure, EDL, for Curiosity, was described by mission lead Adam Stelzner as the result of reasoned engineering thought. A beautiful example of the truism that reasoned engineering thought and common sense, at least of the sort possessed by the average golf club bore, do not always match up. The Curiosity EDL appears to the untrained eye to be bonkers, or maybe overcomplicated, but it wasn't, and it worked. Tucked up inside a protective shell, Curiosity encountered the outer layers of the Martian atmosphere, 125 kilometers above the surface and traveling at around 20,000 kilometers per hour, at 10:23 p.m. Pacific Daylight Time on the 5th of August 2012. The spacecraft, at this stage cocooned inside a protective enclosure, flew entirely under the control of its onboard computers, with no input from mission control on Earth. This was the first time an autonomous guided entry system was employed for an interplanetary mission, using a combination of thrusters and the ejection of balance masses to shift the center of mass and trajectory of the spaceship and guide it with a design accuracy of around 10 kilometers towards the chosen landing site. This guided rather than ballistic trajectory allowed for a much wider choice of landing sites for Curiosity than for the previous landers, which required around 100 kilometers of flat, safe land surrounding the nominal touchdown point. But it also required the rover to fly itself. The round-trip travel time for a radio signal to Mars was over 13 minutes when Curiosity landed, making control from the Jet Propulsion Laboratory in California impossible. During the first stage of descent, a heat shield constructed from a unique material known as pica, phenolic-impregnated carbon ablator, protected Curiosity from peak temperatures of around 2,000 degrees Celsius, generated by friction in the thickening Martian atmosphere. 4 minutes after beginning the entry phase, slowed to just under 3,000 kilometers per hour, Curiosity's parachute deployed at an altitude of 11 kilometers above the surface. The supersonic parachute is a vast and complex structure, 80 suspension lines over 50 meters long, attached to a 16-meter canopy. Having slowed to a velocity of 700 kilometers per hour with the help of the parachute, the heat shield was jettisoned at an altitude of 8 kilometers, allowing the onboard radar to get a view of the ground and deliver high-precision altitude and velocity measurements. With the parachute fully unfolded in relatively dense, low-level Martian atmosphere, Curiosity drifted in the Martian sky for 80 seconds, descending ever more slowly. At an altitude of 1.8 kilometers, traveling at a sedate 280 kilometers per hour, the NASA timeline calls for a deep breath as Curiosity separated from the parachute system and dropped in freefall towards Mars. For engineers, says the NASA website, it's like jumping out of a plane for the first time. The freefall drop was designed to allow Curiosity to separate far enough from the parachute system so that it wouldn't accelerate back into it when 300 meters further down, its retro-rockets fired and the powered descent phase of the landing began. For the Viking landers, this was the final phase, but for Curiosity, after the rockets had delivered the rover to an altitude of just 20 meters with a descent velocity of less than 1 meter per second, almost a hover, the audacious final phase of the landing protocol kicked into action, the sky crane. The rover slowly departed the rocket cradle, attached by 3 nylon wires and an umbilical cord of electrical connections 7.5 meters in length. 4 of the rockets, angled away from the vertical so as not to damage the rover, continued to fire, allowing the whole delicate system to approach the surface at walking pace. At 5 meters from the surface, Curiosity unfurled its wheels, stowed for the 8-month journey from Earth. At 10:32 p.m., the rover confirmed its wheels were in contact with the Martian surface and issued one last command through the electrical umbilical up to the sky crane. I'm down, cut the cables, and fly away. After a 500 million kilometer journey, Curiosity was delivered safely to Mars, just 2.4 kilometers from its nominal landing point. a triumph of engineering ingenuity and brilliance. Curiosity was sent to Mars to explore Gale Crater, a 150-kilometre wide impact crater formed during the late Noachian or early Hesperian period, when liquid water would have been present at least occasionally on the surface. In the great tradition of astronomy, the crater is named after the Australian amateur astronomer, planetary observer, comet hunter, and occasional banker, Walter Frederick Gale, who discovered a host of comets as well as a number of geological features on Mars at the turn of the 20th century, using self-built telescopes in his backyard. The primary reason for choosing Gale Crater was the unusual central structure Mount Sharp, or Aeolis Mons, which rises over 5 kilometres above the crater floor. There is still debate about precisely how Mount Sharp formed, but the layers visible from orbit along its flanks suggest that it is the weathered remains of sedimentary rocks which once filled the crater and were laid down over time after the impact. Subsequent erosion by the relentless Martian winds removed much of the surrounding rock to reveal the ancient crater floor once more, while leaving the towering central structure intact. Deep, exposed sedimentary layers are extremely enticing to geologists, because a cross-section through rock is a cross-section through time. As surface and atmospheric conditions change, different sorts of rock are laid down and chemically modified. As Curiosity ascends the slopes of Mount Sharp, it climbs forwards through Martian time, and scientists are close behind. Joy Crisp, the deputy project scientist from NASA's Jet Propulsion Laboratory, explained the choice of landing site in the weeks before launch. Mount Sharp may be one of the thickest exposed sections of layered sedimentary rocks in the solar system. The rock record preserved in those layers holds stories that are billions of years old, stories about whether, when, and for how long Mars might have been habitable. Just as the layers of exposed rock in the Grand Canyon on Earth reveal the story of our planet, the exposed sedimentary layers of Mount Sharp are a storybook that the winds of Mars have opened, ready for Curiosity to read. At the time of writing, Curiosity has travelled almost 19 kilometres from its landing site on the flat plains to the lower slopes of Mount Sharp, stopping along the way at each interesting site to characterise the geological environment. Curiosity's suite of scientific instruments is the most sophisticated ever installed on a spacecraft. The rover is a mobile geological laboratory capable of analysis of the Martian surface and the layers just beneath. NASA loves acronyms. Curiosity acquires samples using the SSS, the Surface Sampling and Science System. It is made up of 3 parts: the SASPAR, Sample Acquisition, Processing and Handling Subsystem, SAM, Sample Analysis at Mars Instrument, and CHEMIN, Chemistry and Mineralogy Instrument. The main components of SASPAR, which is mounted at the end of Curiosity's robot arm, are an integrated scoop and sample processing system, Chimera, and a drill for acquiring surface and subsurface samples. The scoop and sample processing system surely has one of the most inventive of all NASA acronyms. CHIMRA, pronounced Chimera, after the multi-headed creature of Greek mythology, which stands for the Collection and Handling for In Situ Martian Rock Analysis Tool. Someone deserves an award for that. These are transferred into SAM, which includes a gas chromatograph, a mass spectrometer, and a tunable laser spectrometer, and CHEMIN, the first X-ray diffraction experiment ever flown in space, and the most sophisticated modern technique for characterizing mineral samples on Earth. The science returned from Curiosity is only just beginning. As older data are analyzed and published, and new data from its climb up the slopes of Mount Sharp and through Martian geological time continues. But current results are consistent with, and greatly enhance the detail of, our picture of a planet that was warmer and wetter when Gale formed around 3.5 billion years ago. In early October 2012, Curiosity rolled to a halt at a place the geologists christened Rock Nest, and scooped up a handful of Mars. The sample of dust, dirt, and finely grained soil was fed into the SAM and heated to 835 degrees Celsius. The baking process revealed the presence of significant amounts of carbon dioxide, oxygen, and sulfur compounds. Sam's analysis also suggested the presence of carbonates, which form in the presence of water. Perhaps most surprising of all, the soil from Rocknest didn't just provide circumstantial evidence for ancient water. Around 3% of the sample's mass was water, suspended as small ephemeral droplets of salty liquid. Curiosity is sitting on the floor of a lost lake, a body of water that filled Gale at the Noachian-Hesperian boundary. The patterns of sedimentary deposits suggest the lake rose and fell in multiple cycles over tens of millions of years. A transient landscape of ancient streams, deltas, and ponds is bounded by the border of the crater. When alighting on ancient riverbeds running down from the crater's rim, Curiosity has found sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all the necessary building blocks for life. Summarizing the results in August 2017, Michael Mayer, NASA's lead scientist for the Mars exploration program, said, "A fundamental question for this mission is whether Mars could have supported a habitable environment. From what we know now, the answer is yes." In June 2018, two new discoveries strongly reinforced the idea that Mars was once a habitable world, and maybe still is. Curiosity found complex organic molecules a few centimeters below the surface, in rocks known as mudstone that form from silt deposited on lake beds. This means that all the ingredients for life were present at the time when Gale Crater was filled with water. Detected molecules include benzene, toluene, propane, and butane. Even more tantalizingly, Curiosity also observed a strong seasonal variation in methane levels in the Martian atmosphere today, reaffirming and enhancing previous observations of methane spikes from orbit. The important additional information from Curiosity was that the methane peaked repeatedly in the warm summer months and declined in the cooler winter, which is what would be expected if the methane had a biological origin. This is not irrefutable evidence of life on Mars today by any means. It's thought that geological processes may be able to account for such a seasonal variation, although if this were Earth, a biological explanation would be favored. The appropriately cautious Michael Mayer had this to say in June 2018. "Are there signs of life on Mars? We don't know. But these results tell us we are on the right track." Science is a humble and cautious pursuit, and from the time of Viking we've known that Martian soil chemistry is notoriously complex and can easily catch out the unwary scientist. So we should leave it there. Curiosity continues its journey through Martian geological history emboldened. It is certainly driving across an ancient lake bed where, for a reasonably extended period over 3 billion years ago, conditions were favorable and all the ingredients for life were present. While we shouldn't speculate or read too much into the results to date, we can let our imaginations wander for a moment to picture what Gale Crater might have been like during the late Noachian, when life was gaining a foothold on her sister world. We stand on the shores of a lake partially filling Gale, fed by runoff from snowmelt on the far northern rim. Where Mount Sharp now stands, a small island breaks the surface blue, not the mountain of today, but a small central peak left over from the impact. A place of grand beauty, where each Martian evening the pale sun sets in the west beyond the island, rays glinting dimly off the still waters, interrupted by the shadow of the peak out to the crater's edge. A sundial, marking the passing of time, on a lake populated by microbial Martians.
The Earth is replete with features named after rogues, because history is the province of the rich and powerful, and the deserving rarely become either. To find more worthy geographical nomenclature, it is necessary to look further afield, to a place that escaped the attention of the vain. The dark side of the moon is such a place. because nobody had seen it until the Soviet spacecraft Luna 3 photographed it in 1959. It isn't dark, by the way. It permanently faces away from Earth due to an effect called tidal locking, and receives the same amount of sunlight as the familiar Earth-facing side. The first humans to see it were the crew of Apollo 8, when Bill Anders memorably described it as looking like a sand pile my kids have played in for some time. It's all beat up, no definition, just a lot of bumps and holes. Lacking the smooth lunar maria, the dark side is an expanse of craters, and many of these have been named entirely appropriately after deserving scientists. Giordano Bruno is there, of course, alongside Pasteur, Hertz, Millikan, D'Alembert, Planck, Pauli, van der Waals, Poincaré, Leibniz, van der Graaf, and Landau. Arthur Schuster, the father of the physics department at the University of Manchester, is honoured. And tucked away in the southern hemisphere, next to a plain named Apollo, is a 65-kilometre wide, partly eroded crater called Leavitt. Henrietta Swan Leavitt was one of the Harvard computers, a group of women employed to work at the Harvard College Observatory by Professor Edward Charles Pickering. By the late 19th century, Harvard had collected a large amount of data in the form of photographic plates, but the professional astronomers had neither the time nor resources to process the reams of material. Pickering's answer was to hire women as skilled and cheap analysts. Scottish astronomer Wilhelmina Fleming was his first recruit, whom he employed after proclaiming that even his maid could do a better job than the overworked males at the observatory. Fleming became a respected astronomer. She was made an honorary member of the Royal Astronomical Society in London, and amongst many important published works, discovered the Horsehead Nebula in Orion. Buoyed by this successful policy, Pickering continued to expand his computers throughout the later years of the 19th century, bringing Henrietta Leavitt into the team in 1893. Pickering assigned her to the study of stars known as variables, whose brightness changes over a period of days, weeks, or months. In 1908, Leavitt published a paper based on a series of observations of variable stars in the Small Magellanic Cloud, which we now know to be a satellite galaxy of the Milky Way. It consists of a detailed list of the positions and periods of 1,777 variable stars, and towards the end a brief but extremely important observation. It is worthy of note that in Table 6 the brighter variables have the longer periods. It is also noticeable that those having the longest periods appear to be as regular in their variations as those which pass through their changes in a day or two. This discovery immediately caught the interest of Pickering, and for good reason. If a star's intrinsic brightness is known, then it is a simple matter to calculate its distance. Put very simply, the further away an object is, the dimmer it appears. Leavitt and Pickering published a more detailed study in 1912, in which they proposed a simple mathematical relationship between the period and intrinsic brightness of 25 variable stars. This relationship is known as the period luminosity relation. All that was required to calibrate the relation was a parallax measurement of the distance to a single variable of the type observed by Leavitt. If this could be achieved, then the distance to the Small Magellanic Cloud could be obtained. In 1913, the Danish astronomer Einar Hertzsprung, in a spectacularly accurate piece of astronomical observing, managed to measure the distance by parallax to the well-known variable star Delta Cephei. Delta Cephei has a period of 5.366341 days and lies 890 light-years from Earth, according to modern measurements by the Hubble Space Telescope. Because of its historic place as the first of Leavitt's variable stars to have its distance measured, these stars are now known as Cepheid variables. Inexplicably, even though Hertzsprung managed to get the parallax measurement and the distance to Delta Cephei correct, his published paper quotes the distance to the Small Magellanic Cloud as 3,000 light-years, which is badly wrong. The modern-day measurement is 170,000 light-years. There is speculation that Hertzsprung made a simple typographical error in the paper and for some reason couldn't be bothered to correct it. In any case, the technique had been established, and 2 years later Harlow Shapley published the first of a series of papers that refined the method and led him to the first measurement of the size and shape of the Milky Way. He concluded that the galaxy is a disk of stars around 300,000 light-years in extent, with the Sun positioned around 50,000 light-years from the center. This is roughly correct. The Milky Way is around 100,000 light-years across, and the Sun is about 25,000 light-years from the center. This was an important moment in the history of astronomy, because it was the first measurement that relegated the solar system from being the center of everything. It's true that few, if any, astronomers would have claimed otherwise by the turn of the 20th century, but science is a subject that relies on measurement rather than opinion. The journey into insignificance had begun.
The solar system is in fact a system. Although we might feel isolated on a ball of rock in the dark, that is an illusion. No planet is an island. The system evolves as one. Draw a diagram of the food chain underpinning all complex life on Earth today, and at the base is a stream of photons generated 150 million kilometers away inside the Sun. Green plants are the interface between a star and civilization. Our understanding of Mars demonstrates that a planet's relationship with the Sun is not all light and sweetness. The star can provide the energy for life, but the solar wind can also destroy life or prevent it from ever emerging through the damage it can cause to planetary atmospheres. The solar wind emerges from the Sun's atmosphere, known as the corona. The temperature at the Sun's surface is 6,000 degrees Celsius, but the temperature of the corona is over 1,000,000 degrees Celsius, heated by energy transferred from the surface by the powerful solar magnetic field, twisted and coiled by the star's rotation. At such high temperatures, atoms cannot hold together. Electrons are ripped away from atomic nuclei, and matter exists in a fourth state, not solid, liquid, or gas, but a soup of negatively charged electrons and positive ions known as a plasma. Some of these particles are moving so fast that they escape the Sun's embrace completely, streaming outwards across the solar system at velocities in excess of 800 kilometers per second. This is the solar wind. When these high-energy charged particles reach Earth, most do not smash directly into atoms at the top of our atmosphere, because we are protected by our magnetic field. They are deflected harmlessly by stretching and distorting the field out on the night side of the planet. The stretched field occasionally reconfigures, accelerating electrically charged particles back down the magnetic field lines to the Earth's poles, where they collide with atoms and molecules in the upper atmosphere, exciting them and causing them to emit light. This is the aurora, the northern and southern lights. From Earth, the aurora can be seen by those lucky enough to be far enough north or south on the right night, when the sky is clear, the Sun is active, and the interplanetary magnetic fields are favorably aligned. From the lofty vantage point of the International Space Station, the aurora reveals itself as halos dancing around the poles. It is an unforgettable sight, undoubtedly one of nature's wonders. But as is often the case in science, and in life for that matter, the experience is greatly enhanced by knowledge. The lights, dancing faster than the eye can see or perhaps the brain can comprehend, are a direct result of the structure of atoms. Electrons shifting between allowed energy levels, determined by the number of protons in the atomic nucleus that holds them captive. High-altitude oxygen glows red. An atom is struck by a charged particle accelerated down the Earth's magnetic field lines towards the pole. The interaction shifts an electron into a long-lived excited configuration. If the atom is not involved in a collision in the thin air for around 100 seconds, an eternity in atomic time, the electron will shift down closer to the nucleus, and a red photon will be emitted. At lower altitudes, a different reconfiguration inside oxygen atoms causes the emission of green photons. This time the atom must avoid collision for around a second, still an atomic eternity in the denser air. Excited nitrogen molecules add a deep red or pink to the lower edges of the towering curtains of light during intense displays. This is quantum mechanics written across the sky, the structure of atoms revealed. To calculate the colors, physicists treat the electrons as waves trapped inside a deep well created by the electric charge of the protons. Particles imagined not as tiny flecks of matter, but as fields that can span great volumes of space. The energy to drive the display comes from nuclear fusion reactions inside the Sun, a factory 1,000,000 times the volume of Earth, converting hydrogen into helium at a rate of 600 million tons per second. The weak nuclear force acts slowly and grudgingly to convert protons into neutrons in the core, nuclear alchemy that results in the creation of neutrinos, which stream across 150 million kilometers at close to the speed of light before passing unhindered through the entire planet on their journey to infinity. Thus, 60 billion per square centimeter stream through your head every second without even a nudge, because your head is almost entirely empty space, and neutrinos hardly ever come close enough to interact with your sparsely distributed molecules. It might happen once in your lifetime. The nuclear forces at work inside the Sun also assembled the heavy elements that make up your body inside old stars long ago from hydrogen and helium forged in the first few seconds after the Big Bang: carbon, oxygen, nitrogen, sulfur, phosphorus, and iron. Gravity assembled the stars by forcing the collapse of primordial interstellar clouds, causing them to heat up in their centers and triggering the nuclear reactions that release the energy to halt the collapse for a few billion years, long enough for life to emerge in the gradient between the nuclear furnaces and the chill of the expanding universe. All of these thoughts are ignited in the imagination by the auroral display. Our experience is enhanced by knowledge. A central component of the web of physical processes that make the aurora shine is our magnetic field, which deflects the solar wind harmlessly past our planet and allows it to return in a much subdued form to the poles. Without this, the processes that Maven observes stripping the atmosphere of Mars would happen on Earth. The magnetic field is one of the most important differences between our worlds. Earth's magnetic field is generated by what is known as a dynamo, which is easy to explain in broad brush terms, but extremely complex and not fully understood in detail. The basic physics is simple. Earth's core is composed largely of molten iron, which is an electrically conducting fluid. Plumes of molten liquid rise and cool as they approach the mantle, and the Earth's rotation swings these columns around into circulating, rising and falling flows. This circulating flow acts as a dynamo and generates a magnetic field. The stability of the dynamo is related to the temperature gradient between the core and the mantle, the radius of the core itself, the rate of rotation of the planet, and numerous other subtleties. The rate of heat flow through the mantle is affected by geological processes including plate tectonics and volcanism. The precise nature of the flows depends on the constituents of the core other than iron, for example the sulfur content and distribution, and so on. It's fiendishly complicated, and because of this complexity, our planetary magnetic field gives every indication of being a delicate phenomenon. It was certainly delicate on Mars. We suspect there was once a Martian dynamo, because the Martian crust is still partially magnetized in places, particularly in the ancient southern highlands, suggesting that these rocks cooled in the presence of a global magnetic field. The Hellas impact basin, which formed around 4 billion years ago, shows no sign of magnetization, suggesting the dynamo shut down before this impact. Impact basins that formed over 4.05 billion years ago do show signs of magnetization. The Martian meteorite ALH 84001, dated at 4.1 billion years old, also shows clear signs of having formed in the presence of a magnetic field. These observations lead to the current baseline view that Mars had a magnetic field not unlike Earth's, which seems to have switched off just before the Hellas impact. From that point onwards, the atmosphere was exposed to the full force of the solar wind, and the Maven results tell us that this was likely the key driver for the loss of the Martian atmosphere. It would be tempting, but wrong, to suggest that the loss of the magnetic field was the trigger that drove the change from the Noachian to the Hesperian. The timescales probably don't match, and in any case the loss of the magnetic field wouldn't have led to an immediate loss of the atmosphere. Sputtering is a gradual process which still continues today. There have been speculative attempts to link the switch-off of the dynamo to the Hellas impact, or multiple impacts around the time of the late heavy bombardment. The idea is that the heating of the mantle can disrupt the heat flow out from the core, in turn disrupting the smooth convective flows. At the time of writing, the sequence of events is reasonably well established, but there is no consensus on how or even if they are causally linked. A complicating factor is the relative instability of the Martian orbit. The planet's obliquity, the tilt of its spin axis, varies by tens of degrees over timescales of a few 100,000 years in response to gravitational interactions with the other planets and the Sun. In comparison, Earth's axis drifts gently between 22.1 and 24.5 degrees in a 41,000-year cycle, and even this small change is responsible in part for Earth's periodic ice ages. Imagine what happened to the Martian climate when the polar regions with their reservoirs of carbon dioxide and water ice tilted towards the Sun by 20 or 30 degrees. The stability of Earth's spin axis is maintained by the damping effect of the Moon, which is unusually large relative to our planet. The Earth-Moon system might almost be regarded as a double planet system. The more we learn about other worlds, the more fortunate our presence on Earth appears. Despite all this marvelous complexity, the simple thought with which we began this chapter probably captures the spirit of why Mars died. The red planet is simply too small. It lost its heat more quickly than Earth from its smaller core and through its thinner mantle and crust. Geological activity fell markedly after reaching a peak during the Hesperian, and the planet faded. The atmosphere, held more tenuously than Earth's because of the planet's lower mass and gravitational pull, and unprotected by a magnetic shield, was stripped away by the solar wind, and the surface approached temperatures more in tune with an orbit far from the Sun. Mars's fate was sealed during its formation 4.5 billion years ago. It is too small and too far away from the Sun to have remained a vibrant, active world. Today, faint auroras still dance in the Martian skies, as photographed by ESA's Mars Express spacecraft. Blue ghosts of a Martian past generated by localized magnetic hotspots scattered across the planet, and the last traces of carbon dioxide in the atmosphere, energized by the relentless solar winds. Despite its 3 billion-year quiescence, Mars had a bright and active adolescence that echoes down the ages and may yet have profound consequences for us, confined for now on her planetary neighbor a solar system's lifetime away. There may have been, and may still be, life on Mars. We're looking hard, and the next generation of spacecraft may find evidence for Martians within the next decade. The discovery of a second Genesis would have important philosophical, scientific, and cultural consequences. It would mean that, given the right conditions, liquid water, active geology, and a sprinkling of organics, we would know that life emerges with a sense of inevitability through the entirely predictable action of the laws of nature. It would be confirmation that we, along with every living thing on our planet today, are an outgrowth of the planet, an extension of geology. We would understand that whatever magic we perceive in the depths of our souls has its origins in the interface between water and heat and minerals and gas. We are bubbling chemistry that thinks. If it happened on 2 neighboring planets in a single solar system, it happened everywhere. We would understand that we are part of a grand living universe. We are not God's children, but we are also not alone. Of even greater importance, I think, is the role that Mars must play in our future. Mars is rich in potential. It has reservoirs of frozen or even liquid water below the surface, and a great wealth of mineral resources, all the things that are necessary to support a civilization. Because of its history, this is a world in waiting, a treasure island in stasis. I think in my lifetime there will be Martians. The Martians will be us. We will go to Mars and make it our home, partly because there is nowhere else to go. Mars is the only planet beyond Earth on which we could even contemplate a landing in the near future. The message from Mariner 4 was not interpreted correctly. There is a second chance for us on Mars, when we feel ready to take it. I don't mean that we will leave Earth en masse for the new world. This is manifest nonsense. The Earth is by far and away the best planet we know of anywhere in the universe. We were born of it, and sculpted precisely and perfectly to flourish on it through the action of evolution by natural selection. Yet it is possible now to build a colony on Mars. I imagine a group of pioneers on the new world, living off the land and constructing the infrastructure necessary for tens, hundreds, and ultimately thousands of individuals to follow in their footsteps across the solar system and extend the human frontier for the first time in many centuries. Frontiers are important. The intellectual frontier is the domain of science, and where would we be without the pioneers who felt drawn there? The physical frontier is the domain of adventurers, engineers, and dreamers. And dreamers need somewhere to go. In Werner Herzog's film Encounters at the End of the World, a man named William Gierser describes the sort of person who gravitates to Antarctica, the last of Earth's frontiers. I like to say, if you take everybody who's not tied down, they all sort of fall down to the bottom of the planet. So that's how we got here, you know? We're all at loose ends, and here we are together. I remember when I first got down here, I sort of enjoyed the sensation of recognizing people with my travel markings. I was like, hey, these are my people. PhDs washing dishes and linguists on a continent with no languages. Mars is the step beyond the Antarctic, and perhaps we all need to take it in our imaginations. Our civilization feels untethered to me. We're at a loose end, huddled in a tiny corner of our